ben scherp, hè? I had 2 cups of coffee, so that helps.
Right, so we're going to have a book raffle. Basically, it's going to be first sign up for the raffle. You get a number. I think if you reload it, the last rate question is yes. There.
So we built extra.
Yeah.
Why are there crabs in space?
Well, that's one of the talks about.
Book signings. But we don't have a okay, sure.
Yeah, but it will be pretty more crabs in space.
Yeah, sure. Yeah. They call this comfortably cool. Yeah. Here, yeah. Especially the lights. I could really feel it because I had a different hair. Also, first time this year, they was like, oh, maybe I'm going to get sunburned. Outside. I don't think this today will be as Welcome back, everyone.
Hello, hello. Good morning. Good morning.
Good morning. So I had a great set of talks yesterday. I really enjoyed every speaker. Also, gorgeous weather.
Yes, a little bit less so today.
Yeah, probably not as great, but we can hope.
But that's also good because it will be less hot in here, I hope. So maybe that will be a little bit better. Yeah.
Maybe we should introduce ourselves. So we are your MCs for today. My name is Wouter.
And my name is Sterts.
Hello. I was wondering, how long have you been using Rust?
Ooh, I think it must be over like 6 years now.
6 years. Oh,
Yeah. What about you?
Me as well. Yeah.
Wow.
So,
Great.
almost brothers. Okay. To kick off, first mention, I would like to say that please follow our code of conduct, which is the same as the Rust code of conduct.
It is not. It's the Berlin Code of Conduct, but
Oh,
you
Berlin,
can find
okay.
it online on our website.
Yeah.
And
It's a subset. Maybe, yeah.
It's,
Anyway, the code of conduct also applies to other events related to this event. So, for example, if you have organized a dinner or the unconferences that are happening after this conference from the various working groups, please also abide by those code of conduct rules there. Yeah.
All right. Should we get on to the schedule?
Sure.
Right, there it is. We have some great talks for you lined up today. There's also some workshops. If you're here and you signed up for a workshop today, then you're in the wrong spot. You should be in lab. I hope everybody's in the right place.
There will also be book signings today with Mara Bos and Luca Palmieri. There will be also, I think, a raffle.
There will be a raffle, yes. If you want to join the raffle to win some books, come in the next break, come here to the stage. We'll give you a number, and then in the break after, or whenever we'll announce, it's a bit, you know.
Sign up at the first break, that's the important data. Yeah.
You get a chance to win some books.
Yes. The agenda for today is, so we have these talks. You can find them also online. You already probably have found them. At the end of the day, we'll have drinks from 5 till 7. And, well, we'll only have talks today. So,
yeah. And also at the end of the day, there will be boats again. But no tour this time, just straight boats to the station. Okay, then a quick shout out to our sponsors again. Yeah, all of these lovely sponsors who made this event possible and allowed us to do what we do.
I think we have some bookkeeping also as well.
We have some bookkeeping, yes.
Yeah, so like we have lost items. You can find them at the reception. I think the game console that was announced yesterday that was lost and found is still not retrieved by someone.
It's still not retrieved, but yeah. Oh, it is? Okay, great. And the keys have been found as well, but if you lose anything today, it will be at the reception, hopefully. If we find it, it will be at the reception. Hey, thanks. Yeah? More things to win at the book raffle. 20 microcontrollers for Rick Arends.
Really want one. So it's not like, oh, it's free, but if you want embedded Rust programming, I have 20
We'll collaborate with Rick to organize
surprise.
something to get 20 microcontrollers.
Okay, speaking of game consoles and stuff, you might have seen some Bevy games on the big screen here during the breaks. We've collected some of those from the Bevy community. And we're very happy to have them. There's also some Ratatouille apps on the sides sometimes. There's like a slideshow of things. So that's just to explain whatever was going on there. I think that's it. I think we can go to the first speaker.
Yeah, the first speaker. We are very honored to have our next speaker. She has helped to create a lot of things, like the Rust Leadership Council, small thing, new shell, but also TypeScript. And has worked at Mozilla on Rust compiler errors, IDE support, and the Rust ergonomics initiative. She has served at the Rust core team, and she is here to unveil a new secret project. So give a warm hand of applause to Sophia.
Wow, thank you for the warm welcome. That is way late in my presentation. It's, ignore it, ignore it. Close your eyes, close your eyes. OK. Hi, everyone. So my name is Sophia. Today, we're announcing a secret project. Before I do, thank you for the warm backstory. I did have a lot of luck and worked on a lot of really cool things. One of the things that I worked on for the last few years was actually teaching Rust professionally. And a lot of us have been using Rust. OK, I want to get a kind of a show of hands. How many people feel really comfortable in Rust? Raise your hands. OK. And then drop your hand. Now, you're allowed to drop your hands if you've been working in Rust for less than a year. Oh, look around. OK, that's how long it takes. So in teaching Rust, one of the things, yeah, you can set your hands down. In teaching Rust, one of the things that I notice is watching people's faces when you're teaching Rust for the first time. Some of you who've been teaching Rust have seen this look. You start explaining one concept, you're like, hold on, hold that thought, and you start teaching another concept, hold that thought, you teach another concept. And eventually it starts to click, but it takes a long time for things to click. So I started thinking, can we bring safe systems programming to a larger audience? So here's the secret project. Here's our secret question we want to answer. Is it possible to bring safe systems language that's easy to read, easy to teach, and easy to learn? Is this even possible? Does it have to have the complexity of Rust to be a safe systems language? So, introducing a new project called June. I've been working on this project for the last year and a half to try to answer this question. So here's our goal. We want that readability. We want that teachability. In fact, during the last few years, I've been talking to a lot of friends in the industry. And some of the people I've been talking to are Go developers. And I was like, is it even possible? This sounds wild. Is it even possible to have a safe system language you can learn in a weekend like you can with Go? We also wanted having the ability to teach quickly or to learn quickly. We pair that with being able to maintain it as well. So we're not giving up too much. We want a code base that grows. And as it grows, we're not accruing a lot of technical debt. As well, as you can imagine, I spent a lot of time working on Rust. A lot of blood, sweat, and tears, as we say. And I want Rust to continue to grow and thrive in the areas where it's great. And I think that this can be kind of a sister language to Rust. For the things that Rust doesn't focus on, we can focus on. The kind of focus areas of Rust and embedded and like high-performance systems, that's great. But what about application development? We could have a design of a language that fits well for application development with a bit of a systems flavor. As they sit together, they cooperate. So that's the kind of thing that we've been thinking about. OK, review. I'm sure everyone is looking at this slide going, what the heck? That's not quite Rust. So what are we missing? Lifetimes. Not just lifetimes, but say louder. Okay. There's some syntax. Well, okay. So when we say lifetimes, what two things do we mean when we say lifetimes? Yeah, we've got parameters and annotations, right? So if we stick those in, okay, yeah, you and your semicolons and commas. Okay, so this is starting to look a little better. But if you think about this from the perspective of what do you have to teach to understand what you're looking at? When I started working in Rust, it took me months to understand this because, as we think about it, there's about 5, give or take, different concepts that work together. And as they work together, you begin to understand what you're looking at. We have the concept, the general concept of lifetimes, then annotations, parameters, the general concept of ownership and borrowing, and how that goes with the ampersand, and of course, generics. So not only do we have lifetime parameters, they're part of the larger generic system, and you have to understand the relationship. It's quite complicated, but it's quite precise. It's one of Rust's core strengths, is to be able to have this kind of memory precision. So the question is, what happens if we don't have this kind of precision? If we loosen it just a little bit, what happens? So that was one of the questions I wanted to ask. Because I know that if you want this kind of precision, you get this kind of complexity. Okay, so this is what we're going to do. We're going to think in groups. Groups of related allocations specifically. If we make a linked list, so we've got a 3-node linked list here. If we thought of this as separate lifetimes, where each piece of memory has a separate lifetime, this can get pretty complicated to encode in our lifetime system in the kind of bar checker. But if we think about all of these as having a single lifetime, imagine a pointer pointing to the head. That single pointer could have a single lifetime, and everything that you reach to that pointer could share that lifetime. Has some interesting trade-offs, but has some really interesting benefits. So let's talk about the benefits. Before we talk about the benefits, though, I have to show you some code so that we can build up to seeing these benefits. So let's see some June code. Here's our first piece of June code. How many people can read this? That was quick. All right, so we're readable so far. That's good. We'll check in later about that. So we've got our struct, and we're creating a new employee. And that new keyword is handling an allocation and construction, just like it would in something like Java. For us, in this language, we actually don't have a borrow checker, but we do check the lifetimes of things. And in fact, we infer the lifetimes of things. So here we're going to start inferring the lifetimes of the pointers that you're creating. New employee is going to create an employee pointer. And to understand the lifetimes of that pointer, we start asking questions. Because all the lifetimes come from a group of related allocations, we kind of collapse the idea of lifetimes to something very simple. Does this pointer escape the function? Yes or no? No. So we have a very simple name for this lifetime called local. No tick A or tick B, just local. All right, see another example. Slightly bigger. Raise your hand if you can read it. All right, okay. It's warming up. Okay, good, good. All right, so in this example, we're a little bit more complicated. We have our instantiation of our employee, then we pass it to setStats, and setStats updates the employee with the new stats object. All right, so our question now is, what is the lifetime of the pointer, the new stats age 33? Well, does it escape the function? Yeah, how does it escape the function? Through the, through employee, through the parameter. We'll call that param employee. So it turns out there are 3 different ways that you can escape the function. Or you can not escape the function. You can escape through a parameter, or you can escape through a return value. And those are 3 different lifetime names that are very readable, that we can kind of present in error messages, and we can teach very easily. Okay, there is a bug in this code. Raise your hand if you can see this bug. Ooh, it's subtle. One person. I'm very excited. Anyone else? Okay. I mentioned that allocations are grouped. So if an allocation is grouped, it lives as one and is freed as one. What happens to new stats age 22? It kind of leaks, yeah, but it doesn't leak in a traditional sense. A traditional leak, the memory is gone and you can never reclaim it. In this sense, you can kind of think of it as a memory bloat, quote unquote, in that it's part of the group and it's just going to stick around until the group is finished. So that's going to be part of our trade-off that we'll have to address as we develop this idea further. And we'll talk about some of the ways that we'll address it. So keep that in mind. Okay. Now let's have some more fun. Linked lists. Raise your hand if you can read this one. Yes. Pretty straightforward, right? It feels kind of like Java, or something lightweight, something garbage collected. So we create our linked list, we just set it up, and we're done. All the lifetimes coagulate? What's a good word? Collect into a single lifetime. And that gives us the flexibility to do this. We make a circular linked list just as easily as we made a singular linked list. Raise your hand if you want to write that in Rust. I thought so. Yeah. So having that single lifetime simplifies the lifetime system down to the ability that we can make any arbitrary data structure we want as easily as possible. Obviously, like I said, there are trade-offs, but these benefits are plentiful. Okay, on we go. Let's take a pause. I just made a circular linked list. What rule did I just break? Think in Rust. If I have references, what am I allowed to do? I can have? Well, it's circular, yes. But if I have references, if I have two mutable references to the same thing, is that okay? No. Why? What did I just do? Yeah, see? Aliasing, mutable aliasing. What did I just cheat on here? Well, it's not actually that. They are real pointers. Yeah, I bent a rule. So I have a mutable pointer and another kind of like another pointer pointing the same thing. We've got an alias. That would not be allowed in Rust. So let's take a second and think about it. See if I have a slide for that. Yeah. Before you do, let's do a little quiz. Why? Let's do two mutable pointers pointing to the same thing. Why is this bad? Yeah, that's the big one. If I have that same thing copied twice, put one on each thread, and I write at the same time, there we go. So clearly we need to protect ourselves against that. So what are we going to do? Just like Rust, these kinds of shared pointers are not allowed to be sent between threads. Okay? Now we're down to single-threaded, two mutable pointers, or one mutable pointer, one immutable pointer pointing the same thing on a single thread. What happens now? Well, you get some tricky situations. Yeah, I see you back there, Nico. So one of the big ones that you're going to get is kind of spooky action at a distance. That's what you might call it. So I write to something in this area of the code way over here, and I observe it way over here. And it's difficult to debug, right? So we need some solution to that as well as classic things like iterator invalidation. Okay. So one way we can think about it is we need to kind of isolate ourselves when we have these kind of shared pointers. You can kind of think of the graph. If this helps your visualization, great. If it doesn't, fine. But you can kind of think of this interrelationship of owners and pointers, and they're kind of pointing onto each other. And there could even be like more complicated relationships, like some pointer pointing to some faraway place. What we need to do is to discipline this graph of relationships that are happening in your program. One way we can do that is through, like I mentioned, isolation, by kind of cordoning off the group of related shared pointers from everything else. If we can prove that they're fully isolated, then the kind of spooky action at a distance disappears. And we have a set of clear ownership patterns, and then in little fenced-in areas, we get to bend the rules a little bit more because there's a discipline to it. Okay? So what does this look like in code? There happens to be something that we can use from object orientation to get this kind of isolation. Encapsulation. So if we go back to traditional encapsulation, being able to say that information is hidden from, or I should say the implementation information is hidden from the rest of the world, we can say, all those shared pointers are stuck inside of the class, and that doesn't leak out. In fact, let's tighten encapsulation even a little bit more. If we do that, we can enforce that no pointers go in and no pointers go out that can create aliases to the inside of that class. Okay, once we do that, now we can have that full graph isolation we were talking about. Okay, so in code, this is not scary. I don't know if we'll actually use traditional classes like OO. We'll talk about that here in a second. But the idea holds. We've got a class. We've got a private data. We have the ability to kind of create new of these circular lists. We can create a nice API around this. And we can prove that nothing is aliasing into this or out of this. This gives us some really cool properties. One of them is, if we have an instantiation of this class, we can make that a single owner instantiation, right? Once it's single owner, we can send that between threads. We've just given ourselves thread safety and the ability to create any arbitrary data structure we want. Because of encapsulation, we can create a clean API, just like we can with traditional classes and whatnot. We've got all private data, and then we can create our set of methods and a clean way into working with it. I mentioned before that this does have some trade-offs. So we saw the flexibility. We can make arbitrary data structures. We can kind of isolate them. But we saw the memory problem from earlier. How do we fix that? So one of the things that encapsulation lets us do is to fix it, is to say, here's a set of pointers that we want to track and then we want to work with and potentially recycle. So let's talk about that. The traditional way of working with memory like this, if I have all of this memory that's going to live together and then die together, I can't just pick a little piece of it out and free it, right? Just like you have like an arena-style allocation, you have like everything lives and dies together. But instead, we can use a classic technique like free list. We can take that piece of memory and then put it in the free list. And if we need some memory later, we can just pop it out of the free list and use it. But the problem with free lists is that they're not safe. If I accidentally put something on the free list that has an alias somewhere else, that's not okay. So what we need to know is if we have multiple copies of that same pointer, if we do, then we don't allow you to recycle it. Okay? So we need to build this into the language. You'll be able to annotate a class. You'll be able to track all the pointers in that class. And then when you want to recycle one of them, you can just say recycle that pointer. And it will only allow you to recycle it if that's the last copy of that pointer. Does that make sense? Everyone's kind of staring at me. Yes? Okay. So we have a kind of balance here. By having a flexible system that groups allocations, we have the ability to describe, like I said, any arbitrary data structure. The code is very easy to read, easy to use. And having been using it the last few weeks, I can tell you it is actually quite a joy to write in because you never have to think about anything. And then when you need to tighten your memory up, you can use this safe memory recycling technique to say, okay, here's a node. I'll recycle this node, and then I'll reuse that memory later. Okay. So I kind of touched on some of these. These are some of the things that are coming up. There's going to be a recycle keyword. It's not automatic because it's a linear time operation. But yeah, this gives us that safe memory recycling. All right. So there's a lot of work that we're going to be doing. We have a reference compiler that we're going to release later today. And in that, most of what's in this talk is already implemented, except for the safe memory recycling. That will be coming in the coming weeks. We also want to add better abstractions. I kind of mentioned classes. I didn't want to talk about the experiments that we're doing, but we want something that's like object orientation, but is even easier, even more composable, even more modular. So that's another thing that we'll be working on. As a sister language to Rust, one of the things that's really, really important to us is to be able to interop this language with Rust. We want something like the Rust stable ABI to be in place so that June is not isolated from the rest of the world, that June can connect to not only to like C-based APIs, but also Rust ones, connect to the Crate ecosystem, and to be part of kind of the greater kind of Rust or safe systems ecosystem. So we're definitely looking forward to kind of collaborating on ways that we can do that. And finally, there's quite a lot of new techniques that are coming up in working with memory in a safe way. The creator of Veil recently put together a list, and there's something like 14 kind of unexplored memory safety techniques, in addition to, say, the borrow checker, that we're very much looking forward to kind of continuing this exploration. So you can kind of think of June not as something that we're trying to ship today as a 1.0, but as like opening the conversation about how do we make safe systems programming open to a much larger audience, and then continuing to kind of grow that over time. Okay, so here's some of my socials. The GitHub repo is not yet public. That will be public soon, and there's going to be a blog post very soon that comes after this talk. That's going to go live. That will go into a little bit more detail and give you a little bit more of a place to jump in if you're interested. Okay, any questions?
Thanks, Sophia. That was great. Are there any questions about this? I see one of here.
Thank you. Is there an overlap between Rye and June?
So Rye and Truffle, which was another one that was secretly released about a week ago, are embedded in Rust itself. This is completely a standalone language with its own compiler and everything.
Okay, and it's not going to be interpreted, it's going to be fully batched?
There may be a REPL at some point. People that have been following my new shell work know I'm quite a fan.
All right, in the back there.
You mentioned Rust interop. How do you do that without a stable Rust ABI?
You can't, unfortunately. So we would have to emit Rust and play inside of Rust's way of thinking about the world, which is considerably different than the June one. We did play with that idea initially, but I think the path forward requires Rust ABI. Something like Avigno's work would be chef kiss perfect for this kind of interop.
Thank you.
There's one over here.
So when you're talking about the safe linked list, you're talking about kind of an encapsulated set of pointers where the pointers weren't allowed to escape. And I was wondering how you would then iterate over that list, because in Rust you would maybe call iter and you'd again get a reference to each item. But if the references can't escape, then how do you do that?
Yeah, there's a couple of ways that we're playing with. I'm not sure exactly what's going to become the quote-unquote June standard way of doing it. We're playing with the idea of generators, so being able to pass in a block that runs, and then the container can safely run it over the elements. There will likely be a kind of borrow as well that's very limited. So you can ask the container, hey, I would like the item at this location, and it lets you borrow it in a very kind of local scope that doesn't escape into a struct or get returned or whatever. So we will have some limitations like that. That will allow you to access and iterate.
I mean, some of you're inferring many properties to allow the lifetimes to be as you shown. Couldn't you instead have that implemented in Rust itself?
You can't, because it's just exceedingly different to what Rust does. There is a package, though the name of it's escaping me, that gives you some amount of that, but part of the tricky issue with Rust is that the Rust learning curve is immediately going to hit people. They have to learn some amount of Rust. And with June, we just remove all of that. We go straight to having a simplified memory model for the grouped allocations. And that's really the big win at that point.
Just a quick question. How do you write the compiler? I mean, which language do you use to write the compiler?
It's not self-hosted yet, but I'm sure at some point it might be. It's all in Rust currently.
In the first example you gave of working with the employee record, you passed that to a function, modified it, and then looked at it in the caller. And it looked like there weren't any sigils on the parameter type, so it seems like you're by default passing by reference and allowing that to be mutable. How
yeah, I
do
guess
you
I
do
kinda-
pass by value if you want to?
Yeah, so I kind of breezed over this. It's kind of hard to introduce the language and all the little nuance all at the same time, but this actually brings up a really important point. Everything that you're creating in June is a pointer. Every pointer has a lifetime. So every bit of user-defined data is always a pointer. If I pass that pointer to a function, it's a pointer to that function. The function says the binding is mutable or not. If it is mutable, it's a mutable pointer. So that's one of the things that keeps it easier to read, is that we remove this, like, the differentiation between reference and value and whatnot. It's just all pointers.
So what do you do in June if you want a type that has value semantics, like something that feels like a number, for example? Like, I can pass it, I'm passing a copy, I'm not passing the original.
There is currently no way to do that. We have enums and pattern matching, though I don't show them here. And we may at some time have a record-y kind of thing, but one of the things that we're trying to do, like we did with New Shell, is start with the basics that we think can bear the most weight, can kind of carry us forward the best, and then only add the things that we need as we absolutely need them to keep us as kind of streamlined as possible.
Hi, so thank you for your talk. It was great.
Sure, thank you.
And I had a question because one of the big draws of Rust, at least to me, is the very elegant way of error handling. And I was wondering what that looks like in June.
That's one of our favorite questions. It's currently being designed. So Jane, my collaborator, is sitting right behind you. And we are both, as you can imagine, exceedingly passionate about errors. Since I created the compiler errors and she worked on error and some of the important machinery for error reporting for users. So these are conversations, Jane can tell you ad nauseum, that we have been exploring and exploring. We'll continue to explore because we want this to be top-notch.
There's a question online. What about lists and iteration? What about lists that are iterated and updated while in iteration? Is that something you support, and how would you do that?
Yeah, so the iteration story we were talking about before is still kind of in progress. We want to kind of pick the right balance of features so that as it lands, it can kind of do more work than just kind of simply iteration. Sure, whichever's next.
All right. I think that concludes the questions. You've answered them all well.
Okay.
All right, give a big applause to Sophia. All right, now I'm going to announce the next speaker. The next speaker is Kevin Boos. He is currently a principal architect at FutureWay, and he's working on Project Robius, where he's a tech lead. And Project Robius has as a goal to create a seamless multi-platform app development. So it's a community-wide project, I believe. Am I saying that right? With multiple frameworks, making them work on all platforms. Take it away.
Great. Thanks very much. Give me a second. Could I have my laptop screen on the projector? Oh, there we go. Thanks. Is that orange or is it just me? It's like quite... I don't think I have the night shift on, but I will check that. Okay, that was fast. It looks okay on my screen. I'm not sure. Oh, is it per display? Yeah. Okay. No? Okay. We'll just... All right. Well, you'll just have to deal with that. Please don't fall asleep. Okay. Yep. I'm from Seattle, so I appreciate the gloom. Okay, great. Yeah, I'm going to talk about a relatively new project that we've embarked upon in the last 6 or 7 months called Robius. The goal is to bring seamless and immersive multi-platform app development to Rust as a purely native Rust project. So at a glance, this project aims to, like I said, create a multi-platform app dev experience entirely in Rust such that developers can leverage all the great features of Rust that you know and love: robust ecosystem, safety, performance. The developers wouldn't have to deal with multiple languages or different environments, as is common with these bridged approaches, where you're bridging to Flutter or something like that. And ideally, they would never have to write a single line of platform-specific code, though they could if they wished to, but it wouldn't be required by default. Sort of a second sub-goal here is that we want to make mobile a first-class concern in the Rust community. I think over the past 6, 7 years since, well, I guess it's 9 years since Rust 1.0 had become stable, mobile has sort of drifted behind embedded and systems programming use cases, so we want to elevate that to sort of a first-class citizen. A little bit of a background here. So Project Robius is fully open source. It's decentralized. We have collaborators across North America, South America, Europe, even Australia, New Zealand, and China. We try to keep all of the projects, the individual parts under this large umbrella, somewhat independent, and we let the communities drive each one of those. So I'll talk a little bit about that later. But as I said, everything's entirely written in Rust. So why do we need a project like this? Like, what's the main motivation behind this? There's already a lot of great Rust UI toolkits out there. You're probably familiar with many of these. You saw demos from MakePad by Rick yesterday. And all of these other projects have done a great job of bringing a relatively nice UI experience to Rust. But there's a lot more to developing an app that has immersive features and leverages the platform nicely and robustly than just drawing UI widgets. Because of that, a lot of existing Rust apps, for example, Signal, the Signal Secure Messenger, an app commonly referenced as a major Rust project, actually has a lot less Rust than you would think. There's sort of a Rust core, and then all of the platform-specific stuff for each platform, Android, iOS, desktop, Electron, are still using those native things. So there's not as much Rust as you would think. So let's dive a little bit more into the motivation behind this. So I think everyone who frequents the Rust subreddit or Hacker News or any kind of Rust forums has frequently seen posts like I'll show in a minute where app devs are expressing a desire to use Rust, either front-end devs who already are familiar with other app toolkits or Rust devs who want to experiment with front-end dev, but they're not sure how and where to start because of all those offerings I mentioned before. It's a little unclear which ones you use. And these projects are independent, which is a good thing, but it's not always clear how to integrate them together into a functional toolkit, something as powerful and integrated as Flutter. There's obvious business advantages. These are the same as Flutter and any multi-platform app dev toolkit like React Native. You get that nice, consistent experience for both the developers and the customers, and you get to avoid the redundant development effort of tinkering with multiple different platforms. And of course, as we all know, Rust is great. I don't need to spend too much more time emphasizing this for this crowd, but we get these traits here, which is super nice, no pun intended. Right, so our goal here is to attract front-end developers to the world of Rust and then also allow existing Rust experts to experiment with front-end dev and maybe develop an app of their own. So these are some of the posts that I was talking about. There's just sort of an endless amount. Right? So if you've seen these, you're probably getting a little bit tired of these, especially if you are a UI dev, right? So you're saying, okay, that's not great. So as I already mentioned, there are a variety of Rust apps, but they typically suffer from platform-related pain points. So I mentioned the example of Signal already. So it sort of looks like this with the main Signal business logic written in Rust in this lib, oh, you can't see my cursor. Oh, you can. In this lib signal here. And then on each platform, it's whatever is the native wrappers, the native UI dev toolkit wrapped around this lib signal. All right. So because of this, you have to maintain a bunch of different projects, which makes it hard. You don't have that nice luxury of a single code base, which is what we're aiming to do. So on iOS, Signal has an additional almost 500,000 lines of code. That's in Swift and Objective-C. On Android, 1/3 and on desktop, because it's Electron, 250,000. But still, that's a pretty significant per platform effort. So I can probably skip this stuff about Rust. We all know Rust is great. It's most wanted. And we get these nice features, right? Okay, so I'm anxious to get to demos, so I'll skip through this stuff. But I do want to highlight a couple of motivating shortcomings from Rust, from a UI standpoint. So a lot of app developers and UI developers typically are expecting this familiar object-oriented programming patterns where one widget can inherit from another widget, so that's something that's a little difficult to accommodate in Rust. But many of these UI toolkits have developed DSLs specifically for that to get around that problem. Another frequent complaint we hear is it's hard to realize and deal with shared mutable state where you have multiple different UI entities all trying to share and mutate some data. So this results in this sort of closure-based callback pattern, which some UI toolkits have avoided, some have emphasized. It can be good or bad, it depends on your viewpoint, but there's a little bit of a schism there. And then, of course, everyone's classic complaint about the Rust compiler being slow, which, again, I don't necessarily disagree with. I don't necessarily agree with, because we often give it too much work to do, but folks like Nick are working on that every day. One other potential problem, which I think is relevant to what Sophia just talked about, there's potentially a very steep learning curve for front-end devs who are used to something like Java or React Native's nice syntax. Rust can be a little bit of a thorn in their side. So there was a nice survey from a consultancy venture called Very Good Ventures where they found that mobile developers needed around 3.5 months of retraining to switch to Flutter. So that could actually be worse for Rust. So our goals are to kind of address some of these motivating challenges and see if we can make things a little bit easier. I'll just talk about some goals. The first one is we want to sort of create a reference design of the full system stack where we have all of these independent projects all coming together in a way that is known to work and can just be grabbed and used immediately by a developer who wishes to create an app in Rust. I'll talk more about this later, so we don't need to go into the details just yet. We also want to establish and publish some proof of concept demo apps, not just simple ones where you can see how to do something like recreate eBay or a Taobao style e-shopping app, but also more like commercial or mainstream grade flagship apps. For example, I'm working on a Matrix client, and I'll demo a imitation of Xylm Studio that other folks in our team have worked on. The general meta goal here is that we want to make everything easy for a new developer to fork and quickly modify with nice code, well-structured code, and great documentation. Obviously, easier said than done. So some of the technical goals, I'll just go over them real quick. We have things split into build time and developer tools, and then runtime behavior. I'll just talk about two real quickly. So quick compilation I already touched on. As you saw with MakePad, and if you've seen presentations by Dioxys and other folks, a lot of these Rust UI toolkits combat this slow compilation with live reloading of the DSL elements, which allows you to just quickly change styles and things like that without recompiling Rust. So that's great. Another thing we can do is establish a structure of many small crates, which actually happens to align very well with the sort of decentralized, community-driven individual components. We get the benefit of parallel compilation, and we also strive to minimize dependencies such that we're not compiling a bunch of unnecessary things. I think Rick touched on that a lot yesterday, so I won't go into too much more detail. And then if we can't get all of this, at least we want to make incremental compilation very fast. And then, of course, I already briefly mentioned consistency across multiple platforms. This is sort of our key principle. We don't ever want developers to have to touch platform-specific code, but it shouldn't be too hard for them if they wish to do that. And also, we want to impose the bare minimum of overhead. Okay, so let's get on to some significant challenges. So as you can imagine, a project like this is a multi-year endeavor, and one of the most difficult parts, I think, is how to deal with and abstract all these widely varying platform APIs and OS services provided by the underlying platform. Like even on mobile, just Android and iOS are significantly different, and that doesn't even bring in the complications of the various desktop platforms. We need to handle very complex build procedures where we're not just compiling Rust, which may itself result in compiling platform native code like C or Java, but we also need to support these platform-specific tool chains, linking conventions, and then things that Cargo doesn't necessarily support, like arbitrary post-compilation steps. Then, if you want to actually publish an app and distribute it on the App Store or a package manager on Linux or something like that, you need to generally sign, bundle, and package it properly. And in some cases, this is actually required to even get basic features to work, like displaying system notifications on Apple platforms. So the real challenge here is doing all of this in a somewhat consistent way across widely disparate platforms. We also have a variety of other challenges that we're tackling. One thing is dealing with mixed forms of concurrency, where you have UI threads and some platform APIs that UI workloads and platform APIs that only want to run on the main thread. Otherwise, they throw an error or they just don't display anything. And then some APIs, for example, from an SDK, like the Matrix SDK, typically require you to use async, whereas some other system APIs don't allow. They don't offer any async capability. So this is something that throws a wrench into our plans. And then, of course, we also want to support multiple different UI toolkits, right? So a lot of our work so far has been focused on MakePad, because I think that presents one of the more difficult UI toolkits to deal with, because everything is done from scratch natively. So if we can do it for that, I figure we'll be able to apply these other these platform crates and various features to other UI toolkits like Dioxys with relative ease. Okay, so we also have a joint white paper coming out, which Nico Burns is organizing. And it will be sort of covering the state of Rust GUI systems and the challenges therein and what we plan to do with that. So look for that sometime in the summer, TBD. Okay, so let's get into some specifics of what Robius actually comprises. So we have a pretty diverse community of various projects. So the Robius project itself is sort of just an umbrella that deals with the overall integration and basic app dev concepts. I myself am working on that, as well as platform feature abstraction crates across different platforms. The Osiris project is run by David Reinsberg. I think he's here somewhere, but he also gave a talk on Monday, if you were there at the GOSM. But this is the project that deals with signing, bundling, packaging, and distribution of apps, dealing with how to wrap Cargo properly for that, and then also some wrappers around the lowest level OS services on each platform. We have a meta build project called Quake Build, which is similar in concept to Make, runs on top of the lovely new shell that Sophia has worked on. And this is developed by Cassandra. I'm not sure if she's here. But this is a really cool up-and-coming pure Rust build project that we hope to use to drive the top-level build procedures that we'll actually call Rust. And then there are some other projects I already mentioned, like Concurrency and dealing with the mixed forms of async and UI main thread stuff, as well as how to properly cache widgets when you're populating and drawing data that may be expensive to do. We hope to target, well, we are targeting, but we hope to target more of these UI toolkits. Our collaboration with them, it varies based on the project. With MakePad, I work with Rick Daly to request features and drive development there, and make contributions back to MakePad when possible. I aim to start doing that for Dioxys as well, but for our platform-specific feature abstraction crates, I have targeted Dioxys in some of these cases, which on mobile, it generally uses the same infrastructure as the Towery project, the RAI backend. And then we've begun some very light periodic exchange of ideas with the Linebender project. So we hope to make this flourish more in the future, but that's kind of where we stand with all of the different projects involved in this. So in terms of a philosophy, we generally want to stay out of the UI's way. I'm not a UI person. I don't want to deal with that stuff. I want to let those experts do what they do best and just fill in all the other gaps here, right? So like the concurrency management, platform abstractions, and all these nice little features that you need just beyond the UI. So these are sort of passive libraries that will allow any app dev logic or any app logic or UI logic to drive these platform features and access them in a somewhat consistent manner. So I have an app called Robius, which is a matrix client, matrix chat client, and in the future we'll make it do more things, but if you were to kind of overlay the architecture of a complicated app on top of that reference diagram, it would look something like this, where you have a bunch of different features. And I can show another diagram later about how we deal with the concurrency challenge. But let me just say, there's quite a lot of different platform abstractions that we're targeting. You can also consider some of these OS services. It's all the things that are local to a system. I'm not talking about like accessing the Google Maps backend or something, right? So things like notifications, drag and drop, rich clipboard, MakePad and some other UI toolkits, like the ones that use Winit, they support this to some extent. But there's a lot of other things that many of them haven't dealt with because that's not, I think to be fair, it's not really under the realm of UI toolkit development. So things like accessing your location, dealing with connectivity management, sensor access, these sort of things. So there's quite a lot to do, and as I said, this is a relatively new project, so we're just getting started, but this is kind of where we're at right now. Orange are things that are in progress, green are things that are done. And I should also say that we aim to reuse projects from the existing community already. So for example, the Tori project has worked hard on a lot of nice utilities for desktop, so we can use like the Muda crate, M-U-D-A, for the menu bar on desktop. We don't need to, re-implement everything ourselves just for the sake of doing it. Our philosophy when implementing these platform abstraction crates is just to be as close to native as possible with a bare minimum of overhead and try to minimize the set of dependencies that we use, that we require, rather, for each one of these platform abstractions. So a good example of this is if you're communicating with some platform API on iOS and you need to provide a callback, I think that's an Objective-C block, right? You would think that you want to do that in an async manner. But so what you might initially do is to use Tokyos, like one-shot async channels, to communicate the result of that back to the main thread. But in a lot of these cases, adding Tokyo can triple or quadruple your compile time if you have a very small MakePad app, as we saw yesterday. So we're trying to avoid these as much as possible, or just make them optional when desired. We have quite a few platforms that we're targeting. I think this overlaps with many of the UI toolkits, since we obviously need them to support these first. The ones in green are, I think, our major platforms that I've tested our apps with, and the ones that we test most frequently. In the future, we want to integrate with OpenHarmony and the Oniro project, which is a sort of a European distribution of OpenHarmony. And also web. I haven't spent a great deal of time on that, but some folks in the community have. And then there's some others that we could potentially talk about later, but that's where we stand now. Okay, so that was a lot of boring, I think, boilerplate. So let's get to some cool demos. Here we go, or hopefully cool. So here is my Matrix client. Can we all see that? Cool, yeah. Somewhat basic, but this is written in MakePad, and here, hopefully internet's all working. Yeah, so the performance is great. You can see we're using platform-specific features when required. One thing that I wanted to highlight, just because Rick didn't talk about this yesterday, is rich text formatting. So that was actually somewhat of an adventure that we went on for a few months. I know that Rick loves to show off some really cool demos, like here's a fractal that I can run on an Apple TV, but I was like, that's great, can we please display bold italic text? So, took longer than you think, but yeah. So we're kind of the, I guess, practical side of things compared to the eccentric genius of the rest of the MakePad crew. So we were asking for things, just like displaying block text and things like that. So you can see this is mostly to MakePad's credit. Their performance is really good. It's nice and fast. Hopefully that's coming through on the projector. On my screen, it's gorgeous. And a lot of this stuff is provided by MakePad, but we also do have a few things that we've integrated into this, like opening links and URIs, sort of like a share sheet on mobile, and authentication for things like accessing encrypted rooms. So I can give you demos of that too. Hopefully this works. So this is the exact same app, same code base, 100% the same, no platform-specific code, running on Android. Okay, yeah, I don't know what happened to the text. It's very strange. Well, it doesn't normally look like that on an actual device, but the same sort of thing. Everything's nice. Generally working, so I'm relieved that that's working. But yeah, this is a single code base, no platform-specific code. And right now, it's a very mobile-oriented UI, but in the future, we plan to make it a little bit more of a responsive UI with different types of viewing panes, like a multi-pane, sort of like your IDE, for different rooms simultaneously, and then integrating some LLMs, like AI features into the Matrix chat experience. I talked about some of this on my talk on Monday, but I can give a brief demo of another project. So this, can we see this? Okay, make it bigger. Okay, yeah. So I did not write this app, but this is another app written in MakePad that uses some Robius components, written by the folks from YWorks, who are working with us, Julian and Jorge, wherever they are. So this is effectively a implementation of LM Studio. I don't know if anyone has used that here, but it allows you to download models, local to your large language models, locally and run them, and you can experiment with them and do cool things like chat. So we're using the Wasm Edge backend to run locally on my machine these models within a Wasm environment. And as you can see, some of our rich text formatting has also paid off here. So I can talk to it and say, hi, tell me the coolest 5 cities in the Netherlands. And this is all running locally, so hopefully it gives me a list. Ooh, okay, there we go. Yeah. Oh, we're good. Hey, that's fast.
Is that true? Are we good to go?
Test, test, test. Okay, sounds good.
We're good to go. Never mind then.
Okay, all right, slight technical problem. I swear. Thanks. I swear that the apps developed using these frameworks are power efficient, and that was purely a coincidence. Yeah. So anyway, you can see how something like this would be nice to implement across multiple platforms. This currently only targets desktop, but we could also run it on mobile, assuming that we could run the local LLMs well. And we plan to sort of incorporate this and the Matrix app together such that you can do something like talk to the local LLM instance within your Matrix chat context and feed it all the local room data that you have, which doesn't jeopardize end-to-end encryption or your ownership of your data sovereignty. So anyway, yeah, this is a very sleek app. So this, I think, serves more as a MakePad demo for rather than anything else. But you can see it's quite feasible to develop nice, seamless application experiences, across multiple different platforms. So some other things that we've been working on are, as you may expect, some of these platforms require a little bit more effort to support than others. For example, on Android, we frequently have to build small Java class files such that we can pass, for example, a callback to a platform interface and be notified when it completes. So a good example of that is authentication. So I can give a quick demo of that. Oh, this is very small. Okay, yeah. Where are we? Okay. So this is just a very simple testing application. I don't know if it's been built, but it should be relatively fast. Okay. So while that's building, I can show the same application on Android. And this is just a sort of a testing application. Yeah, so this is an older version, but here we have a couple of just platform features that we're testing, something like authentication. So this works seamlessly across all the platforms, as I'll show in a second here. So this is just a basic authentication prompt. I'll run the wrong finger through, it's not going to work. Run the right finger through, and you can see it worked. So that's nice to have. The developer who calls this, I can show you the code. It's very, very simple. You basically just define a policy and call authenticate with a message. So if we cancel it, you can see you get the result that the user chose to cancel it. Similarly, we can test a different crate, which is called Robius Open, which provides opening files or sharing files within our app, opening URIs, things like the share sheet. So we can do something like call myself. Oh, I have this strange bug where I can't use the shift button. There we go, okay. And that should just work, albeit slowly. Okay, there we go. And similarly, you can do the same thing with a different URI. I don't think this is too wildly exciting, but just to prove that it works. There you go. My MacBook is not a top-of-the-line MacBook, so it's struggling. There we go, okay. So yeah, I can run, so in the meantime, we've built the same exact app for macOS natively, and as you would expect, it does the same thing. I am trying to steal your data, authenticate, and you get the expected platform native authentication prompt that you want. So I can use my Touch ID, and it worked, right? Or cancel it, and you get everything you expect, right? Similarly, I can call myself. I think it's going to open up FaceTime. I'm not sure what my default dialer is. Yeah, there you go. And everything works as expected. So this is really nice to use. From a code perspective, it's quite small. Oh, dear. Okay. Oh, all right. I guess it updated silently. Gotta love that. Right. So the code is quite, oh my God, apologies. The code is quite simple for doing these sort of things. So this is, again, MakePad app. In this case, we're basically just querying whether or not we pressed enter on the open field for the entering the URI, or we click the button, and then all you're doing is literally just calling a single line, right? So the platform APIs can be made very simple with these nice crates. So that's kind of our goal here. Authentication is a little bit more complicated, but still relatively simple, right? You're setting a policy, thank you. And then in this case, we're doing it in a blocking fashion because it comes from the main thread, and we want to not allow any additional activity until that happens. But we also have a non-blocking version that uses async under the hood. And you can see it's just a few lines of code to make this work. So here in this entire app and in Robux, there's not a single line of platform-specific code, which is really nice from a development perspective. And we have a series of other crates. Let me continue here. That are sort of the infrastructure to make this happen. So just like you have the CCRS crate for building native C and C++ code from a Java cargo build script, we can do the same thing for Android. So I wrote this little crate Android build that does that. And then we have another abstraction of sort of the environment that the UI toolkit owns. For example, on Android, that would be something like the Java VM, the JNI environment, and the current activity being displayed. So these are things that we need for accessing particular platform-specific APIs, and we have sort of wrapped them up in these nice little wrappers that can be composed currently through MakePad, but also in the near future with the Dioxys app or other Winit-based UIs. Okay, so that's what I demoed. Right, so just to really hammer the point home, I don't have all these platforms with me, but this is the same Robux app running on iOS, Linux, Windows, Mac OS and Android, as you saw locally. So that's nice. I also wanted to highlight that this is a relatively efficient stack because in this particular case, we're not using a web engine. So the MakePad version of Robux, the Matrix chat client that I just showed, is around 170 megabytes of memory usage, a third of which is fonts and a third of which is frame buffer. So it's our goal to begin using native fonts. But to compare that to something a little heavier, like the Element app, which runs on Electron, you can see it's roughly 3 to 4 times the memory usage. And this is also with very aggressive caching of UI elements and UI data population workloads that I have made no effort to improve yet. So how much time do I have? We go until 10:50? Okay, yeah. You say 5 minutes? Okay, great. So I do have time to go through one small challenge that kind of motivates another project within Robius, which is dealing with mixed forms of concurrency. I alluded to that before, but let's go over it in a little bit more detail here. So this here is the draw flow for displaying that view of messages that you saw. Where's my element, right? So that draw function is called every time that you're viewing a different message here, right? So this is the particular, This is the particular code flow for drawing an image that comes in as a message. And what you would typically see from, what I would assume a relatively naive app developer using this framework would do is attempt to call, again, this is on the main UI thread, a convenient matrix client function that retrieves the media for you, right, based on this URI, and then will deliver you the data as just a string of an array of bytes. The problem with this, as I'm sure many of you Rust experts can tell, is we haven't done this. This is an async function. We haven't called this within an async context, so that's not going to work. So you say, okay, that's easy. I'll just wrap it in an async context, and I'll spawn it onto an async task using something like the current Tokyo handle. Right. However, this is the UI main thread, and we don't have any async context. This thread has not been attached to a Tokyo runtime. So you're going to get a runtime error this time. So you made it past compilation, but you're not getting runtime. So I think this highlights one particular issue that is a perennial problem in UI toolkits, which is the obvious one is that you must not block the main thread, right? So if you invoke a blocking regular synchronous function from the main thread, obviously that will hang the UI, especially if it causes a system call in which the OS could put the thread to sleep if it needs to. I think less obvious is that in general, you shouldn't also call async functions on the main thread because those could also block it. So this depends greatly on what your async executor is doing, but it is possible such that a native thread could be blocked while the executor is polling whatever futures are being awaited. And what I mean by that is that the main UI thread would be, its time slice would be used by the async executor rather than the UI toolkit, which they generally expect full control over that thread. Right? You can have the same problem on background threads, but it's not really an issue because those aren't blocking the UI. So the key point here is, in our opinion, we shouldn't invoke any blocking functions, even async ones, on the main UI thread. So that causes, I think, a lot of difficulty because now you have to deal with multiple forms of concurrency. So the immediate solution that we have for this is sort of an ad hoc one specifically for this. We're fetching media here, which is inherently an asynchronous operation. It could block, and it could take a long time. So I created a sort of a media cache with a function that is aware of this possibility. It's non-blocking. It will submit a request here. Should be the code. Okay, that's a slow animation. Right, so here's the code of that, which will basically just submit an async request via another thread that runs in the background with async context, meaning it's attached to a Tokyo runtime. Right. So we're using a variety of queues and channels to make this happen. But once this happens, so this is the enum variant request that we send over. And in the background thread, we've run one of multiple async workers, which is an async task here, that will then correctly and properly be able to invoke this async block where we can actually await on this future that the Matrix SDK provides. And then once it's completed, we can update the media cache. And then the next time around, that you got that try media call. Let me see this one. The next time that you call this, that entry will have been populated, and you can very quickly get the image data and display it. So what this looks like, oh yeah, we do use this pattern for a lot of different things, sending messages to, paginating in the timeline, loading earlier messages. What this generally looks like is quite a complex web of channels, queues, and various forms of inter-thread communication across all these different categories of threads. So we have a standard synchronous to synchronous channel, like what you'd get in STD MPSC, between the main thread, which is a standard thread, and the background thread, and then we have sort of, non-heterogeneous channels, I'm not sure what to call them, in which one side is async and the other side is synchronous. It depends on who is receiving the request and who is sending the response. So this is exactly what I showed previously, and with the media cache, you're accessing this via shared memory rather than specific channels, but it's the same issue. So dealing with this, I think, is a massive headache, and this is one thing that motivates us to come up with some sort of maybe proc macro-based solution or something where a developer would be able to say, hey, I have this async function. I want you to run it for me. When I have the result, just give it back to me next time I need it on the UI. Thanks. So I don't yet have a fully formed solution for this, but this is another thing that I think falls under the domain of a project like Robius. So hopefully we'll post a cool solution to this in the future. Okay, so I'm out of time here, but I just wanted to say a few things before we wrap up. This is a new project. I've been working on this maybe for 6 or 7 months. A lot of that was contributing back to MakePad and shoring it up and aggravating Rick as much as possible. But we have a lot of challenges remaining, so we're always looking for help and contributors. We do work closely with these UI toolkits, and I hope to use this conference to communicate with more of them and work even closer in an ongoing manner. Our roadmap for the rest of the year is to continue developing more of these key platform feature crates. We have about 3 or 4 right now. I demoed 2. But there's like a series of 9 or 10 key platform features that we want to have before we can really publish an immersive app like that Robrix Matrix client. Speaking of, we do want to actually publish those to the App Store to show that this pure Rust app dev experience can result in an app that is actually usable and publishable on app stores and package managers. And then I also want to create some really nice documentation, like guided walkthroughs on how to write an app like Robrix from 0 to completion. Finally, I just want to thank all the folks who are working on various parts of this project, the MakePad team, Jonathan from Dioxys, some of my colleagues at FutureWay, the Yworks folks, and other people working on various aspects of this. Without them, it definitely would not have been possible to show off all this cool work. And with that, I'm more than happy to take any questions. Feel free to reach out here on my various socials, and check us out on Matrix as well. Thanks.
I see a question over there.
Thanks, really nice project. I was wondering, compared to Flutter, where you can also do mobile apps, you can also do browser apps with Canvas. Is something similar possible with Robius or in the works?
Yeah, so as I mentioned, web was one of the targeted platforms. I have not spent a great deal on that personally, but I know MakePad and Dioxys and other UI toolkits have. So not everything can currently target WASM. There are some hiccups, for example, in the Matrix SDK. That's why I didn't show an example of Robrix running on the web. But those can be ironed out. We do intend to support web as a full target platform. I think it lags behind desktop and mobile a little bit right now, but that also depends on the nature of what your app is doing. But yeah, it will be targeted in the future. It's a little bit incomplete now.
I see one there. Oh, wait a minute.
Oh, 1 second. Yeah.
So for the various platform feature crates, those are for things like gesture recognition and like authentication and so on?
Sure. Yeah.
Are there plans to make sure that Winit and Winit-based GUI frameworks and so on can consume these easily?
Yes, so that's the goal. They would be usable with very minimal configuration from the app dev side with a variety of UI toolkits. So as I mentioned, currently we've spent most of our time focusing on MakePad compatibility, but I also have Dioxys support in mind, which I think will also natively support Tauri since they build on the same frameworks. With Winit, I know that the Linebender folks are working on that, and I have discussions with them, but I'm not an expert in that, so I'm not exactly sure how hard or easy it will be to neatly interface with Winit. But yes, I would like to.
Excellent. This is something. So I'm from Bevy, and this is something that a lot of our users making games really want. Is they want better access to the platform abstractions, especially on mobile, where they don't want to go and constantly write gesture recognition code or set up like in-app payments or figure out how to integrate with like motion controls and so on. So this is really good to hear.
Yeah, I would love to talk about Bevy support as well. I know the least amount about that as a platform compared to the other ones.
Awesome.
But that was on one of our original, I think, slides from last year's GoSim. So I do have Bevy in mind as well. It's just there's so many things to support,
Absolutely. Yeah, I'll talk to you later.
Yeah. Thanks.
Hi, thank you. My question is about the native API. So where do you hook your FFI, let's call it a bridge? Do you hook it like on the layer of Swift and Java? Or do you hook it in the layer of C and C++? So let's take example the Bluetooth. There is the native API, which is C and C++, like low layer for driver. And there is the one that is provided by Apple and Google. Where do you hook your...
Yeah, so it's going to be dependent on the particular feature. So for authentication, we do it at the Java layer on Android, and then on iOS and macOS, it's done at the Objective-C layer. So there's no Swift UI usage from our Rust crate. But that's not to say that we wouldn't do that in the future. I think it really just depends on, for that particular feature, what is considered to be the most canonical standard way by the platform to access it. Publishing an app to a lot of these app stores and package managers, they have very specific restrictions on what you can and can't do, so we don't want to do something weird like remove all Java usage or kind of go to some hacky interface that isn't considered a public API provided and endorsed by that platform. So the answer is it depends, but generally what you would typically use if you were writing a native app on that platform via their SDK.
Nice project. A little bit of attention about your media loading example. You say blocking with futures is a problem in the UI thread, but couldn't you just consume the future itself because your media type is effectively not done of pending and some?
Yeah, sure. So I admit that was a bit of a contrived example in the sense that you can easily get around this. But I think it shows, so in this particular case, I can provide a bit of background context, which was that the previous apps that had been developed with MakePad were just using sample data or test data, and they weren't really grabbing things from like an official backend server like a real Matrix client would or a real general app would with their own SDK. So this is the first time where we integrated something like that into a framework that previously fully expected only synchronous function calls, right? So there was no async usage really. So in this case, yeah, there are many other solutions we could explore. I merely went over that example to highlight, I think, what will be a common pattern when developers first start to use one of these UI toolkits and want to integrate something a little bit more complex. But obviously it depends. If you have like a web engine one, it's highly likely that you already have a lot more access to different features underneath the platform. That's why I said MakePad is one example that presents, I think, the most challenging project structure, simply because everything's done in our own native manner, and we're not relying on underlying web engines or something like that. But yeah, there's definitely many other solutions to that. I think it just highlights a case of where a project like Robius could step in and provide a more ergonomic way to deal with something like mixed concurrency. Yeah.
Thank you.
A final question. Does anyone have one? Oh, yeah, I see a hand there in the back.
Yeah, not a question, just a comment on the async stuff, because that's also part of the MakePad architecture. The reason that we haven't done any async yet is because I feel that it's maybe an extension feature, and yeah, there's many solutions, as Kevin said. We do have an async executor that is single-threaded that we could use for that, but I found that if you use async, you start to have to wrap your data in RC ref cells, or you gotta do the borrowing runtime. So we chose to go, okay, let's stay very simple and keep the async as a sort of an add-on if you really need async flow. But it's definitely in work in progress, because I don't think this is a particularly pretty way to solve it. Yeah, if you have ideas here, I'm open to suggestions as well. So.
Okay, so give a big hand of applause to Kevin.
Thank you. Appreciate it.
So we'll be shortly going into a break. So to remind everyone, there will be a raffle and signing of the books by Mara.
Appreciate it.
Jets, could you bring the book and hold it up? So you can have this book, if you brought it, signed, and you can enter the raffle to get it, which we'll do later. And Luca will also be there and give away a few books directly and also sign them. Check out also our sponsor stands, which are in Chemie en Chaos, or Chemistry and Chaos building over there. And we will have 30 minutes, around, yeah, perfectly 30 minutes. And we'll see you back here at 11:20. Until then.
So I think the lighting went down with the lag. Yeah, I think so. So we saw the first growth and then boom. I'm wondering what the line is. Just like the break breaker. Maybe a bit too much. Yeah. Maybe if you less tiny bit, but probably not. That's not significant. These lights just way more power. Yeah, but if it's like if it's actually holding on, maybe. It's unlikely, but then maybe. Yeah, I just fix my light makeup and that's restarting everything.
Okay, I will be video. I don't have your audio yet. So I haven't created like a creating maybe the voiceover. So I guess basically go into system.
There's one that may need to actual keyboard after like 3D or like 2D slides. There's only one 2D slide. I thought it might be a good idea to clarify what the word personalization means. Because it has some association.
Okay, what was it? That's pretty good. No, because we're going to show it from there. Otherwise, we won't recognize it.
Yeah.
Right? So we could go
Right.
We'll have to make some.
You got your Chromium installed?
Ish.
Are you only fine?
Just come here?
Yes,
Just call my phone. I'm going to call my
like my color temperature is good. You're able to check that? Yeah. Yeah. No, it's not that it wasn't successful. It's that he was extremely ambitious. That he
Technologie.
gelijk die mag weg. Ja.
De andere is al betreden.
Oh, is this for the book? You want a book?
A book? No, I mean I would like ask you what to do for this talk.
Oh.
I would take one, that's not
It depends on when you're on, but in general, you should be here.
Be on time.
Yeah, so it's roughly like when the Q&A starts, I guess. You can walk over to
That's cool.
them over there.
Okay.
And Terrence will be here as well. So okay. Oh, there's already.
Are you giving the talks?
Yeah.
That's cool. Hopefully.
Ja, laat staan. luck already. You too. No, this is adequate amount of money. So I listened to one of those like speaking coaches ones, and they said like I can hear it if someone didn't wake them up to 3 days in advance. Well, but like if someone didn't take good care of their voice in that duration, they could hear it basically. I don't know, but I think it helps. And this is like I would rather have too much than this. In fact, I'll just take this. Like when you actually start, like and everything starts constricting, and you still want to just like sat. It really looked like a terminal, right? So yeah, that's right.
Okay, it's time. It's time. Please come inside the room and take a seat because we must continue. I'll wait 1 minute.
Yes. Also, for the people in the back, there's many more seats over there and over there. I mean, you can stand if you want to, but there are enough seats.
And keeping track of the time.
Okay. A minute sharp. He's looking at his watch. How many seconds do we have left?
8 seconds.
7.
No.
No, we'll leave the countdown out.
Okay, I think we can start. So welcome back. I hope you had a nice break. I need to correct some communication that we just did. So
yeah,
I
wait,
just
yeah. So I'll do that because there was more development.
Oh, more development. Do that.
So,
yeah, sure.
There might have been some miscommunication,
Yes.
but the raffle has been here, and if you've got a number, you're signed up, and we'll announce the results later. That's just it now.
Yeah, but you can join the raffle, right? Still.
No, we closed it.
You closed the raffle. Nah, that's not fair.
Okay. We can give people another chance next break
Yeah, next
here
break.
at the stage.
Yeah, next break
Does that
here at
sound
the
fair?
stage. There will be
That sounds
another
fair.
chance to enter the raffle. I apologize for the miscommunication. And the books will be handed out over the raffle will be drawn, I guess. The numbers will be randomly drawn before the last break. And then the book signature of Mara will be in that break. So at the end of the day, all that will happen.
It was a lot to keep track of. We're sorry. Okay, before we move on, I quickly want to give a shout out to our live stream partner, Hyperswitch, who make it possible that we can have a live stream and that people from all over the world can watch this conference even if they're not here. And also this live stream is actually organized by the awesome people from Lijm en Cultuur who are doing some great work, editing it live and doing a lot of great stuff there. So big thanks to them. Now let's go on to the next talk.
Yeah, so the next talk will be given by Volkert. You may have read one of his blog posts. He works at Tweede Golf, so if you want to read his blog posts, go to the Tweede Golf website and you can read a lot of interesting blog posts. So he has worked on NTDB-RS, so that's a re-implementation of the time server infrastructure in Rust as part of the Secure Internet Initiative. He also works on another language named Rock, and he's really passionate about that. Give a big hand of applause to Volkert.
Yeah, thanks. So, welcome to Compression Carcinized, implementing Zlib-rs. So, about that name, it alliterates, which is why I picked it. But this word, carcinization, comes from biology, and it means to evolve a crab-like body plan, which is a phrase I really quite enjoy. And we'll see what we can do with this idea a little bit later, but this happened several times over the course of evolution because it turns out that being a crab is an incredibly successful survival strategy. So, what is Zlib-rs? Well, as the name sort of implies, it is a Rust implementation of a thing called Zlib. And Zlib is a library for compression, in particular for dealing with the gzip compression format. And it is a very widely used format, and therefore Zlib is used in a lot of places. So for instance, if you download a binary on the internet, like Rust Analyzer, it is very likely that these are provided as gzip files, both because the compression is pretty good, and because most users already have some kind of program on their device to decode such files, right? So there are definitely better compression methods out there today, but a lot of software is just compatible with gzip. Even if you haven't downloaded Rust Analyzer today, you've likely loaded a web page, like rustlang.org. And it's very likely that those web pages also use the gzip encoding, and therefore indirectly use Zlib to encode that page. So when you load a page, you don't get raw HTML bytes, but instead you get sort of a compressed representation, and it gets decompressed on your local device. So Zlib is used in a lot of places, and it's really at the foundation of a lot of our tech stacks, in particular of a lot of internet infrastructure. And so it's a very important project. To get a bit of a sort of a better idea of what Zlib is that in practice it is often a dynamic library that is somewhere on your system at least once. So here I've tracked it down on my own machine. And we can see that it exposes a bunch of functions that have something to do with compression or uncompression in their terminology. And so applications on your system can load this library in and then make use of this compression and decompression functionality. In practice, this is a C dynamic library, which means that it exposes functions like this, which looks very nasty from a Rust perspective. It has like pointers, mutable pointers. It returns errors, but really it's an int because, of course, right, C types. It can do better than that. We can. Sort of that as sort of a summary of that. So the idea of the Zlib-rs project is actually to sort of aim high and replace that C dynamic library, to build something in Rust that pretends to be that C dynamic library, but secretly it's all, nice Rust inside. So that also means that our sort of target audience is people that don't necessarily have sort of warm, fuzzy feelings towards Rust. And so we need to somehow tempt them to upgrade, right? To sort of make that very easy, and we can do that not by sort of re-implementing all of the logic in Rust and then saying like, hey, we made this really cool Rust library, but by actually sort of bringing it to them so that upgrading to Zlib-rs would be just swapping out a file. But of course, like if we go through all the trouble of implementing that logic in Rust, we may as well also provide it on crates.io and sort of make it available to the Rust ecosystem. That still has advantages. If you're using Rust anyway, then sort of importing it directly into your Rust compilation is better in various ways than relying on it as a dynamic library using that very nasty C API. So today we're going to go over sort of a crash course in compression, sort of how does Zlib work, what does it do, and sort of why is it effective. Then having a look at the Zlib ecosystem, because when you are going to like rewrite it in Rust, it's important to know what you're actually rewriting so that you can sort of look at design decisions and make choices. Maybe you want to adopt certain decisions, maybe you want to innovate in certain ways. And so it's a good way to have a bit of an overview of what that ecosystem looks like, what properties you want to preserve. And finally, some ponderings on porting, on sort of this project of like rewriting the bottom of the stack in safe Rust, which to me is really like delivering on the original promise of Rust, sort of bringing that improved language and toolchain to all of those places. Let's see what we can learn and what we can maybe do better. So the sort of core idea of compression is, why use many bytes when few do trick? Right? Storage space and bandwidth are expensive, and so we would rather send fewer bytes than many bytes. Also, especially in the context of the internet, sending fewer bytes over a wire is faster than sending many bytes over that wire. Now, this is slightly more complicated because compression and decompression are not free, and so you need to somehow make sure that the compression, then sending fewer bytes than decompression, is faster than sending the uncompressed stream. But in practice, gzip is sort of used everywhere on the internet, so clearly that must work. But that is something to keep in mind. Performance actually really matters here. So the kind of compression that we're looking at is so-called lossless compression. Compression where if you have some data, you compress it, you decompress it, then you want the original sort of input back out. This is sort of opposed to lossy compression, where they can get away with just chucking out detail, like in JPEG images or MP3s. We don't get to do that. We need to actually be able to replicate the original input, and so we can't just conveniently forget information. So the algorithm that is implemented here in Zlib is one that looks at your input, which is in general a byte stream, but because we're humans, we're going to use characters today. And it's going to look for repeating sequences of characters in this input. So here we have the string foo bar foo, FOO repeats, and so what this algorithm does is it replaces this sequence with an offset length pair. And so what happens here really is that this offset length pair refers to an earlier part of the input stream. And this is more worth it, this saves more bytes, when that repetition is longer. So if we had 4 characters instead of 3, we would gain basically by having fewer bytes to transmit at the end. This is also a representation that is fast to decode again, right? So this is relatively straightforward to like almost interpret. It really looks like an interpreter loop when we start decoding this information. The tricky bit is finding how to insert these offset length pairs, right? If you look at this sort of seemingly arbitrary sequence of characters and ask you like, okay, what offset length pairs do I insert? What are the repetitions that you see? That is hard. And that is hard for humans, but also for computers. Like if we throw a bunch of nested for loops at this, performance would just be absolutely terrible, right? The big O of that would be bad. And so we need to be smarter than that. We need a couple of tricks to sort of break down this problem and make it manageable. Because again, like we need this to work on web pages on the internet. Like sort of throughput and time to first render are really important. Yeah, and an additional problem is you want to not just find repetitions, like finding one character repetitions is easy, but they need to be as long as possible because that gives you the best compression. So in practice, how Zlib works is it runs over your input, and so we have a sort of current position, a current character, and we're going to search backwards for repetitions that match with the current cursor position and the sort of characters following it. Right, so we run over our data. character by character. But then we need to sort of impose some restrictions on this to make it manageable, to get that big O complexity down. And basically, this revolves around reducing the amount of work that we do per character. And so the first limitation that we're going to impose is that we're going to only look within a certain amount of space backwards. If it's sort of off to this side, it doesn't count anymore. We can't use it anymore. And so this makes our search space smaller, but also it reduces the likelihood that we'll find a good match within this smaller window. And if we make it larger, then the chances are better, but we spend more time searching through. And because there's no sort of objectively good answer to how big that window should be, it is a user configurable parameter. Similarly, the compression level is another user tunable parameter, and this is roughly a measure for how hard we're going to try to find the longest, the sort of optimal match in our window. So here, if we search our window from left to right, we find a 3-character match, and we have to sort of decide, are we going to continue to search to find a 4, 5, potentially, 100-character match, or are we going to just stop here, not waste any more time, and move on to the next character of the input? And so again, there's no real, that's a gamble. You just don't really know. But at a low compression level, you basically say stop when you find something halfway decent. At a high compression level, you would continue to search, sort of hoping for sort of getting lucky. That still wouldn't really work, though. If you go about it in this way and you search through this whole window linearly for every character, this window is typically 32K or 64K. That will be way too much work that you do per character of the input. And so actually what we need to be doing is remembering some of that work. And so what we're going to do, what the Zlib algorithm does, is it keeps track of substrings of the input, 3-character substrings, and the indices at which it has found these substrings. And so in this case, we find the string FOO at index 0. We find OOB at index 1, and so on, until we find our second F. Because in this case, we're again we want to insert the string FOO, but it's already there. And so now we know sort of two things, which is that at index 0, which is in the sort of value set of foo, we find a match of at least 3, which is already pretty good. That's sort of about break even in terms of do we gain anything with that insertion of an offset length pair. But potentially the match is longer, right? That is sort of what we're hoping for. But also any index that isn't in that set, we know for sure that there won't be a match there. Like OOB will definitely not match FOO, and we don't need to actually go look at the data and compare that character for character, but we know because of this dictionary that we've kept that we don't even need to go look there. And so in this way, we can sort of skip over vast amounts of the input and just never treat them at all. So I hope that sort of sketches sort of roughly how the algorithm works and gives some intuition for why this is so incredibly effective on web data. Because if you think about HTML or CSS, there's just so much repetition in there, the repeating class names, property names, just words in text, that even at low levels of compression, you sort of achieve very good results. And at low levels of compression, you expend little time, but you still get actually quite a sizable reduction in the overall payload. There's one further trick that Zlib uses, which is that it is a streaming implementation of these algorithms. So that means that if you load rustlang.org, you don't just wait for that whole compressed HTML page to arrive and then decompress it, but instead your sort of device can start decompression as soon as the first byte comes in. And so this really helps with overall sort of that time to first render. Unfortunately for me, it also really complicates the implementation. Because like now you need to be dealing with you get 1 byte of input, you get 300 megabytes of input, you get 3 bytes again. And so you sort of need to keep track of this, and we make heavy use of fuzzing to make sure that the implementation is robust for sort of this fragmented input. All right, so that's sort of roughly what the algorithm does, and I hope that is useful. So what are we actually implementing, though? Well, so generally, when we talk about Zlib, the Zlib that is actually everywhere, because it is a default in a lot of operating system distributions. This thing is called Zlib Adler, the OG, and its goal is stability. This is a dependency from 1995. If you look at its source code, you can really see that. It still supports 16-bit systems. Who here has programmed on a 16-bit system? Exactly. And also, it doesn't use modern hardware very well, right? So it's sort of one generic implementation that runs everywhere. It is good C code in terms of performance. Aesthetically, I have thoughts, but you know. And so it doesn't use a lot of sort of modern hardware instructions in specific ways. And this is unfortunate because that is where most of the innovation in the hardware space has been for at least the past decade. We can't run more instructions per second anymore, and so what we're doing is sort of inventing more powerful instructions that do more effective work in a single instruction. And to some extent, compilers can sort of transform our sort of standard programs into programs that use these instructions, but generally they just aren't capable enough. And you need humans, for the time being, to actually write those implementations. So because performance is important to many organizations, several forks have been made of Zlib Adler. The most prominent of these is Zlib-NG, where basically they say, we want performance. We want performance specifically on modern hardware. So that means removing a lot of legacy stuff, amongst other things, the 16-bit support, and relying on these modern instruction sets that have these SIMD instructions that do that sort of more work per instruction. But Zlib-NG is still fully API compatible, so that means it exposes all of the same names with all of the same type signatures as the original Zlib, and so it is a drop-in replacement for the original Zlib, just with less platforms that it supports, but still the same API. Now, these are both C dependencies. And C has various problems. Rust has various solutions. So all of the usual sort of points apply. We have bounce checking. We have borrow checking. Rust is nice to write. I think for sort of a project at this level of the stack, it is especially important that we vastly reduce the surface area of our project. So in part, this is reducing the amount of code that we write through good use of the standard library. We have one dependency, which is libc, which I would like to get rid of. We'll get there. In part, though, it is actually using cargo, because it is, I'm going to posit something here. It's my opinion that any sufficiently complicated C project contains an ad hoc and formally specified bug-ridden slow implementation of half of cargo. This implementation right. You should, like, just sort of like looking at, you know, an accident, you should look at the build system of some C projects, because in practice, this implementation of cargo is a makefile and 1,000 lines of bash. No one wants to write that, no one wants to read that. Detecting errors in that kind of code is incredibly tricky. And this is not hypothetical, this is sort of part, at least, of the recent XZ attack on another compression format, where a malicious maintainer added a single character to one of these bash scripts, and it made the script take a different branch, and then you are now, you know, compromised. Update your threat model, don't use thousands of lines of bash. So if we want to do better than that, in Rust, the way to sort of use or interact with gzip files, the recommended way, is Flate2. And this is a crate that provides a nicer API for Zlib and similar functionality. So instead of that nasty pointer-based thing, we actually get impl read, impl write, we return results, etc. It's very nice. It's also used in cargo, because again, gzip is everywhere. But Flate2 itself is actually just a shell. It doesn't implement any of the actual compression logic. For that, it uses one of several backend crates, which you can sort of toggle with a feature flag. So you can use Zlib-OG if you really want the compatibility, or you want to just use the thing that's already on your system. You can use Zlib-NG if that is what you want. But also, you can use Rust implementations. And until recently, the only Rust implementation available was mini-z oxide. And this is a safe implementation of a subset of the Zlib API. So it really covers a lot of use cases for Rust users, but it leaves some things to be desired. So it doesn't cover the full Zlib API. It's not a drop-in replacement. And also, it is relatively slow because it doesn't make sort of dedicated use of these SIMD instructions. And Zlib-rs fixes this, right? We still want safety in the sense that we implement this in Rust, we try to be really careful, but also we really want performance. In order for this implementation to be competitive, we need the performance to be at least okay, and hopefully over time, better than the alternatives. We also, implement the full API. So in practice, this sort of architecture that we get is this unsafe sandwich, which doesn't get food poisoning, but there's some stuff in there that we'd rather like, So at the very top, we need an unsafe API for exposing with the outside world. That is that nasty pointer-based API that we need to provide. That's sort of the point. At the very bottom, we have SIMD and even some inline assembly to achieve the performance that we want. And these are sort of like, we can't get around the unsafety here, probably ever. And then in the middle, we have mostly safe business logic. There's some unsafe in there dealing with uninitialized memory, but those are actually, the code comes from the standard library, it's just not stable. And so over time, we can hopefully get rid of that. So then, like in terms of performance, this is sort of what the landscape looks like. This is speed up versus Zlib-OG, sort of as a factor of its speed. First of all, Zlib-OG performs not well. Then mini-Z oxide really tries, and at low compression levels, it's doing all right. But at higher compression levels, you can really see the difference between implementations that use and those that don't use the explicit SIMD. And in general, that's like almost a 2x difference there at level 6, which is the default. Right? And like higher compression levels basically do more computation, so the effect of using SIMD becomes more pronounced. Also, like, we're doing all right with Zlib-rs, but it's still not quite there with Zlib-ng. That just means I get to stare at assembly for many more hours. So you can actually use this today if you're already using Flake 2. We've been a little bit quiet about it, but the implementation totally works, so you can flip this feature flag. Please give that a go if you're already using Flake 2, and let us know how it went, both if it went well and if it went poorly. All right. So finally, I wanted to say some stuff about sort of this project of translating C into Rust, because rewriting in Rust is easy to say, and the people who say it most rarely do the actual work. Typical. So something I've been thinking about is this sort of spectrum of porting, this sort of idea of we can have an organic implementation or a line-by-line rewrite of an existing C project. And there's various places on this spectrum with various trade-offs that we can make. So if we have a sort of fresh implementation, like Russell's or NTPDRS, then they, in a sense, reinvent the wheel. They sort of throw out a lot of existing knowledge and code and start from scratch and have to sort of absorb and digest all of the information relevant to the domain. On the other hand, they can also innovate in terms of mostly architecture, I think is the most useful one, by sort of being unconstrained by existing implementations. Refactoring architecture is really hard in practice. So in a sense, this is high risk, high reward. It takes a long time for you to digest all of that information and build an implementation that works, then making sure the performance is sort of OK, because that matters at this level of the stack. But ultimately, you get a sort of very nice payoff in sort of the best Rust solution that you could probably come up with. On the other end of the spectrum, we have line-by-line rewrites. And in the most extreme case, we could even do a mechanical rewrite using a tool like C2Rust. And the Revit project is an example of such a project. So this translates David, which is an AV1 video format decoder, into Revit. And so what happens here is that you reuse a lot of that existing knowledge, right? As you can imagine, video decoding, not an easy topic. So you reuse a lot of knowledge about how that domain works and also the sort of performance engineering that went into making that implementation efficient. You also inherit the architecture. It really depends on what C code base you start with, whether that is a problem or not. But ultimately, what you get is something that works on day one. It compiles with a Rust compiler on day one. It has the same behavior and performance as the C implementation. You can test and fuzz it to sort of make sure that you never break sort of those correctness properties. Most of your work, though, is cleaning up code that looks like this. This isn't even the worst of it, but there's a lot of this code. It's very sort of verbose, but its input was C, so what did you expect? And so while this is sort of annoying, I also think that everyone here can see some improvements that they'd make to this code. And so in practice, cleaning this up is mostly a sort of a pretty zen process of moving characters around, turning while loops into for loops, etc. It's only occasionally that you step on a borrow checker landmine. And you have to sort of take a step back and reconsider, like, OK, is the architecture, does it actually work? Do we need to rethink something? Are we going to use some unsafe code here? Choices. So in practice, this is something that Revit has to battle quite a bit because the original library uses threading, and so you can imagine how that would be not a great time. Zlib is somewhere over here, sort of off to the right, where I did most of the translation by hand from the C of Zlib-ng. This is actually a pretty straightforward process. It just takes some editor skills. And we reuse a lot of that existing knowledge, both in terms of correctness and performance. We get very quick results, like in a week or two, you can actually have something that is very solid. And our architecture was constrained anyway, so we didn't think we could really innovate there. We have that C API we need to expose. We need to sort of implement that streaming that really constrains what you can actually do. So, rewrite it in Rust and you. If you've seen the sort of marketing recently and also the Russell talk yesterday, I think what we're sort of realizing is that actually we need to be compatible with existing implementations. So instead of like sitting on our high horse and saying like our Rust implementation is better than yours, we actually need to sort of bring it to the places where this software is actually used in order to achieve any real world impact, which ultimately like that is what I care about. I want my work to sort of be the foundation for modern digital infrastructure. And so we're working on all of these compatibility layers and making integration with existing systems easier. That is why Zlib is a drop-in replacement. Also, we have to be just better, because for someone to mess with their existing configuration on some obscure server that they haven't touched in 10 years, it takes a lot for them to upgrade to our version of X, right? That is just not an easy process, not really something you want to deal with, and it's never urgent until it is. So we actually try to just add more functionality and better error messages. NTPD is a better algorithm. Russell's is actually a better and faster implementation of TLS, and we have to be better in order to get any uptake in the sort of broader community. And then sort of, I don't know, more complicated things. Funding is always a problem for this kind of work. It is, again, very important, but never urgent. It's not very flashy is another problem of these projects. Right? Like what TLS implementation you use is never relevant for your customers until it is. And so it's never urgent to upgrade. But the funding has actually vastly improved versus a couple of years ago. Memory safety is a much more active topic in conversation. A lot of engineers are really sort of on board with this. And it just takes people to get over that hump of sort of actually doing the upgrade process. Looking up the config file, translating it over to the new thing, and actually using this stuff in production. So if you are in a position to sort of smuggle in some unglamorous Rust into the bottom of your stack, please do. And please let us know, because it really makes our day, and it really makes this sort of project of using Rust at the very foundation of our systems that much more possible. All right, so in summary, why use many bytes when few do trick? Compression is very neat and very useful and used everywhere. In particular, on the web, it is unreasonably effective due to the type of content that we send. If you are already using Zlib-rs, or if you are already using Flight 2, please try out Zlib-rs. Let us know how it went, right? Please use more unglamorous Rust in production. It doesn't need to be worthy of a blog post, like just actually use Russells instead of OpenSSL. And finally, keep evolving crap-like body plans. Thanks.
All right. Are there any questions?
I have heard, by the way, from some people that we would like the question askers to stand up so that the camera person can find them.
Hi, which levels of SIMD do you support? Do you only do AVX, AVX2, 512 even?
So in the current sort of, like we're not entirely done with this, so generally we want to support everything that x86 has, so that would be like SSE, the various versions of SSE, and then AVX and AVX 512. And also in ARM, we support Neon currently. And then, I don't know, there's some ideas about do we want to do RISC-V or do we want to do other things. This is sort of needs-based and also based on what hardware I have. So like I don't have AVX 512 in my CPU, and then actually implementing that is tricky. So we'll get there and sort of roll out support. But this is really the easy part, at least if we can sort of adopt that code from Zlib-ng. Also, PR's welcome, I guess. You know, if you really like looking at SIMD code, it's kind of rough.
Hello. So I had a question about error handling. So you mentioned that the C API has just uses instance stuff, but you also support that API.
Yeah.
So internally, are you able to use nicer Rust errors and then expose those back as the C API, or how are you managing that?
Well, sort of part of what the C API means is that error handling isn't that present in the code that we translated, right? So it also just internally returns an integer and potentially sets a character pointer to a static string indicating roughly what went wrong. So certainly what we aim to do is add more error messages, because there are many cases where the computer just sort of says no, you get a sec fault, and it's not clear why, and you just configured something wrong, and the system should be able to handle that. So we can definitely improve there, even for C API users. And then what we didn't really talk about, but like our Rust API is not ready. I think even then the goal would be to use Flake2 as the actual interface to the implementation. But right now what we use is basically the C API for interacting between Flake2 and well, it's called libc-rs sys, because it exposes a C API, even though all the implementations are actually in Rust.
Anything else? I see some here.
Hello. Back to the topic of SIMD instructions. How do you do dispatch for different instruction types for different x86 processors, for example?
You mean the different, like, yeah, okay. So there is a macro in the RustStandard library, which will, it's something like, is x86 feature detected? And you can query that at runtime. It will resolve to something, if at compile time you know you're going to definitely have a certain instruction set available. It will hardcode that. It will just be like true. Otherwise, it will query at runtime and then cache what instructions your CPU actually supports. This is very important, mostly for safety of that bottom sort of thing, right? Like SIMD operations in general do like 8 additions in one go, so that is not unsafe. The unsafety is computers really hate it when you make them execute instructions they don't know. And so these instructions are not always available, and we need to actively check, and this is part of the unsafe contract. So there is support in the RustStandard library for that, and we plan to use feature flags for if we want to like compile with no standard. So you have to explicitly toggle on, like even though I am on some embedded device, I still want AVX2 optimizations.
Okay, more questions? Oh, yeah. The microphone's going all the way across.
So how many bugs did you find in the original implementation just by porting to Rust?
So this is funny, right? So zlib-ng is used incredibly widely, and what if, like, the way I think about it, it gets fussed in production billions of times a day. And so in practice, finding correctness bugs with the sort of general settings, generally accepted settings, I don't think you're actually really going to find much, because any input that could have been thrown at that algorithm over the past 30 years, sort of like they would have found the edge cases. It's much more around usability, that if you configure something slightly wrong, it will just like sec fault your program, which is acceptable in C, I guess. Like, don't do that, but like we can do better. So it's mostly around usability, not so much correctness of the algorithm. That's been hammered out long ago.
Okay, great. I see another question over there.
Yes, so that answer kind of makes me think of another thing, which is like if you're building foundational libraries in Rust, you know, how do you think of the strategy to encourage the adoption of those libraries more widely than just in, say, Rust projects, right? So that they get more widely used, more widely tested, you know, become part of the larger, say, you know, open source ecosystem used by many languages and operating systems.
All right, so this is sort of a like one step at a time process where one by one we talk directly to an engineer at organization X, and they smuggle in some of that Rust code to the bottom of the stack. We try to make it really easy, right, by making this a drop-in replacement. Russell's is now working on OpenSSL compatible APIs. And then otherwise, it's also a matter of like if you look up the documentation of Zlib, it shows that it's from 1995, right? We can do better than that. We can have like a proper tutorial sort of explaining the general concepts and have proper API docs. So it's mostly about helping actual developers sort of make that process very easy, because it is scary. It is sort of a risk that you take in the short term, hopefully preventing major catastrophe in the long term.
There was another question over there, I think. On the standing row there. There we go.
Hi, thank you for your talk. So I think you mentioned somewhere, and correct me if I'm wrong, using fuzzing to check if the implementation was robust. Do you remember correctly?
Yeah.
So which crates and tools did you use for fuzzing?
This is just a standard cargo fuzz, which is unfortunately still nightly, so you have to rebuild the whole thing. But like just cargo fuzz, and then we have to be a little bit, and I think we can still be smarter about this, like what input you actually feed it, because you can give it a random sequence of bytes and it works well and that needs to work, but it's usually not that interesting. And also especially for decompression, we also try to give it invalid input to just sort of make sure that it doesn't do anything weird, like run into a loop or a panic or something like that. And like, yeah, you just let that run for a couple hours, and then if it comes back good, then, you know, you have increased confidence.
Yeah, makes sense. Thank you.
I mean, there's lots of testing in general of the library too, based on tests from the C code, but also because we did sort of write it piecemeal, we have tests in the individual modules testing smaller bits of logic, because the only test that the original C project has is end-to-end tests. And that is fine if the end-to-end thing works, but if you have a bug somewhere in the middle, then it's really hard to track down why that is exactly. I would argue our implementation is better tested.
All right. One final question over here.
Do you also focus on the C development experience so that C developers can directly use your project instead of using Zlib-rs, so autoconf generation stuff, and yeah, like Zlib provides on most platforms?
So this would be in a scenario where you would want to like statically compile this in? Right, okay, so that's not really something we've considered. I'm not familiar enough with the sort of like how people use Zlib in a static context for whether that makes sense to us. If you're using C anyway, maybe you want to just continue using C. But we can definitely invest some time in also making that experience easier. So I do think it really helps that we have sort of RustDoc where we also sort of need to annotate all of these sort of unsafety assumptions that we make. We occasionally need to make slightly stronger assumptions about like these two pointers should not alias, because otherwise things will sort of go sideways. And so also just that documentation in general will be helpful, I think. And also we can just make a better introduction to the Zlib API than that webpage from, you know, perhaps before my birth. Yeah. I mean, we're happy to help out also for those use cases.
All right, thank you so much. Please give a big hand to Volker.
Thank you. Yeah.
All right, I'd like to introduce the next speaker. The next speaker is Jonas Kukenberg. He's DevRel at Crab Nebula, and he's also a member of the Tori team. But today he's going to talk to us about K23, a secure research OS running Wasm. Please come set up.
Hello. Hey. Yes, it's me. And while we set up, I've got a question for you. Who here has worked with WebAssembly? Maybe raise hand. Wow, not bad. Awesome. Who has built a WebAssembly runtime? No? Yes? We should talk. So let me open that. All right. Does that work? That looks good. Cool. Awesome. So, yes, the name K23, and that is the name because it's a kernel I started last year. Very easy. I'm not, well, right now I'm actually doing R&D. I also work with Tori, as said. I'm not here for that at all. I'm just me, Jonas. And I've been working on a operating system, right? And whenever I talk to people about it, the first question, or the first thing they say is like, wow, cool. The second question is why, right? And so I always answer that with, you know, something like that. when, because like when the operating systems that we all use day to day, they were born in a time when computers looked like that, phones looked like that, and the Berlin Wall just fell, right? Most notably, no internet inside. And there's a quote by Graydon. He talked about Rust in that context, but I feel like it applies to operating systems as well. And I like it a lot. And it's, the internet is highly concurrent and highly security conscious. So the design trade-offs that always favor C and C++ have been shifting, right? And I feel like that is just like a very elegant way to put it, because the operating systems we use day to day, they aren't bad, right? They are good pieces of software, but just designed from a very different time. And I feel like there's space to explore new ideas, and it's also just very fun to do it. I like it. So, what's the thing? Like, what's the project? Let me paint you a picture, right? I, as sort of an end user, I don't want to deal with malware. I don't want to, worry about architectures. Is it like Intel? Is it ARM? Is it like, oh shit, downloaded the wrong thing? Like, right? I also personally really hate dynamic linking, like in its current incarnation, right? Always have issues with it. Don't really like it. And then, please don't be offended if you use Linux. I also don't really like Linux dependency management. It's a mess. Especially with Tari, we have all sorts of issues. We even now started, our own apt repository because it was such a mess. So the idea that I landed on for the prototype is a microkernel, right? It's a small kernel, drivers, libraries, applications, everything runs in user space, which gives better isolation, better stability, but traditionally has also higher overhead, and that's where WebAssembly comes in. Sort of to visualize that a bit, we have the kernel, right? Kernel space, very small. Most of that lives then in user space, right? The drivers live in user space. We have sort of our system interface, and then user space programs, and everything sort of depends on one another. Which brings me to like another feature that I really care about, which is built-in package management, right? Dependency management. Why does it need to be bolted on afterwards? Just make it first-class citizen, have the operating system know about it. In WebAssembly, that looks a bit like that, right? You import a package, or a component in that case, and components, import other components. They do it by a registry, a name, a version, and then more importantly, also a content integrity hash, right? And that means, it's reproducible. I can check it. It's even content addressable if you care about that. And the more, important part that I care about, it's like it's built in, right? It's like first-class citizen. Back to the diagram, right? The arrows imports, right? Like the WASI-FS, right? That imports the disk drivers, and then user space programs import the WASI-FS interface and can do disk operations with it. Right. So to recap, microkernel running WebAssembly means sandbox drivers, daemons, applications, anything, and it has built-in reproducible dependency management. That is the idea. So what are the results so far? That's cool, on paper, maybe. I don't know if you like the idea. I do. I like it. Right now, sort of as it stands, I only have RISC-V support because I looked at x86 and was like, okay, later, don't want to deal with that right now. Also looked at ARM, didn't understand it. Both of that, we'll get to. RISC-V, treated me well to begin with. It is about 60K lines of code. And that is quite a lot more than what you would expect for a microkernel, but it also has a full WebAssembly compiler built in. Split it into two parts, right? The bootloader, that the sort of signature checking and all the setup, and then the kernel, which is essentially just a WebAssembly runtime running on bare metal. And that, cool thing about Rust, it's using CraneLift, which is sort of the optimizing compiler that's written for WASM-time, the WebAssembly runtime. I had to fork it to add no STD support to make it run on bare metal, which, cool thing, will contribute back upstream. So if you want to run, WASM-time on bare metal yourself, that will be a thing soon. And that's actually like one thing I sort of want to emphasize. We heard a lot about like, you know, how great Rust, like memory safety and stuff, but what I really appreciated is dependency, like sort of package management, cargo, right? Being able to just like cargo add compiler, right? I can just pull in crates, 3 of them, and just have a like running compiler in my kernel. Like how cool is that, right? And of course, you know, be careful about dependencies and like gets out of hand if you're not careful. But to me, like that is a superpower, right? Like that is very cool. Yes, you know, memory safety is great, but we heard about all that. The other thing I like, you know, noticed about Rust and writing in Rust is that if you're writing an operating system and, you know, your machine does that all the time, you know, store page fault, load page fault, and like everything just disappears. Being able to just claw back all the static guarantees you can get about your program, like as much as possible, that is very powerful. And I wouldn't have, you know, don't want to write it in C, certainly, because like all the sort of nice static guarantees you get from Rust. Another result, right, something I noticed is that being the kernel that sort of you target, and also the compiler that targets the kernel, unlocks so many cool possibilities. For example, you know, as you heard in the previous talk, oftentimes, you know, you want to target newer hardware features than what otherwise might be available. And that usually means either dropping support for older hardware, or sort of, you know, selectively doing like code path or something like that, or, you know, just being very defensive about what sort of targets, what sort of instructions you can target, right? Because instructions that my CPU doesn't know about bad times. You know, trust me, I know, my JIT compiler does that a lot. But the cool thing is, because I'm the compiler, you know, much like, you know, Gentoo, for example, I know exactly what features each CPU core has, right? And even if it's like a super complicated like SoC that has like one ARM chip and one RISC-V chip or multiple RISC-V chips, like I can target those and just like compile specific code for each of those CPUs, which is very nice. It also unlocks one thing that I, you know, talked about previously, where traditionally microkernels are super sort of overhead heavy, right? Because you need to do a lot of context switching, and that traditionally means like storing all the registers and all the like thread state. And then you have to be really pessimistic about it, because as the kernel, you don't know which registers might have been sort of overwritten and which are still sort of like previously, right? Except for we are the compiler, right? We know which registers are used and which aren't, right? And we can then build special sort of trampoline functions to jump to other processes that just save exactly the state that we need to and not more than that. Which means that sort of, you know, now suddenly the overhead of jumping between different processes, right, becomes like almost the cost of just a regular function call, right? I just push my registers onto the stack and jump to a different process, like no big deal. And I can do that because, you know, I am the compiler and I know exactly sort of what every process needs because I just compiled them, right? That said, I don't know how we're looking on time. Oh, that's all right. Let's do a demo, shall we? All right, so I've got a very complicated program. Let's make that, can I not? How do I like Rust Rover, I just don't, there we go. What's the, oh no, I won't type that. Anyway, I hope you can halfway decent see that. It's a Fibonacci program, right? It calculates Fibonacci numbers. And if we now go ahead and compile that, it compiles very fast, I know. We have, you know, our WebAssembly sort of compiled. And then if we jump over to sort of our test function now in the kernel itself, right? What we do is sort of we do all the setup, we include sort of the WebAssembly bytes, and then, you know, we parse it, we link it, we instantiate it, we get the, you know, the Fibonacci function, and then we call it, right, down here. And so, maybe I should, because that's the fun part, open that and sorry for the white. All right. here, I can just make that very large. Right. And when we run our kernel, we'll sort of compile that, run the bootloader, set everything up, and then compile everything, and it has a lot of debug output. Jump to WASM, and we get a result. I'm very happy to report that is one of two programs I can run, right? Very exciting stuff. The other one is the same program, but written in C. So, good times. Get that back up. All right. I just said, I have 2 programs I can run, which isn't a lot. I know. So, what's next? Because I feel like this is a good idea. It's fun, and it's also something I just want to push a bit more. It's an idea, it's a prototype. I want to explore it a bit. I have so many ideas I want to try out. For example, build a real-time debugger. I have an experiment visualizing like heap allocations and sizes of all that. More WebAssembly, like support more stuff, support proposals, support the components proposal, core types. Build a proper scheduler, dynamic linking, all that, and then open source it, right? That's very important to me because I like open source. I don't know about which is soon TM, right? I won't open source it right now because I didn't have the time. If you want to follow along, right, and know when it's open source, hang out, chat about it. I made a Discord server if you want to hang, talk about WebAssembly, talk about embedded, talk about OS stuff like that. Very happy to have you. Otherwise, Twitter, Mastodon, or just, come and talk after. That said, thank you. Questions, and then lunch. Two minutes.
I should not stand in front of the QR code. So are there any questions? Hands, please. I see lots of phones. I see a question there. Oh, okay.
Start. Hi, I was wondering what you intend to do about DMA safety in drivers and things like that.
Right.
I know this is a challenging thing.
That is a challenging thing. One experiment I want to try is, how WebAssembly has the concept of linear memories, right? And by default, you have one, but you can also have multiple memories. And you can also import and export memories. And so the one thing I want to try is, can I import from the kernel sort of a memory with like a special name, right? And instead of that being just like a heap allocated space, it would then map to like a MMIO, sort of memory mapped IO, yeah, MMIO. Register thing, right? So basically, you treat everything as memory mapped I/O, and then import and export different memory regions. That's my plan right now. I think it might work. We'll see. If not, then revisit that. But that's a research item, definitely.
Yeah.
Oh,
so
awesome.
how do you plan to deal with things that are very performance intensive, like things like Zlib that have to be simply optimized explicitly? That's
right. So WebAssembly has support for SIMD, right? And my idea is that if sort of we have this compiler that everything shares, right? If I want to optimize something for a sort of very specific hardware, then why not just contribute that support to the compiler instead of baking that into my app where only I can use it? Why not make that be supported by the compiler so possibly more people can use it, right? So sharing work in that way, where if I work sort of on this shared thing, then possibly more people get to benefit from it than just sort of my weird niche little optimization scenario. Yeah, I hope that answers it. Any more questions?
Hey.
Yes?
Yeah, I'm working on firmware that is written in Rust, also known as Orboot. You might have heard of it. I would really like to run this here. Let's do this on bare metal.
Yes.
And I've actually been pitching this, so this is perfect because I also wanted to do this, and now you did it, so thank you.
Awesome. Well, any more questions?
Final question, there again.
Hey, nice talk. I just wanted to commend you for doing anything related to Wasm time, because I have also ported that to one of my Rust OSs, and it was a nightmare. So I don't want to let people walk away without understanding how impressive that is. So great job with that. My actual question is, there have been a variety of Wasm-based operating systems in academia and open source. Some are like KWAST, Redshirt is one. I was wondering if you could, if you're familiar with them, could you explain like what are the main differences in your work versus them?
So I must admit, I haven't, as far as sort of code goes, haven't looked at those too much. So
Okay.
that's a good question. I
Yeah,
actually
no worries.
really can't tell you. I think one of the big differences, at least right now architecturally, is that I only support RISC-V versus most of those operating systems that sort of target x86, right?
Yep, they do.
And that really has nothing to do with the WebAssembly part of it, but that sort of means like, you know, all your sort of code in the sort of behind the scenes operating system and the bootloader and the setup and all that tends to be like sort of, you know, shaped by the x86 idiosyncrasies. And mine, you know, right now, sort of I tried to keep it like reasonably general so that the abstractions could map to x86 as well. But it's sort of definitely shaped sort of by, you know, reduced instruction set architecture, sort of, you know, ARM, RISC-V, kind of that space.
Maybe one last follow-up question. Why did you select the microkernel architecture? You have Wasm, has some degree of isolation, maybe not perfect, especially in the face of like speculative execution attacks, but do you ever think about running it all in ring 0, whatever that's called on RISC-V?
Yes, and I mean, you could, the cool part is like running stuff in, it's called, in RISC-V it's called supervisor mode. Well, it's machine mode, but then you don't really run in machine mode. The cool part about sort of having this setup is that sort of running WebAssembly in supervisor mode versus in user mode is really like just a different trampoline into Wasm, right? Like that doesn't really change anything. Why I sort of think it's cool to have this microkernel architecture is that WebAssembly has very strong support for modules, for imports, for exports, and to me, like that just lends itself very well to like doing the microkernel architecture, where like everything is sort of in modules, and you have like sort of package management and do all that of like that way. Also because you sort of, you know, as I said, you kind of eliminate most of the overhead of like traditional like two-system call IPC in microkernels, where you like need to like send messages through the kernel space every time.
Right. Okay. Thanks. Yeah, I'd love to contribute to this as well, since I have an OS that runs some of this stuff for x86 and ARM, which is perfect since that's I don't.
Happy to chat.
Yeah.
Happy to chat.
Thanks very much.
Awesome. Well then.
Thanks a lot. Yeah, give a big hand of applause to Guns.
Right.
So that concludes this block of talks. We'll have the raffle if you want to enter right here in front of the stage in a moment. And I will not keep you for lunch. Lunch is again in Chaos en Chemie. I don't know what the weather is outside, but we'll see. So I'll see you back at 2 o'clock. Thank you. so you have the wireless power consortium standard,
right?
and then you have for your phone, basically. Separate graphics memory. Those points. Now the problem is that the relative size of the cores must be so much. So you have to feel it's also. But I wanted this.
Of data from these different levels. It's not like some nicely, beautifully coherent cache architecture. Like, in fact, a lot of times the caches are incoherent, and they promise you that they are incoherent. And you explicitly have to say, I am done using this data this way, and I'm now beginning to use it this way, and do what you need to do. Right? And so the creation of something like Mesa that can drive, say, an AMD
like 2 days after
is
some basic.
it's a major effort. And so, but the nice thing is that I think that Mesa, most of the interesting parts of Mesa all run to user space. And the only thing that's large in the kernel is the stuff to manage GPU's page tables. Multiple page trees looking at different, and it's for scheduling, right? So, you know, here is a block of GPU machine code to begin execution, right? And then there's like synchronization stuff that happens. Oh, and data transfer files, right? So say here's a block of data. So the actual machine it's probably only horribly drag your music, right? As opposed to Mesa itself, the user space is massively large. So yeah, I think that emulating the kernel, or I think that
it's all Rust async.
Implementing something like the Linux kernel APIs that Mesa drives seems like probably something that you can do, and then you can run Mesa in user space.
We mounted to with opening in for the battery.
And then you would just be vocal, right? And then you wouldn't have to. So I don't know how much but the idea of Vulkan is the first layer possible on top of, right? And like it really was just the AMD people, the way it got started. The predecessor was the AMD people saying, here is our internal API. Why don't we just use that? Right? And so, and then like in fact, it's promises to do no validation whatsoever. Right? It's like, wild DB, you break any of our rules, good luck. Right? And then they have the validation there, which you can check.
And this is async await and
everything. So that's just like
it also has 60 degrees of freedom, IMU,
right? And so it's really a pretty nice
battery charger. So this is the battery charger. So you have a picture.
Run that in your user space. And then it would just use
so vibration, basically a laptop speaker.
Yeah, and then you wouldn't have to deal with WGPU valves, WGPU knows how to drive local.
No, so this is the charger chip. So it's this battery is way too small for this chip. I needed the feature set.
Well, yeah, but then you've got like
physical constraints, right? So, if it would be like 6 centimeters, then I could make that
basically, you open something in the...
This thing is already pretty expensive.
Yeah, and then you IOC to the point.
Yeah, this is 0.8 millimeters. That's basically
because you don't live in the business. Yeah.
It's probably 7. Yeah, I wanted to keep it as small as possible. So the prototype will be semi-transparent plastics. Yeah. So you have this now getting 3D edition with like
it's actually running
a screw and then
each bed gets a separate SIM.
And then for the
and so if this is true in some of your simulations, then you have no choice but to run both the then with masks sets. They don't do anything if you're false. And then you complement the mask, and then you run the else, right? And so the actual flow protocol is not
Yeah, exactly. I still need to populate the antenna, but that's here. I need to tune it as well, like this is really new features, so but fine.
But if you have like a large scale, if it's not like 100 lambda the chips can identify the hotspots and right? So every individual laptop is spending the same value optimizing the same thing, right? Sharing something is really hard because you want to say, oh look, I found that when I'm running this server, we need to do some optimization. But you don't want to just give them a binary because that is optimized out of class, and then you don't have any verification.
So you want to use this whole? You need so if you want to use async, you need to have all that support basically.
That's what
mostly executor.
Yeah, okay. So you're
like synchronization primitives. There you re-implemented basically the Nordic stack. So the NRF file is not at all alive. It is again. It is again? Okay, it was there for a time. Yeah.
Yeah, and it's really interesting because specifically this project, you can analyze
yeah. You have to do that.
It's better than yesterday. Yeah, so much better. Very good. I really.
No, but there's also things like what if there's an update and like it's potentially the original stack.
You have self-inflicted shit, like silly person.
Yeah. I think the halls are pretty mature right now. Yeah, just be an async. You don't need it.
Yeah, sure.
It actually compiles one function. Yeah, the question was how mature is RustNL? It's F7 you said? F4.
F4 is very well supported. It's mostly like features that only a couple of chips have, they might not be implemented. And the ADC.
So you use ADC quite a lot.
Yeah, Embassy itself doesn't have support.
So you only need to know when the DNA is ready transfer.
Yeah, and Embassy does make it easy because you can have a DNA transfer and you can just wait when it's
what the async state is preventing in this regard, but for embassy.
Well, yeah, but for like
yeah, exactly. But for your futures, it needs to be also integrated properly. And I encountered some problems with the ESP32 C6, and that's I'm now using embassy. But still, you do need to do the management.
Well, but also the null pointer is not a valid C string.
That's the.
I know. So
yes.
Well, yeah.
But in Arctic you always had like hardware tasks, software tasks. Now with Arctic V2 it has integrated async. Hardware tasks are still the same. Software tasks are all async. Because you blocking out in them, of course. Have to care. But at least you've got the option.
Yes. Yeah. Do you have a specific reason why you might want to go to async? Because I don't know if battery is like a major concern for your drive. Like the motors will most definitely take more power than the controller 3D, but yeah.
It can boot on I don't know.
Yeah, it's good.
So we provide some power also that can go up to but the motors they go to like I don't know, they can get like
yeah. Yeah, for me that's a major reason why I went to async. So you want to wait for interrupts.
That's really nice. Like you don't have to like debounce buttons anymore because you can just wait for high and then for low.
Yes.
I don't care that much about async. I just want the code to be
readable, easily maintainable buffers.
You just that doesn't really, it provides you some structs and whatever to work because they really give you an
Yes, that's how we do it.
Because of this function materialize pins and you need those pins. And then it broke because now they started to use the part of the type is if it's input or output.
Yeah.
And in the new version they started using it to actually not do anything if you try to switch it into mode, which it already is. So now our transmute is just breaking because we would always just transmit it as an input.
Yeah.
And sometimes they weren't in the input, right? So I just go around and put
that's the reason why we have these types.
Exactly, yeah. So
I'm working right now on a GPU expander chip, which is connected to I2C bus. And I wanted to have like nice types, like if you have a peripherals crate or an L, that you take the pins out of the GPU peripheral. I want that same experience, but then for my GPU expander, that I can pass around an object to another thing. Yeah. That's the ownership of that pin of the GPU expander. And I want it to be future, fast and await. And you have this expander crate, which supports like 8 different GPU expands, but it's not async await at all.
Right.
So I might want to fix or change that crate, but I don't know what's still need to have the discussion. But I'm doing it on my own driver for now.
Yeah. It's actually funny because these types of things just aren't something you do in C.
Yeah.
And at Embedded World, I
those pins are embedded HAL for the expander crate, but you don't have embedded HAL GPIO ASIC.
No.
That only on the interrupt side. So if you listen of an input pin and you configure an interrupt for that pin, that exists, but not for the others. And configuring itself also is an async operation, of course, because it's an I2C.
Oh, like you want set high and set low to also be async.
Exactly. Yeah. So I'm trying to get that also done. Yeah, it's I2C, but you don't know.
I feel like that was a conscious decision, but
yeah, but I need it.
Yeah, well, yeah.
You want it. So I'm first implementing it, and then I'll have the discussion. I'll make a crate, publish it, and then if we want to merge it in the expander crate, then
yeah. Something that's also missing in embedded HAL that is like up and coming slowly still, but it's I3C.
Yeah, for sure. I haven't used it yet, but I have the BMI 323 Bosch accelerator for IMU on the board.
Yeah.
The BMI 323, that's a new general purpose accelerator. Yeah, and it has. Yeah, so it's it has I3C. Cubed. I cubed C.
I don't think it's I cubed.
I'll think it's
anyway. Like I3C.
Well, you also have I2S, right?
Yeah.
Yeah, but the nice thing about I3C is that it's compatible with I2C. So
backwards
compatible, yeah. So you can still hook it up to like an I2C bus.
I haven't used it, but I came to the documentation of that accelerator, and you can have like interrupts on the bus.
Inline, yes.
So it can broadcast like, hey, I have this.
Yeah, so it's actually pretty nice. So you can have multiple chips on the bus, and they can like assert the bus in some way that the microcontroller.
Extra line, yeah.
Without an extra line.
Okay.
No, it's just the two lines.
Okay.
The microcontroller can then pick it up.
Yeah.
You don't know which one then has it, but you might be able to put out like a broadcast message, and then all the ones that have an interrupt enabled will reply or something.
It's when I read it, it sounded quite complicated. So I was like, I'll deal with this later, and my ESP32 has no I-cubed.
No, like the newer STM32H5 has it. I think some new expressive stuff has it as well, like the P4.
And NRF, I think, also is coming.
The 54, yes. Which
54H, right? You need to call it.
Yeah, there is a 54L15, and then also an NH, and I don't know.
Oh, they added more.
Yeah.
I don't get their newsletters.
There are two variants at least.
I haven't done something with Nordic for a while.
Yeah, but like I start to dislike them because like they're announcing all this stuff, and then you're gonna look there like, oh, what's the data sheet, and then
Expressive
there.
also has this problem though.
Okay.
So like they announced the H4 to P4, and no news about it for a year.
But like with STM, they announced the U0. I looked at their data sheet, like, this looks nice. I went to Embedded World, like 4 weeks later, I got a free board with U0. And you know what? Now MDC has U0 support. This is how you do it.
I think it's delays. So they announce it from Optimism, and then there's some production issue.
Because I also asked them about their DECT NR Plus support, and they just couldn't tell me anything. Like,
They've talked about this 2 years ago.
Yeah. Like, this is nice, like maybe I want to use it, but like, what's the API gonna look like? Will it be part of like NRF modem? No. Maybe this summer they'll have more information.
This year they have increased sales, and I don't know how. Maybe Apple made something with one of the chips. Maybe the 53 that they made like Airbuds or something, Bluetooth LE audio.
There was this weird construction where it would first send one byte from the data register, and then it would start the EMA for the rest
kinds of drugs are already, let's see.
You don't use it for normal, right? You just set up the DNA and then start with
Depends on the use case.
Well, I've got like a really nice one with an digitally controlled induction heater I have. Because it's digitally controlled, I need to know, I need to measure the voltage over like the coil, or at least one part of the coil, because I need to be able to calculate the resonance frequency of it.
Dynamically adjust it. Because it also depends on what you put in the core, right?
Yes, it changes.
Yeah, exactly. Yeah.
So I need to continuously measure this. So I've got an ADC attached to it, but then how do I synchronize it with like, because I need to time it very precisely.
Exactly.
So I've made it so that the hardware timer that actually controls the IGBTs, which do the oscillation, it sends out an internal signal to the ADC to start, like exactly in sync.
Yeah. So you have to sample at the same time. Yeah.
Yes. Yeah. Then on the ADC side, I have to set up the DMA with the buffer I have, so everything is like ready. I need to set the enable bit of the ADC. Then it waits to be triggered. Then the DMA at some point will give an interrupt that it's done. But I'm not really managing that because I'm using Embassy. So from the code side, it has like a bunch of setup. But then it's just like, okay, ADC, start, and DMA, wait until you're done.
Yeah, that's basically what you're going to do.
Yeah.
Right? But how do you get the time for that sample? Like, you can't put it in the same frame or something, right? Or is it not relevant?
Same
Oh,
frame.
you have to fix
fix start time.
You know exactly the time between samples. So
Yeah.
how exact
does the timing?
Well, like if you're off a little bit, it doesn't matter. But if you're off by a lot, like hardware can break.
It's like, I guess, at least in our sequence, like 480 cycles, you can choose how long it takes to how long should the ADC.
Oh, I'm just letting it go as fast as
how
possible.
long the ADC should take to collect it, because then you get more precision if you use more cycles for the minimum.
Well, yeah.
Less cycles for less bits of that. But yeah, you just run it circularly, so as soon as it finishes, it reads another sample and puts it in the memory.
Yeah.
And when you need it, you just read the memory directly, and it always has the sample.
Yeah, well, in my case, I don't really care about the exact samples. I care about the shape that I'm seeing, because I've got like an algorithm that tries to detect the peak. Because like at the peak, you've got like a quarter of the full cycle. So you take the time between the start and the peak times 4, and then 1 divided by that, I guess. And then you've got your frequency. So yeah, maybe like the data isn't great, and if it's like really pushing a lot of current through there, like there's probably tons of electromagnetic radiation.
What are you heating up with it?
Not much yet, because I tried it out. This is a while ago. I need to have some time to, I was pushing it. It was running at like 550 watts. I had like a nice huge steel beam in there, and then I thought like, okay, you know what? It's running fine. I want to push it further, but I want to get my fire extinguisher first.
Yes. Yeah, maybe some precautions.
Just in case. So.
Do it outside, maybe.
Yeah.
We melted our wires in the wall with electric heater. It was like 2,000 watt heater. The wire went through like the box of our light in the bedroom, and the cable just melted inside.
But shouldn't circuit breaker trip?
Oh yeah, it didn't trip off.
Yeah, but
the cable melted.
Too late.
Yeah, but like if it goes through a lighting cable that can only handle like 1400 watts.
I guess. Well, there's just a power socket next to the lighting switch in one bedroom, but both of it runs through the box.
Oh, that's really bad.
I don't know.
Yeah.
Then you like find out the place where it actually mounted.
Maybe install a different cable.
But in any case, so the induction heater is controlled by my laptop through like Modbus, like a nice visualization app. I can just press E for enable, so to have it enable or disable. So I click E to disable it, and my two power supplies both go click, 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 click.
Yeah, overcurrent.
So some stuff broke.
Yeah.
Apparently it doesn't like to be shut off when there's like huge amounts of current. So
maybe inductive spike.
yeah, I've tried to remedy it by like playing with the duty cycles, but it doesn't seem to work very well. So in my next revision, if there will be one, I need to be able to turn on and off the power from the microcontroller, because then I can just set it oscillating and then enable the power and then cut the power and just keep oscillating for like a couple of seconds and then shut it off. So yeah, some stuff broke. I need to resolder.
We also have like power switches that are suitable for inductive ones that have like protection features to protect everything upstream from nastiness. maybe add that as well. They do tend to have a high internal resistance though, so like heat up a bit, but you have several options.
Yeah, I don't know. But yeah.
I think maybe lunch is, the queue is dissipated.
Yeah, well, I'm over the deadline, so.
Oh, okay. Maybe you should go there.
We're about. We're about to start again, so please take your seats. Enter, enter. I still see people coming in, so we'll wait a bit.
Okay. Lucas, could you talk to him? Oh, God, never mind. Somebody's forgotten a backpack, so we'll figure it out.
We're about to start, so please find your seat. Het is wel een spreker van de tijd. Dus het is wel fijn als wij eerlijk zijn en lief de spreker. Welcome, welcome, welcome everyone. Please take your seat. We are starting again.
Indeed,
the Dutch weather
yes.
has asserted itself.
Yes, we have both put on sweaters.
It's raining, so that's also typical. Gone are the sunny days again for this year.
It's important that you get the real Dutch weather experience, of course.
But I hope you have all had a lovely lunch. I did, for sure.
Yeah.
So yeah, let's kick off again. I think we have to talk about sponsors again.
We have to talk about sponsors because they made this event possible. We have some silver sponsors to thank, which are Tandem Drive, Hyperswitch, and of course, we have to thank the organizing partner, Tweede Golf. Erik from Tweede Golf has been the main part of the organization.
Instrumental, yes.
Instrumental, and they've helped out enormously. So big thanks to them.
Round of applause. And I think we're up again for the next talk. So the next speaker, personally, I use his ecosystem of crates daily. So I have a lot personally to thank for him. But he's huge in the embedded community. I think I see him on Matrix almost every day, so that's very nice. He's also a CTO of a company called Achilles. I think I pronounced it correctly. Achilles.
Achilles.
But he has founded the Embassy project and is project lead. And I think also that his talk is concerning this project. So give a big hand of applause to Dario.
Thank you for the warm and awesome welcome. So yeah, I'm Dario, and I will be talking about Embassy. So for a bit of background, like how did I end up here? Who is this guy? So I'm the CTO of Achilles, my company where we do smart access control systems. So it's a suite of devices with different capabilities for access control. So we manufacture, design, and test, and then sell the hardware all in-house. And as part of this process, we had, of course, to write the firmware for them. So at the very beginning, I wrote the firmware in C, using the tools from the vendor SDK. It worked. It was enough to launch. The devices worked well enough to get paying customers. But as the project scaled up in complexity, we wanted to do more things concurrently, add new networking protocols, expand the capabilities of the devices. I found C was starting to become a nuisance. So this was 2019. Async Rust had just been stabilized. Rust had been on my radar for a few years. And async Rust was the trigger. I was wondering, hey, maybe this could be great. So in 2019, 2020, I actually did the crazy thing of rewriting everything in Rust using async. And as part of that process, I started writing some tools like an executor suitable for embedded systems, and then hardware abstraction layers for using the chips we were using, and then other chips. Posted it on GitHub. It started getting some traction. So this is what's now known as the Embassy project. So I'm also now the maintainer of it, main maintainer. So when I say async for embedded systems, embedded is a very wide term. I'm focusing mainly on microcontroller-based embedded systems, not embedded Linux, like routers or kiosks, but just microcontrollers. So these are really small chips, commonly using architectures like ARM M profile, so it's more restricted than the ARMs on your phone or RISC-V, other architectures. They come with no OS. From the moment you apply power to the chip, the first instruction that runs is your code already, unless, of course, you can bring your own. More on that later. They are tiny. A small microcontroller would be 4 kilobytes of RAM. They go up to 256K, would be considered a big one, and 1 megabyte of flash. And also, this is interesting. Since you typically have so little memory, it's a best practice to not use alloc, to not use a heap. It's not actually required. There are crates you can add to your project to get a working heap, and it integrates with the standard library, so you can get vec and string and all the maps working. But since you have so little RAM, it makes RAM usage actually very unpredictable. You don't want to receive a big string over the network and then run out of RAM in a random place in your code that's impossible to handle the error. So basically, all you can do is crash and reboot. So to avoid this, you typically avoid using alloc. You use fixed size buffers. If you know you need to handle 3 connections, then you create 3 connection slots, etc. So when you write firmware for a microcontroller, in C, traditionally, you would use an RTOS, a real-time operating system. There's many of them. This is by no means an exhaustive list. There's a Wikipedia list, which is really intimidating. There's hundreds of them. Because as soon as you want to do like moderately complex things, like handle data on a TCP connection at the same time you wait for button press, at the same time you handle Bluetooth, like if you have no OS, you have no threads, you have to make one main loop handling everything and write everything as a state machine manually, which is really annoying, scales really badly, and composes really badly. So you would use an RTOS. It gives you threads, which is commonly called tasks in RTOSes, which actually has nothing to do with async tasks. It's the same as threads in Linux. So each thread has its own stack, its own CPU registers, and there's like a tiny kernel that does context switching and scheduling between threads. You get all the usual niceties to use threads, semaphores, media access channels, mailboxes, whatever. You get drivers for your microcontroller. So if you have a serial port, you want to do some I/O, that typically comes as part of the RTOS. So you write on top of the RTOS APIs to do I/O, and that uses the drivers for your chip underneath. And for more complete RTOSes, depending on your use case, you may want to get a network stack, a file system, key value store, whatever. So in 2019, and it has improved a bit today, but I would still say this is the case. There was no mature RTOS in pure Rust back then. There were a few like TOC, but like for more niche use cases that didn't apply to the things I wanted. So I had the option to either use no RTOS, but that wasn't very appealing. I had the option of use a wrapper for a C RTOS, but that's not very appealing either. If you have to bind gen, it comes with its own set of problems, and you have to juggle the C compiler and the Rust compiler. So if you can avoid that, I would recommend you avoid it. So I thought, hey, there's Rust. There's this thing called async, just stabilized, with a quite unique design, like this thing that converts straight line code to state machines for you, and the state machines are like completely sized at compile time, so it could work without alloc. So even if the underlying mechanism is very different to RTOS threads, maybe this could give you like a similar developer experience. Like you got tasks where you write straight line code that each task handles one thing, and you got like a scheduler. In this case, it would be the executor that makes sure all these tasks get scheduled and run concurrently. So I wonder, hey, let's give this a try. So to begin with, the most critical piece of using async is the executor. So this is a rough overview of how a standard executor in Linux would work, like Small or Tokyo. So first of all, you allocate all the tasks in the heap. Each task contains the future, that is like the top-level future for the task, plus a bit of bookkeeping data. You got wakers that point into these tasks. You got the executor, which has a task queue of all the tasks that have been woken and are pending to be pulled. All of these have pointers into the heap. You can have multiple pointers into the same task, so you need to reference count them. So each waker counts as a ref count. Each time the task is pointed from the task queue, that counts as one ref count. All the other things like join handles and stuff like that also points into tasks, also counts into a ref count. So when the ref count reaches 0, you can deallocate the task. Like when it exits and there's no wakers pointing to it, you can reclaim that memory and then reuse it later. And all these tasks, when pulled, they register their file descriptors into something commonly called a reactor, which is usually driven as part of the executor. The reactor collects all the file handles and then tells the OS, hey, I've pulled all these tasks. They're waiting on all these file descriptors. And then you do a single system call saying, hey, please notify me when one of these file descriptors becomes ready. So the main loop of the executor looks something like this. So this obviously doesn't work in embedded. First of all, it uses alloc. We have to get creative to try to get it use no alloc. And second of all, we have no operating system. We don't even have a concept of file descriptor. So we don't have EPOL. How do we make this work? So this is the main structure of this talk, I will be going through all these challenges, and we will explore how Embassy solved them, what similarities and differences are there between Embassy and a standard async executor. So first of all, let's get rid of alloc. So obviously, you cannot allocate the tasks in the heap, but also there are also other uses of alloc in the executor. For example, your task queue could be a vec or a dequeue that, since it can hold an amount of tasks that you don't know at compile time, it has to grow dynamically, so that uses alloc also, so we cannot use that either. We have to use different data structures. So where do we allocate the tasks? So in a Rust program, there's only 3 main places you can allocate things. You can allocate them on the heap, on the stack, or on statically, on a static. So of course, we cannot heap allocate them. We cannot stack allocate them either, because wakers have no lifetime attached. They can live forever as long as the user wants to. And we have to prevent waker pointers from becoming dangling. So with a reference count, you can actually delay deallocating the task until all the wakers are gone. But in the stack, you cannot do that, because the user can return from a stack frame at any time, and the whole stack frame will be deallocated, and that will leave dangling pointers in the wakers. So that's not a possibility. So the logical conclusion is, third place, the only alternative left is statically allocate them in a static. So this is what Embassy Executor does. Each task gets its own static variable with a task structure. That same idea. It wraps the task top-level future with some extra bookkeeping data. And for the task queue, instead of using a dynamically sized queue, we use an intrusive linked list. Because it's, even if Rust is not great at linked lists, you have to use some unsafe. But the good thing about it is you don't need dynamically sized data structures. Like every task you allocate has room for 1 pointer for the next task, and then the executor has a pointer into the first task. And then wakers, of course, just point into the tasks, and you don't need to do any ref counting at all. Like, since tasks are statically allocated, they live forever, so all these pointers are valid forever. So waker drop is a no-op even. So this actually simplifies the executor a lot. So to statically allocate tasks, this is how a small Embassy program would look like. As you can see, it looks almost the same as a standard Rust async, like you would write in Tokyo. You write an async function, and then you spawn it. The only difference is this thing here. We got a macro saying, hey, this is a task. This is not a regular async function. This is a task. And you need this because you need to create a static for each task. And the only way to do this is with a macro, if you don't want the user to write this manually. So this expands to a static containing the task, then the async function, which is renamed with an inner suffix, so the user doesn't touch that directly, and then the function that the user does call initializes the task in this static, and then returns something called the spawn token. So instead of returning the actual future, it returns the spawn token, which is kind of a pointer into a task that's been initialized and is ready for start to run. Because like we cannot actually pass the future to the allocator like you would in STD, because the executor would have to heap allocate it. So one challenge with this is in Rust, maybe you've run into this if you have used async. The return value of an async function is the future for it. And it is actually a struct auto-generated by the compiler, like this automatically generated state machine. It implements the future trait, but the actual type of it is a magic type that is not nameable. And in Rust, there is no type inference in statics. So you have to name the full type of the task future in the static. So how do you do this? Is using nightly only features, type alias input trait. So you can say, hey, I have this type alias called my task future, which is input future. It's some type that implements future, I will leave you to the compiler to figure out what it is. And it's kind of some whole program type inference. So it will look at all the usages of that type. And when you equate that type with the actual future type returned by my task inner, it will actually infer, hey, this type is this future. So this way you can give a name to this magic unnameable future type. And then you can just use it in the static declaration. So of course, the challenge is this is nightly only. So currently, Embassy works on stable, but it has a fallback, which uses a very simple bump allocator. So you do have out-of-memory errors at runtime, but only when you spawn tasks, which you typically do only at boot. And only if you use nightly, you can opt in to be fully no alloc. But yeah, this is something that should get stabilized eventually. And when that happens, Embassy will be truly no alloc. And the second challenge is we got no operating system at all, as I said before. So how do we do I/O? Well, a very rough overview of how I/O works on a microcontroller. These things are actually called system on chips. They're not just the CPU core. They're a set of things, among which there's the core, which is actually what runs your code. It's connected to a data bus. And through that data bus, it can do memory transfers to flash, RAM, and also to peripherals. These peripherals are connected to the pins, the physical pins on the chip. And you would connect them on your board to like buttons, LEDs, motors, sensors, whatever you want your device to do. So to talk with these things outside your chip, you need to use these peripherals. So how do you use a peripheral? Well, the peripherals are memory mapped. So you use MMIO, memory mapped I/O, typically, which means like the peripheral appears in some magic region of memory, which is neither RAM nor flash. Instead, it has like registers, which are like magic memory locations where like you can do a write to tell the peripheral to do things, or you can do a read to receive information from the peripheral. So for example, imagine you connected a button to a GPIO pin. You could say, hey, pin config, write, direction input. So you tell the peripheral, hey, configure this pin as an input, because I want to read from it. And then you can read the input register, and the peripheral will tell you, hey, the pin is low, so the button is not pressed, or the pin is high, so the button is pressed. So this is the basics of how you do I/O. But you not always want to read the state of something. You sometimes want to wait for something. For example, we want to wait for the button to be pressed. This is a really common thing to do. Typically, if your device has some kind of UI, you sit idle, and you wait for the user to press a button or touch something in the touchscreen. Or a sensor to detect something. So the dumb way to do this is, OK, fine, I will spin, read this register in a loop, and wait for the value to change. So when it goes high, hey, the button has been pressed, and then break the loop and continue. But of course, this sucks for a few reasons. First reason is, while you're spinning here, you cannot do any useful work. You're just waiting, burning CPU time. And of course, it's also really bad for low power. If you build battery devices, battery-powered devices, which I do, you don't want to do this because you're like keeping your core on all the time. If you would do something smarter, if there's nothing else to do, you could put the core to sleep, saving a lot of power. So to solve this, peripherals also have this thing called interrupts, which is an extra signal from the peripheral to the core, where the peripheral can say, hey, something happened. And then when a peripheral fires an interrupt, the core will magically say, oh, something happened. It will magically stop executing wherever it was executing it. It will interrupt execution, that's hence the name, interrupt. And it will jump to an interrupt handler, which is this function at the top with this interrupt attribute. So as you can see, this function is never called. And this is not because the example is abbreviated. This function is really never called from the rest of your code. It's called by the hardware. It's like a callback that the peripheral sends you. So for example, you can tell the GPIO peripheral, hey, write the sense field to high. Like, hey, wait for this pin to go high. Send me an interrupt when it goes high. And then once you've done this, you can go do other things, or you can go sleep, and the peripheral will send you an interrupt. And then when you receive this interrupt, you can check the event, check what happened, and say, hey, the button was pressed. So we get the same functionality as before, but it's much more power efficient, much more CPU time efficient. So this is the core of how I/O works on a microcontroller. Like all peripherals are a version of this. They might be more or less complicated, but the idea is this. You wait for interrupts. So let's asyncify it. Let's actually wrap it into Rust async to make this actually easy to use instead of getting interrupt callback hell. So how do you do this is you write a feature. So at the very bottom level, when you're interacting with the hardware, you will have to write features manually instead of using async fun. So what you do is, the first thing you do is you register the waker on a global variable. And then you check the pin. Is it high? Is it low? Is the button pressed or not? If it is, then great, we're done waiting. Return ready. And then the caller will keep executing async code that was after it. If it's not, return poll pending. That will signal the task to yield, saying, hey, I'm waiting for something, I cannot do any more progress. And since we registered the waker in a global variable, the interrupt will fire. And when the interrupt fires, you wake the waker, which will put back the task into the executor's queue. It will get polled again. This time, we will go into the ready branch, and then execution will resume. So once you've stood up all this infrastructure for peripherals, using async is really easy. You just await things. And you can use all the classic combinators and timeouts, join, select, whatever. So this is a bit of an overview of the main loop in embedded async. So it's not driven by epoll, it's driven by interrupts. So you got the tasks that poll futures. The bottom leaf futures will wait for events from the hardware, so they enable the interrupts to tell the hardware, hey, please send me an interrupt when the event happens. And the interrupts will wake the task, which will cause polling again. And so this will go on and on and on, and this is what drives execution forward. So one very interesting difference between this and desktop async is there's no reactor. Like, you might have noticed here, this is the entire implementation of the driver. There's nothing that talks to the executor saying, hey, please register this file descriptor, or hey, please wait for this interrupt. The driver is completely self-contained. It registers the interrupt handler and enables it and talks to the hardware all on its own. It doesn't need anything from the executor. So the executor is just polling tasks and then sleeping the core. So one really cool side benefit of it that I found quite surprising, because I was hoping this to be worse in embedded than in non-embedded, but actually it's the other way, interestingly, is you don't get this fragmentation that you get in standard executors like Tokyo, where if you use Tokyo TCP I/O, that needs to register a file descriptor in the Tokyo reactor, and then you must be running the Tokyo executor for that to work. Otherwise, it just won't. So this is not the case in embedded. You write drivers, they work, and they work with any executor. And as long as you write your executor properly, it will be able to run any driver without having to explicitly add support for particular hardware to it. Like it's almost architecture independent even. Like, if you want the executor to put the core to sleep, you have to do some architecture-specific things, but that's about it. And we got our goal of replacing an RTOS. So async is not an RTOS, but it gives you the convenience of one. So you can use it instead of an RTOS, not on top of it. We're not like getting POSIX APIs from an RTOS with epoll or select and then laying async on top of it. So the advantage is it's fast. It's about as fast as using an RTOS. Like the latency from wakes and scheduling is pretty much the same. Code size is smaller. The executor is just like 600 bytes, while for an RTOS, a kernel that does context switching would be bigger. And also, it's kind of simpler because you're not using lower-level things from the architecture for doing all the context switching. So to finish, this is actually not perfect. There is one big hole in Rust today that is causing problems for embedded usage, which is DMA. So when you read some data from a peripheral, If you want to read byte by byte, you will get an interrupt for every byte, which is really inefficient. So what you do instead is you tell the peripheral, hey, here's a pointer. Please receive 256 bytes to this RAM location. And the peripheral will do all the receiving there. It will write the data for RAM to you. And then it will only send an interrupt at the very end when all the receiving is done. So it's much more efficient. And it's also more ergonomic. You just do a read on a borrowed buffer. It's transparently using DMA underneath. It combines perfectly with all the async combinators. So for example, with a timeout, if you drop the read feature, it will go and tell the DMA, hey, please stop reading. I'm getting aborted. Please, that buffer is no longer yours. Just stop. But the problem is, in Rust, you don't have guaranteed that drop is called. You can leak things. So you can create a feature that borrows a buffer, start DMA, and then forget the feature. It will prevent drop from running, but it won't stop DMA. DMA will keep writing to that buffer, which is no longer borrowed. And you can, like, for example, return to the allocated, and then that buffer will be reused for something else, causing undefined behavior. And the truth is, Rust has no good solution for this today. Like, I've tried everything. Embassy's current position is just please don't. So it's a bit unfortunate that we still have a bit of like C thing that, hey, you're holding it wrong. So it's actually the same problem as in I/O U-ring. So I/O U-ring solves it by using owned buffers like vec, but we can't because no alloc. Using static inline buffers causes a lot of bloat. Static buffers is not really ergonomic. So Rust really needs a solution for this. So there's been a lot of conversation about this in the past years, either some auto-trait leak, forgettable, or must move, like undroppable types or unforgettable types. So we really need something like this, because otherwise there's no way we're going to get safe and ergonomic embedded DMA libs or I/O U-ring libs that have no overhead. So to finish, a rough overview of the Embassy project status. We have the executor. We get also real-time preemption. You get all the utilities you would expect from an async runtime: join, select, channels, mutexes, timers, instant and duration. It's got a built-in network stack where you can do async I/O, USB stack, Bluetooth, and then within the Embassy project, we maintain hardware section layers, like collections of drivers for doing I/O, for Nordic NRF, STM32, and Raspberry Pi RP2040 microcontrollers. But actually, as I said before, you can also choose to just use Embassy executor and then use another hardware abstraction layer. For example, Expressive ESP HAL, shout out to them. It has really great async support. So current status is it's mostly mature. It works really well. It has allowed us to ship really working, really stable firmware with lots of like fancy networking things: Bluetooth, Ethernet, Wi-Fi, mobile, mesh networking, and also low power. Like async is really great because it gives you like low power operation for free. Like we get battery powered devices where the battery lasts for 1 year without actually having to do any special things in your code. Like just yield and wait, and the executor automatically puts the core to sleep, and you get the best power consumption possible. So yeah, that's it. Feel free to reach out. Feel free to check out Embassy. If you have any questions, just ask. Thank you.
Thank you, Dario. Thank you. Right, so are there any questions for Dario? Oh, there's one.
So one nice thing about RTOS is the ability to have hard deadlines. How would that work with Embassy?
Yeah, so I've glossed a bit about it, briefly mentioned it here. Async is purely cooperative. So if you have two tasks and then one task wants to run, for example, it's got an interrupt, and another task is running, it will have to wait for this task to finish. However, this is only within one single executor, and then Embassy layers on top of this a real-time layer where you can create multiple executors at different priorities. And executors at higher priorities are driven by interrupts. So if a task on a higher priority is woken, it will trigger an interrupt, which will trigger the higher priority executor to start polling it, preempting whatever task was at the lower priority. So yes, you can get real-time preemption, kind of like in RTOSes. You pay a bit of latency for the executor in the higher priority, but it's mostly constant time unless you do like really egregious things. So yeah, you can do real-time stuff with it. If you really cannot pay the overhead, you can, of course, choose to use raw interrupts. And you can even mix in the same program raw interrupts and async for the less higher priority things. Yeah.
Someone online is asking, are there any production-ready projects written in Embassy so they can check it out?
So they tend to be mostly closed source because it's people using it for their companies. There's an Embassy in the wild section in the documentation. It lists some open source projects like sensor platforms, keyboards. I don't know of any like commercial grade project which is open source. Like mine isn't, for example, sadly.
Yeah, so in normal async await, you know that your code will only yield at an await point.
Mm-hmm.
But if you're using interrupts, I guess, well, your code can be interrupted at any moment. Does that have any consequences for the way you program your application?
Yes, very good question. So within the executor, everything is cooperative, and the executor is kind of single-threaded. So tasks running in the executor don't need send sync, like, for example, in multi-threaded Tokyo executor. If you spawn tasks at different priorities, then different priority levels from interrupts, even if you're using them raw or you're using them through a higher priority executor, different priority levels behave kind of as threads, because you get one kind of priority level that can be preempted at any time, like literally between any pair of instructions by another thread. So how it works is, if it feels a lot like threads, we can use the Rust send sync mechanism. So sending things across priority levels requires send. Sharing pointers across priority levels requires sync. And if you want interior mutability through sync things, you have to use a mutex, which is a critical section, which will temporarily block interrupts, saying, hey, I want exclusive access to this piece of data. So yeah, it does have an impact, but it's fully safe and fully checked at compile time, the same way standard Linux threads are in Rust. Yeah.
All right, any more questions over there?
Yeah, so is there anything that would be in your fantasy interrupt controller or fantasy hardware platform more general for this kind of?
So most of the work in Embassy has been the hardware abstraction layers, because hardware vendors do really crazy things at sometimes. Like sometimes you can tell, for example, they designed a peripheral to be used only by blocking, and then they bolted interrupts on top, but the interrupts flags work in weird ways, or they magically clear if you do some read. Or they even expect you to only do I/O in the interrupt, which is not the case in here, because you use the interrupt just for waking, and then the I/O is done from the task. So I don't have any actual concrete wish list. Like the existing design, like the ARM NVIC interrupt controller is really good. In RISC-V, we could use some more standardization. I don't think I have anything in the wish list. Actually, the only thing is, vendors, please don't do weird stuff. Like stick to regular interrupt flags that you manually clear and work the way they should work, and that's it. Yeah.
Hi.
Yeah, first of all, thanks. We use Embassy, over here. We use Embassy in production, and it's great. It makes our life a lot easier.
Awesome.
I am wondering, not all of the crates are currently on crates.io, and so we have to use like a Git dependency. Is there anything in particular that you're waiting for before having like a proper release cycle, or maybe a version 1 or something like that?
So all the crates are on crates.io in January. We released 0.1 of everything. Since then, there's not been many changes in the core, so the versions on crates.io are still relevant, and they're perfectly fine. On STM32, there's been more changes, so 0.2 release is a bit overdue. So yeah, the plan is to regularly do releases, maybe every a few months. But yeah, help is always welcome on that, because like coordinating releases and writing change logs and blog posts is a bit annoying. So yeah.
Alice over there.
So you said you had mutexes with atomic context-like things. Do you have operations that are unsafe to put inside such atomic contexts?
So the way it works is the atomic. No, so there's atomics, which are the standard core sync atomic.
So I'm thinking you mentioned a mutex.
Yeah.
Which prevents interrupts.
Yes.
Which reminds me of stuff we're doing in the Linux kernel, where we have trouble with, like, while you're in an atomic context or like the critical region of a spin lock, if you call anything that sleeps, that's a problem.
Yeah, so you already get that naturally, because while you lock the mutex, you have a closure. So you're already prevented from doing async stuff there. But other than that, no, there's no list of things you're allowed to do or not. Just if you lock a mutex, you have full immutable access to the interior of it, like in a regular Rust mutex. Yeah.
I guess you don't have threads.
No, you don't have threads. Yeah.
All right. Any more questions? All right. Then a big thank you to Dario.
Thank you.
All right, and he's already coming on stage.
Thank you.
So I'm going to announce him. He has to do some setup. Next up is Rafe Levine. He's a research software engineer at Google, at the Google Fonts team, where he's working on Google font GPU font rendering. He made Pull Down CMark, which is a super popular Markdown parser. He built the Druid UI framework. Now he was working on 2D rendering with Velo. He's built the Druid system right now, and now he's working on Xylm. It's a lot of stuff, and it's super impressive, and we're happy to have him. Please give it up for Rafe Levine.
Thank you. I'm so happy to be here. And this talk really is an invitation to you that we're working on this project of building high-performance UI. It's under the Xylm kind of umbrella for the project, but I'm going to talk about, I'm going to give an overview of the pieces of it, but the call to action here is come and get involved in the project. So first I want to talk a little bit about the goals of the project. So the real focus of this entire thing is high performance. And that's actually a little bit of an unusual goal. Like most of the time you're more focused on developer experience and so on and so forth, but we really feel like high performance is the niche. This is why you would use Rust to build UI. So that's driving a lot of the decisions that we're making. We're also focused on a very rich 2D graphics model. We want to have full access to vector graphics with all of the goodies like gradients and also really good font support. I'll talk about that a little bit more. Of course, that's what I do. But we don't want to just have something that's high performance and rich but very hard to program. We also want to make a really ergonomic, easy to use API on top of that. And we want this to work on desktop and mobile. The project is being funded by Google. It's a research project that's being funded by Google Fonts. And the focus of that is Android apps. So we want to do both. We want to demonstrate a really good experience on Android, but I think the community is interested in desktop and other targets as well. So this is a research project. The goals of this, we're not offering this as a product, something that's fully ready to use out of the box. Maybe it will evolve into that over time, but the goals for right now are to discover what is the best way to build UI in Rust, and to what extent are we able to realize these goals of being extremely high performance and fully featured as a user interface. And we want to work with the community. This is maybe a little bit of a newer focus of the project, that we've been maybe a little bit siloed, maybe doing some of our own things, but if you as I go through the slides, you'll see that there are a number of decisions that we've made about how do we cooperate with the Rust ecosystem instead of just doing our own thing. So this is kind of a picture of what the problems that you need to solve in UI, and I want to point people to Nico. Nico Burns did a talk on Monday, and there's also a white paper that's coming out soon, and that's giving that work is giving a much more complete picture of what you're seeing on the screen here. But we're seeing the problem in layers. So there's a top layer, which is reactivity, and this could be provided, like each of these layers, each of these boxes could be provided by a number of different crates. So this reactivity could be provided by Dioxys or Leptos. And then I'll be talking a lot more about what we're doing with this. And then there's a middle layer, which is solving a lot of the guts of what's involved in UI, of having a full collection of widgets and having gestures and layout and your text editing. There's a lot of problems that need to be solved at that layer. And then there's also a really important layer at the bottom of infrastructure. How do you connect to the platform, and how do you do the basic functions of drawing, text rendering, getting to your GPU, and accessibility? I'll be talking a lot more about that. So this is kind of our instantiation of this layered architecture. And so at the top level, we have the Xylm reactive architecture. In the middle layer, we have Masonry, which is our widget set, which does not depend on Xylm. So you could imagine using Masonry with Dioxys or Leptos. And then we're using Taffy for layout. And at the bottom, we have a mixture of things that are Rust ecosystem, like Winit. We made a decision. We switched over in January from our own platform integration to using Winit. And then a lot of the other things are things that we're building that obviously we're building for use in Xylm, but we're also hoping can be used by other projects in the Rust ecosystem. And again, like Xylm is generic. There's a Xylm core, which is generic over the element tree that it's driving. So we can drive Masonry widget set and also give a demo of using the Xylm core to drive DOM and create an experience that can run in the browser. So the Xylm architecture, the Xylm reactive architecture, gives you very simple code. Like this is your classic counter example, and this is really all of the code that there is. This is the actual code that I'm going to run. So it's a pretty simple code to get this functionality. And if I run this, we'll pray to the demo gods. We have a usable example. Very simple. And I'll tempt the demo gods a little bit more and do a little bit of live coding. Let's add a checkbox to this. So I'll add a checkbox and test my live typing skills. And we'll call it is0. And will be checked if count is actually equal to 0. And then on the action, we've got the app state, which in this case is just a count. And we've got a Boolean for whether it's checked, and we'll just set the count to 0 or 1 based on sort of the opposite of the checked state. And we'll coerce that to 32. And this should give an error because check, but I'll just add it. Easier to type than to use the editor action. And this is a Mac M1, so this is going to be a lot slower than what you saw yesterday morning. But it's pretty fast still. And now we've got a checkbox there, and we can use that. And if it's reactive, so like if you change the count here, reset it, it's changing the checkbox state because that's all kind of computed in the app logic that's here. All right. back to the slides. So there's a few things that are a little bit different than a lot of the reactive layers that you see are derived from the JavaScript world, which is typically very dynamically typed. And I think Xylm is a lot more inspired by Swift UI than it is by JavaScript frameworks. So everything that you're seeing, all of these views that are created are statically typed. And that also means that the process of reconciliation, of diffing, this is all working with statically typed data, so it's going to be a lot more efficient than doing something that's dynamically typed. You'll also notice, looking at that code, that there are no macros in there, that these are actually fairly simple Rust value data types. Like, when there's a string, well, there's no label in here. I'm not going to add a label in live-coded, but it's really just a string. And then that string is a view that creates the underlying label widget. But the programmer doesn't really have to worry about that. So as I mentioned, there's a generic Xylm core. In this case, we're generating a masonry view, which is our native widget type. But you could also generate other things, like web. And I'll show an example of that. So Xylm is based, the core of Xylm, drawing is really essential to any GUI toolkit, and that's also where you tend to spend most of the CPU time, most of the performance is just how fast can you get this thing drawn onto the screen. And so that's a lot of what I've been doing over the past few years, really, is building a fast 2D rendering engine that does as much of the work as possible on the GPU. You want to do as little as possible on the CPU. You want to offload all of that work to the GPU. So it is implementing the full standard 2D imaging model. So we have vector paths with fills and strokes, gradients, images, clips, blends, and text. Let's go to the demo. Let's see, don't need to have too many things running at the same time. So I'm just going to run through kind of our standard test scene. So you always have the tiger, obviously. You need to have that. Some of these things, like we have a lot of things in there for stroking, because just in the past few months, we've moved from the stroke expansion being computed on the CPU to entirely being computed on the GPU. And actually, there's a paper that I just submitted to a conference. You can see the preprint. There's a lot of math that goes into computing this stuff on the GPU. Also, I mentioned the turn vsync off. Things go a lot faster. Here's a fun test scene that has, a little bit. This is actually not a lot of strokes. We have test scenes in here that has, tens of thousands of strokes. And so this one is showing a bunch of things. It's showing the animation and an image in there. And one of the things that we're also showing here is that our text and font handling is able to do variable fonts. And one of the goals, one of the things that's kind of driving this, is to be able to do richer things like animate those variable font parameters. So you can go from light to bold, and you can animate the width completely dynamically. And that's to get really high performance. This would be a major challenge with existing 2D graphics libraries. So this is just kind of going through. This is our engineering test scene. So here you can see all the different blend modes. There's more coming up that are sort of stress tests for how many line segments that you can have and still get decent performance. Yeah, this is another one. This is the motion mark example. And let's see, with the stats that you can ramp up to, I think it goes up to like 70,000 and still running at over 120 frames a second. So the performance, moving all of this from the CPU to the GPU just unlocks hugely increased performance. I'll show you another example that really shows off their performance. This is one of our standard test scenes. It's a map of Paris. It has 1 million path segments in the image. You can zoom in. You can see there's a lot of detail there. And when we're vsync off, you get hundreds of frames per second. And again, with standard rendering thing, it's challenging even to get 60 frames a second out of this particular test scene. So that's really a lot of what the Xylm project is about, is how do you exploit, if you have all that power, if you have all that graphical power, how do you exploit that from Rust UI? So there's a lot more to be said, including the multi-threaded encoding. Like, if you're rendering a scene of that richness and complexity, and you're only able to get that data to the GPU from a single thread, that can easily be the bottleneck. So one of the goals of this project is have the different parts of the UI running in different threads and have it assemble all of these scene fragments together. So there's a lot of technical detail. Actually, I have a talk that I was going to put a link. I forgot to do that. I did a talk at Rust Lab last November, and I go into a lot more detail about the Velo engine. So if you're interested, go check out that talk. So the way that we use Velo in Xylm is also interesting, because this is a different API. This is not having a canvas context that has an and mute reference to it, which would restrict you to a single thread. So we have a model in which the widget in Xylm retains a scene fragment. So the scene fragment is kind of, you can think of a scene fragment as like a snippet of binary SVG. So if you're painting, you don't have to repaint the whole widget every time. That you can retain that scene fragment and only re-encode the subtree when it's changed. And so you can do things like change the transform. So if you're doing scrolling, you don't have to be re-encoding all of the content of what's inside that clip window. You can just reuse that and then have the GPU do all the work of re-rendering it. So it's all about making the CPU do as little as possible and making the GPU do the work, where it can be actually about 10 times as efficient in terms of how much throughput you can get per second or how much throughput you can get per watt. Another one of the layers, or another one of the bricks in that image, text is obviously really central to any GUI. And so we have this new crate, and all of these crates, by the way, that you saw, the pictures that you see here in bold, most of these just got released in the last like 2 or 3 weeks. Some of them, I think the Xylm crate actually got released at midnight, so yesterday or today. A lot in preparation for this talk. And of course, we've been working on it for a very long time, but Parley is another one that got released, I think, maybe 2 or 3 weeks ago. And it's an advanced text layout engine, and so it does the basics of text layout, so it does paragraph layout with line breaking. It has the ability to set attributes. You can do bold and italic and all that fun stuff. But it goes, and of course, it's designed for performance, really metal performance. But we're also trying to do some richer things. So it supports variable fonts, and one of our goals, we don't have it, what you saw in the demo was not using Parley, I don't think. But we want to support variable fonts. We want to support the animation of variable font access and do like richer interactions in the UI. Parley itself, of course, it works well with Velo, but it is not tied to a specific 2D rendering image. So this is one of these blocks that you can mix and match however you like. There's some details here. It's depending. There's 2 crates that are kind of below Parley. One is called Fontique. And Fontique accesses the system fonts and enumerates them and figures out which font is needed to render which script. And there's also a crate called Scrifa, which does the low-level font loading. So this is really the Rust alternative to FreeType. I think one of the most exciting things about Scrifa is that there's work in progress to get this integrated into Chrome. And so that's actually in a Chrome Canary build, I believe, under a flag. But the goal is to make that really production quality to support all of the font loading that kind of low-level font needs that Chrome has, which is a pretty big requirement. Another major goal of our project is to support accessibility well out of the box. And so we're funding work on AccessKit, which is, I think, the Rust ecosystem crate for doing accessibility. And so it's a portable abstraction layer. Each platform has its own API for how it exposes accessibility. And so the Mac and Windows and Linux, more recently, backends are working pretty well. Android is in progress. That's one of our goals, to get that working. AccessKit is, of course, written in Rust, but there are bindings. We want to make that available for other languages. And there's some technical details I'll skip past and just go straight to the demo. So we'll actually use that same simple example. And I'll go into the settings here. And I think I'll probably turn down the offer to update my software and go into accessibility and just turn on VoiceOver. Great. Fantastic. So now I can use, why is it not reading out loud? The demo gods are not smiling on me. VoiceOver on. You can see what it's supposed to be reading, and then it's not reading it aloud. This is you'll have to see me after. This is really disappointing because I wanted it to be reading aloud, but I will at least be able to show that I'm able to use the keyboard to navigate the different widgets here, and be able to control these widgets from the accessibility layer in the platform. All right, go see me after, and I'll get this demo working, and you'll be able to see it then. And then I should probably turn it off. Okay, all right. And actually, while we're on the text layout, I want to show one of the other demos that I've got going here, which is our 2Do MVC. And so this is all work that's in progress. This is not, there's a lot of stuff that is working, but there's a lot of stuff that isn't wired up yet. So we'll greet the RustNL audience. And then let's translate it into, let's see, well, we'll go with Japanese today. All right. And so the input method works. So we're able to type in Japanese and have that work with the application. And of course, we're rendering that in the Japanese font and displaying it. And of course, it supports, pretty much all of the international scripts there. All right. Great. So the next demo that I want to show, there's a lot of demos here, is Xylm vector graphics. So obviously vector graphics is a major focus of what we're trying to do. And this is a different instantiation of the Xylm generic reactive layer. So instead of generating the native widgets like you've just been seeing, we can also generate DOM nodes, and in this particular case, really focused on SVG. So this is another instantiation of the Xylm core layer. And then we have a goal, there's an early prototype of using those same views and drawing them with the Velo drawing layer, but I'm not going to be demoing that today. Instead, I will be showing you, so we use this thing called trunk, which is just something that compiles Rust into WASM. And let's see, and then I'll pull up the browser, and we'll just go there. And we have now, so this is something that I was developing as a sort of interactive exploration of the curve stuff for the stroke expansion. And so you can move the curves around, and you can change the offset. So these are all HTML and SVG elements that are under the surface here. And one of the things I wanted to show you is just how nice and beautifully interactive this is for exploration. So I can go into my editor here, and let's take that red stroke and change it to green. And then as soon as I do Command S, like watch what happens. As soon as I do Command S, it's about 250 milliseconds, and it rebuilds that WASM blob and loads it in the browser, and now I have a green stroke instead of a red. And that's fully recompiling this little Rust application. So that's, I think, showing some of the power of Xylm as a reactive layer, and we're going to be working towards convergence so you don't have to write your code completely separately, once for the web and once for native. All right. So I also want to talk a little bit about some of the future work, and I think one of the reasons why I'm talking about this right now is that it motivates some of the design decisions that we want to do. So if you're using a UI toolkit at scale, you have to deal with large data sets. And one of the things that you absolutely cannot do is generate a vector, a vec, or an array, or whatever, of all of the elements in your scroll view and diff over that whole thing. That works up to a certain size, maybe up to 1,000 elements or so. But when you're dealing with really large data sets, you have to do this in a more efficient way. And so we have a plan. We have a rough prototype of this that It hasn't been released, but like enough that I think we have confidence in this approach. And so what we want to do is to have a viewport. You know what's scrolled on the screen at any given time. You're only materializing the widgets that are in that viewport. And then there has to be a communications protocol between the widget layer and the view layer. So the widget layer knows what widgets are available, which ones are being scrolled into the viewport, and then you're sending messages. And these are actually, if you think about it, those messages are not that different than saying, hey, this button has been clicked at this time, but instead of that, you're saying, please materialize this widget that's being scrolled into view and dematerialize it when you don't need it. And it's actually a little bit more sophisticated, the logic that you need. Like, for example, if you have a widget that's focused, if it's a text view that's focused, if you scroll it out of the screen, you still want to keep it materialized because you don't want it to lose state. And the idea is that the widget layer has all of that context. The widget layer knows which widgets need to be materialized, which widgets need to stay there. And so it's in control of that, and it's asking the view layer, cooperate with me, so that as new widgets need to scroll into place, get those materialized. So this is a fairly easy problem if you know the height of all of the elements in that list, because then the calculation for like where the scroll bars go and so on and so forth is just divide by the width. It's trivial. But we also plan to handle the case where the different children may be different heights. They may be posts in a social media app or something like that. And we're planning to do a fairly sophisticated thing where we use statistics to estimate those heights and incrementally refine them so that, as you scroll through, you're materializing more widgets, you have more accurate information. And so that's something, that's kind of a juicy problem. It involves computer science and a little bit of magic, like how do you hide, if you don't have that geometry exact, how do you hide that from the user so they don't really see the approximation going on under the hood. And then we also want to make the view layer ergonomic. So we want to have a rope-based vector so that it looks just like a vector. You can insert and delete and do all those kind of things. But if you say, here's the old vector and here's the new vector, give me the diff between these, instead of running down all of the elements in the vector, by using a rope, we'll be able to use sparse diffing, so it'll only look at the pointers that have changed in that representation and hopefully be super efficient. I think one of the motivations for this kind of approach is that you can't really do this completely seamlessly using web technology. It's very seductive to try and build on the web, and the Diaxis project is doing amazing things, building on the web, building on top of web technology, but there's certain experiences that you just can't quite reach. And we think this is one of those, and so we're really excited to build, a list view that has significantly higher performance. Another kind of characteristic of our project is we're really focused on working with the community, collaborating with a lot of other great projects that are out there. So as I mentioned, we have switched to using Winit for our platform integration. Previously, we had our own crate because we thought, maybe we can do these things a little bit better, but we've really decided we're going to be working with Winit, and we're going to be trying to do our improvements into Winit so that it can benefit the entire Rust GUI ecosystem and not just our project. We also made a decision about 1.5 years ago to switch all of our GPU infrastructure, instead of doing that ourselves, to use WGPU. And I think that decision is really paying off in a big way, because we are able to interop with other applications, and there's really amazing work. You've all seen the Bevy stuff. There's a lot of applications that people are building on top of WGPU. There's AI and machine learning stuff that's using the compute capabilities of WGPU. And this is a real goal of our project, that if you have an app that's doing rich 3D content, we want to be able to mix and match that with the Xylm content in a completely seamless way. And of course, if we had built our own GPU infrastructure, maybe we would be able to optimize, incremental percent on Vulkan a little bit better, but we would be giving up that ability to interoperate with WGPU. We're also working with Nico Burns on Taffy. So we're bringing in Taffy to do the layout. There's a demo. I'm not going to show it. I think I've probably tempted the demo gods enough, but there is a Taffy demo. And and you can play with that. And then we're also, a lot of the crates, so these are crates that are, the ecosystem that we're using, but we're also building a lot of stuff that we think is going to be potentially really useful to other people that are building these 2D apps that are out there. So I think the big one is Velo. The world needs a very high performance GPU 2D rendering engine, and I think Velo is becoming that, and we're starting to see that being adopted by other projects. So the Blitz renderer, which is also known as Stylo Dioxys, it's the native rendering layer in Dioxys. That's using Blitz. We're looking forward to them. We're having conversations. Over lunch, we were talking to people at Servo about maybe using Velo to do some of the content in Servo. And so we really want to make this something that can be used by everybody in the Rust ecosystem, and not just if you're using Xylm as the toolkit. Text layout is in the same category. And I should add, we're aware of the work that's being done in Cosmic Text. That's really good stuff. And we looked at that and decided to go our own direction because we feel that there's certain things that we can do better. And text is also, I'm working on the Google Fonts team. I'm working very closely with engineers on Chrome and other projects inside Google. So, we felt we can do a better job on text. At the same time, a lot of the stuff that we're doing, if you're using Velo, if you want to use Velo with Cosmic Text, we have a demo of that application. That works. We want to support that as well. But we're hoping that this Parley text layout library is something that can be used again across the ecosystem. And then, of course, Access Kit. Everybody needs to do accessibility in their UI toolkit. And I think we've been seeing, when new UI toolkits pop up, it's very common for them, even out of the box, to be including Access Kit, and that's really, really great to see. So today what you're seeing is a snapshot. You're seeing work in progress. A lot of this stuff is still in rough state and being built. So over the next few months, we definitely want to build out more of the widget set, all of the stuff that you expect in a UI toolkit. A lot of that we're going to be importing from Druid. This has sort of roots in the Druid project, and so there's a lot of code there that we think we can adapt pretty quickly. We also want to build that high-performance scrolling list view. That'll allow us to test out a lot of our performance ideas. Are we really able to realize that kind of dramatically stepped-up performance over the current state-of-the-art? And then, of course, we want to make this work really well on mobile, really work well on Android. And so the IME, the soft keyboard, is a major challenge. There are not a lot of things out there that do this well today. That's one of the reasons why you saw the IME demo earlier, is we need to get the interface with the IME smooth so that we can get that working really, really nicely on especially mobile platforms. And there's a lot more to be done on development tools. There's actually Olivier, who's one of the people working on the project, showed me a demo of a widget inspector that he's working on. That's part of if you read his blog from earlier this year on the plans for Masonry, you'll see that the widget inspector and testing and developer tools are a large part of that story. So so this is all stuff that we're working on. And we have a very, I think we've been putting time and effort into making ourselves into a good community. I feel Rust needs, we used to sort of have r/Rust as the gathering place where everybody came together, and I think that we're moving into a world where we're growing past that, where there are sub-communities, and we want to be the sub-community not just for the Xylm project, but for 2D graphics and Rust GUI. And so we have the center of our community is a Zulip instance. And of course, anybody here is welcome to go and sign up or just browse. You can browse it. You don't need an account to read it. So that's the sort of central gathering place for our community. We have a blog we're updating. We have a monthly update we send out every month, and then we have special topics on what we're doing. And then another feature is weekly office hours. So anybody who's in Delft tomorrow at 5 p.m. Dutch time, please come by, and you can see me about the technical details. But we hold office hours every week. We don't we don't post those to like social media and stuff like that because we don't want to be swamped. But if you're interested in building or actively using Rust GUI, you are welcome to come by those office hours, and those are a really great, productive way to engage the community. So that's a goal. Like we don't want to be a closed, a walled garden. We want to be open. We know there's a lot of really excellent work you've seen, yesterday and this morning. Some of the other Rust GUI projects that are being done, and we want everybody to be working together and collaborating towards a future in which we have the advantages of Rust, but we're also building really great UI. So that's my talk.
Thank you, Ralph. Are there questions? Yeah.
Stand up, please.
Hello, thank you for the great talk. It was very interesting. So I maintain a crate called Ratatouille. It's a terminal user interface library for Rust. Mm-hmm. And my question or the idea is, can we use, so you mentioned Xylm core can be used to, in a generic way to like render in the web. Can we do the same for the terminal by using Ratatouille as like a widget provider?
I think so. I know, I can't remember off the top of my head. I think there's been a little bit of exploration of using Xylm core for TUI. I don't think that's a completely new idea, but absolutely. Like, let's explore. Let's find out what works well. Maybe what are some of the pain points. Yep. Let's try it.
Hi, thank you for your talk. Quick question. If I am not mistaken, Skia was working on a backend called Graffiti. I think Graffiti was trying to do something like this. Is there any shared experience since between this project and what Skia is doing?
Yes. So I do work pretty closely with people on Skia. So Graphite is the next generation after Ganesh of Skia's GPU-based rendering. But Graphite's a bigger project. The current state of Graphite, they're not using compute shaders to do the rendering. So it's a step, but it's not a big step in the way that Velo is. So we do have a prototype integration. It's all in very early stages. None of this is anywhere near ready for production right now. But we have a prototype of using the Velo path renderer as one of the backends inside Graphite. So, as this develops, I'm hoping that more of this stuff actually lands in Skia, but at the moment, and that would be through Graphite, but at the moment, this is all kind of early explorations.
Thank you for the talk. So I've been following you and your talks for quite a while now, and the key takeaway of most of the talks is this is all nice stuff, and we are researching a lot of things, and if you're interested, have a look, check it out, but maybe not use it for anything serious. So my question would be, you presented a lot of projects. Has that changed? Are there some that you would say, this is something that you could actually use, or maybe still wait a little bit longer? For instance, Xylm might be very interested in looking deeper into that, but it's always like, maybe not.
It's a good question. Thanks for raising the question. So first of all, there are pieces like, for example, Skrifa, the low-level font loading, is absolutely ready to use in production today. So I think maybe thinking about it as, and I think AccessKit, it's still in progress, but I think taking a dependency on AccessKit today is a really good idea that I would recommend. I wish I could say the same. Like, I think Velo is becoming that. It's not quite there yet, but it's well on the way. I think people are starting to integrate Velo. And then as for the higher levels, yes, this is explicitly a research project, and that's a double-edged sword. That there's a lot to be said for saying, let's just take our knowledge of best practices of how to build stuff and just do the engineering and build a product. And that isn't what I've personally been doing, much. That there's so much interesting research to be done, and I see like there's so much better ways of doing things, and I want to explore that, and that's in tension with, I just want to build a GUI today, and I'm very sympathetic to that. So I think the answer is I want us to be moving towards that. I wish we were farther along on that journey, but I think we are on that journey, and so the invitation, is the same. It's like, join us on that journey. Let's see what we can learn, and also, have our projects cooperating a lot more with other projects that are maybe a little bit more focused on shipping a usable product in a short period of time.
So what are the odds of Xylm becoming the next Druid?
I like to think that, Druid had mistakes in it, and I like to think that Xylm fixes those mistakes and is a more sustainable project. And I think the way that the community has been coming together and building it is a really positive sign that it has legs.
Okay, so Xylm is there to stay.
I hope so.
What you're sincerely hoping. Okay.
I hope so, and I think so.
Thanks.
I would like to thank you for investing in accessibility, first of all, because I think it's very, very necessary. Little people do that, little organizations do that. But your demo also shows that there's a bit lacking in the screen reader department. Is your organization, is Google interested in investing in screen reader department?
I can't speak for what Google is going to invest in. I mean, certainly we are. I mean, the specific thing of it not reading aloud is just demo effect, and I don't know what went wrong there. Like, that does integrate. It absolutely does work, and just not when I'm on stage, I guess. So, I mean, Google obviously does a lot of investment across the board in accessibility technology, in Android, in other products that Google ships. So that is certainly going to continue. And then, we're very happy to support AccessKit. So, like, anything that's rough and not working quite well today, we're absolutely going to be fixing that. And we're very happy to be working with Matt Campbell, who's the real creator of AccessKit.
Someone online is asking how the story with Xylm would work in combination with async. So how would you, for example, make an HTTP request?
Yeah. We just ripped the async out, which is fun. But we had a prototype where we had async integrated fairly deeply. So you have the ability to do waking, which is, of course, the primary point at which async integrates with a UI toolkit, on a per widget basis. So again, this is a prototype that we had working, and then when we were making various different transitions to win it, that was part of the thing that we ended up taking that out. But we are planning on bringing that back. So you absolutely would be able to have a widget that says, send off a network request, and then paint the widget based on the the loading state while you're waiting for the request to come back. And so there's a prototype. I can point people to the code, based on kind of an older version. This is why it's research. It's like we need to figure out the best way for all of these pieces to come together. But it's planned.
I think this is the final question.
Hello, I've also been following your work for some time, and I remember in Druid there was this a bit bizarre layer of integration with the system, like file dialogues and application persistence with window closing. What did you do with that in the new Xylm architecture?
Well, I mean, the platform integration, we've just switched over to WinIt. And that does mean that we've regressed. So there is not a file open dialog in Xylm at the moment. And so we do plan on porting that stuff on top of WinIt. I think there's some really good questions of, do we do that in a way that's specific to Xylm, or do we try and make a more general crate that could be used by other, maybe other things in the Rust UI ecosystem? I think that's a little bit open. Like, the current state is You know, we're trying to get the new infrastructure really functioning and then pull in pieces from the kind of previous Druid incarnation.
Yeah, one such crate was mentioned earlier today. I don't remember the name, but yeah.
Okay, so give a huge hand to Ralph for his talk. Thank you. So we're about to head into the break. The final break before our final two talks. But before we go into the break, we have the raffle for the Book of Mara. So I have here a container with lots of small numbers in it. Jit, if you would come and draw us, I think 10 books we have?
10 books, yes.
Oh. 10 books, yes, yes. Okay, so Ralph is gonna, of Jit's gonna pull out a number and then...
First number is 48.
48. You are the first. So
yes, you can collect it. Yeah, just come on and I'll give you the in a bit. In a bit. Yeah.
Yeah. Okay. So the second number will be.
The second number will be 51. I'll give you this in the meantime.
So the third number will be
9.
9.
51.
The fourth number will be
1.
1. Wow, nice. This random number generator is broken, I think. Maybe.
There you go. Then we got 8.
So this was the fifth or the?
I think so.
Yeah, I'm losing track. Okay.
Then we have 54.
Okay, so that was the sixth? Yeah,
right?
Yeah, I hope so.
Did anybody keep track? 19. Do you have a 19 anywhere? You got 54. There we go.
Yeah.
Then we have 13.
I think we need 2 more, right? Did anyone keep track? I lost time. Okay, well,
nobody did.
Hopefully. Otherwise, I'll buy them a book.
There you go.
Okay, 2 more numbers.
2 more numbers. I'm just going to draw 2 at the same time then.
Sure. Ooh, adventurous.
Exactly. We have 27.
And the final number is?
And the final number is 17.
Woo! Nice. Okay, so that's for the raffle. So Mara will be signing her book in that room over there, and Nico will sign his book in the Chemie building at the back near his stand.
Near the main matter stand, yes.
Yeah, exactly. Yeah. So if you have a book, you can have it signed there. And I think Nico is also giving away some books.
Luca, yeah, Luca.
Yeah, Luca, sorry.
Luca.
Sorry. So yeah, I will see you again at, let's see, 5:50. What time? Or this is correct?
Is that not good?
No.
Okay. Yeah, I think at 50 then. 15:50.
15:50. So have a break and we'll see you then. Thanks.
examples.
Ja.
Binnen examples heb je SP32C en doen. Ik neem aan dat dat is wat ik heb.
Nee, je hebt een ESP32 C3.
Oké, dat is misschien nog
Maar
goed, hoe
nee,
dan
dat
ook,
zit
hè?
in de ESP Hall electronic tempo van de embassy. Dat is een beetje...
Ja, weet je waar je moet kijken.
Ja, oké.
Dus misschien is dat al, ja,
wat
die dependencies allemaal problemen geven.
Ja, nee, je hebt STM32 gepakt, dus dit gaat sowieso weer.
Maar wat is dit dan?
Een ESP32.
Oh,
ESP.
ESP.
ESP is van Espressing. En de C3.
Oké.
Een specifieke chipset. En je kan het als goed is ook zien als je op de chip kijkt, moet je niet kijken.
Oh, nee, dat lukt niet.
Nee, dus dat is het probleem. Ik kan wel...
Ja, oké, dus embassy.
Je hebt waarschijnlijk sowieso geen familie van aanstaan.
Ja, dat heb ik dus aangepast, zodat die RISC 5 staat. Ja, waarom heeft die STM?
Ja, dus de atomics operaties worden dus dan defined in de peripheral access credit, de specifieke credit voor deze chip. Die define hoe atomics werken voor deze chip.
Ja.
En dat jij dus een STM32 cortex.
Ja.
En dan heb je de instructieset heb je veranderd.
Ja.
Dus het zit in de cortex instructieset.
Ja, precies.
En nu heb je een instructieset zonder.
Ik zie nu dat binnen de embassy examples
hier staat C3 mini.
Ja, die had ik wel gezien.
De rest staat aan de buitenkant.
Oké, dus ESP hard, hoe zie ik dat?
ESP zit er al. En dan heb je ook verschillende varianten. Oh nee, ESP al. Niet ESP32, maar ESP al. Ja, en dan heb je hier, als het goed is, examples.
Examples?
Ja, en
we zijn er bijna. Oké.
Ja, dus zij hebben zeg maar moeilijke extra's.
En je hebt
en je hebt ook embassy meeting. En embassy world.
Ja, maar laten we dan een eenvoudigste pakken.
Nee, maar blikje gaat dus niet werken. Dit is geen klassieke LED.
Oké.
Dit is een...
Oké, dan moet ik een Hello World...
Nee, je hebt, als je de LED wil gebruiken...
Ja, maar op zich is een Hello World ook prima. Ik wil gewoon kijken of ik er een programma op kan zetten.
Maar de LED zou misschien, en anders is het... Je hebt ook smart LED.
Laten we even deze kijken. Bla bla bla. Ja. Ah, Hello World.
Hello RGB is
Ja, heb jij hem gemaakt?
Nee.
Oké, SK's X.
Ja, dat werkt het zo.
Oké.
Moet je wel niet even vinden.
Ja. Hij heeft nice. Hij heeft een feature voor ESP32C.
Ja, maar dat is een specifieke pin, dus dat hoeft niet te kloppen. Dit is een specifiek woordje.
Oh.
Maar dat moet je gewoon even kijken.
En die pin zegt van GPIO 8. Dus GPIO 9. Dat staat 9. Toch? Staat ook 9? Dat is, nee, wacht, dat is
Nee, 7 zit 1. Oh, je hebt hier net aan uitgezet.
Ja, gewoon ja, precies. Nou, ik ga dit klonen. Ik werk heel veel bij DSL, maar ik ga het proberen. Ik heb een keer gestandaardiseerd wat ik gemaakt laatst. Ik weet wel wanneer ik
that alone is like so much of what I do is like, not only that, that's hash for each section. If it's an empty file, the whole section, then it will make the marker, like that.
Daarin cargo.
Ja, zij doen wel allemaal enge dingen, dus ze hebben hier alle dependencies instaan van alle examples.
Ja. Nou, maar goed, dan doe ik dit.
Dus stel gewoon eerst
even de juiste feature pakken.
Precies, ja. Er staat squeeze in de readme welke combo. officiële K23 build. Maar het is niet perfect analoog met als je zelf een project zou maken.
Ja.
Die hele stand-up zou werken. Maar dat is niet heel veel hardware.
Nou, dan zou je moeten kijken wat die extra's krijgen.
Ja, precies.
Oké, SP's
ja, packages, dan moet ik nog ESP-hal ervoor zetten. Dus de eerste argument, dat is ESP-hal.
Oh, dat is maar die. Kun je de zin nog in die woonlijn weer?
Ja, dat is altijd mee. For my peripheral vision, it seemed like...
er al heel lang geen leiding meer gebruikt.
Dan heb je vroeger standaard, dan heb je de oude Nightly. Ja, ik pin mensen mijn Nightly op...
ja, wat ik doe is... Ik heb het hier just op je pin. De Rust stable is zo goed geworden.
Ja, ja.
Aan het begin moest je Nightly gebruiken, want je anders niks gedaan kreeg.
Ja.
Als je kijkt, dat is streaming, maar je kent weet je, het probleem met al deze dingen is, er zijn zoveel dingen die verkeerd kunnen gaan.
Ja.
En die haal je niet uit de implementatie. Dus je moet even een soort workshop gepersonaliseerde coaching sessie.
Ja, nee, ze leggen dit soort dingen wel uit hoor. In de toplevel van ESP-hal. Als ik
zo lezen.
Ja. Maar het is inderdaad, de ervaring is niet daarom vaak met cargo template meer. Dat je gewoon kan installeren vanuit een template.
Ja, daarom.
En dan staat meestal Rust toolchain.
TSP Hello World heb ik gedaan.
Ja, maar er staat dus er staat waarschijnlijk een Rust toolchain. En als je een cargo run doet, dan werkt het automatisch.
Ja, want
deze gebruikt wel een HPIDF, dus dit is een andere versie van deze. En de reden is, dus je hebt twee varianten. Je hebt een pure Rust implementatie, dat is HPHAL. En je hebt HPIDF al, en je maakt gebruik van de CL en ook de root operating system. Die door SPX is gemaakt en het heeft met C-bindings.
Maar dat werkt nog steeds.
Dat werkt ook super goed, maar dan ben je niet meer pure Rust bezig met veel thread. Ja, dat is een keus. Dan heb je bijvoorbeeld wel minder gezeur met YouTube.
Oh, dit is ook wat dit is.
Ja. Dat is die.
Wat bijzonder met zijn Twitter is.
Ja, eentje. Ik ga niet over per se.
Ja, maar de naam van deze. Ja, beeld, de zitvlak. Oh, die is.
Je moet zelf hoe je ook beeld.
Oh nee!
Ja, alles moet opnieuw beeld worden.
Ik ben echt verwend door dit. Ik ga nou maar
Ja, nou, dan is het wel computer.
als je dit in programmable node hebt gezet, was niet eens de hele tijd.
Nee, dat was alleen extra staan. Ja, dus dan moeten we wel een beetje keren.
Als ik het een keer al heb geswitcht naar blijft het daarin of moet ik het flash of zo?
Ja. Deze moet je volgens mij even resetten.
Elke keer dat ik hem save. Hij is gebeeld.
Ja.
Nou, kijk of het moet laden. Hoe zou je dat moeten?
Eerst run example. Dus nu hebben we build examples. Dus dat is voor dezelfde stand. Examples. Use serial port 3. Dat weet ik niet wat het is. Maar hij zegt dus op de serial port. Dat weet ik. Wel, dat is dat en hij heeft gewoon een mooie positie. Ja, je kan het ook zien. Als je nu in de positie zit. Works. ESPL. Well, I just got a private lesson. He gave me this yesterday and I was trying to learn.
I think he got some. Yeah, but this is a WS 2822, so it's no longer blinky. It's already smart and advanced.
I'm a bit sad for the ports like only use very old processors because they are low power enough. That is actually a challenge for the students because we want to make them struggle a tiny bit with like how many cycles they're using their program. But basically we can't use any of the features because we have a very old processor.
You could take a microcontroller and maybe put a slower clock on there.
Yes, I've been thinking about that, but we've made so many
yeah, it's definitely out of
just a board.
Remember a course we did like for learning algorithms to have custom assembly and de reden waarom ik dacht dat je serial of zo, dit is een serial port. Serial port aan doen, maar dit is instruction. Dat is hoe dat
Exactly. It matters which instruction you're using.
Wat voor USB-klassen die er aan de hand is, dan dat
Really? No. Well, I'm a teacher for this purpose. Yes.
That was the most fun course I
That's what I thought when I took it. Well, we're still doing it. Just so you know. So this is our growth line. So on one side, which is very fun. And I just did it last so 3 weeks ago. This year session. Yes, we're using Rust for everything. But it's so cool that you did that. You get to go home. Well, that's how I got it, right? Like because in the year that I did it, we were testing Watchful in Rust. So I did the one group in Rust, and then I was teaching the system. So this year, during Xylm from group, this happened. This is our ceiling, and this is the drone afterwards, without all the propellers.
Drone using his propellers.
They're a bit more smooth drones.
Are they? So you still did it on the FPGA stuff? Or the software? Yes. So we switched to software only. Yes. I see. No, we switched to all software because it would be so fast enough for that. But the Bristol was working at like 16 megahertz. Slow enough. So for example, we can't use MSC because it's just too old. I want to use MSC for this because it's so cool. We also have other you can if you want.
All right. We're going to be starting in a bit again. Please hurry inside. Nah. We're at the last block of talks.
Yes, the last two of today and of this conference.
What? Already?
Already, yeah. 2 quick days.
2 very quick days. Did y'all have fun? Yeah. Good.
I really enjoyed the talks up until now. We still have 2 talks. So,
We still have 2 talks, yes.
The judge is still out.
2 amazing talks. We are definitely not stalling for time.
Let's wait 1 minute.
See, some people got their books from Mara. I think Luca was out of books too, so that's great.
Yeah. I hope I didn't give away too many books.
No.
30 seconds.
30 seconds. Still people coming in. Please come in, take a seat.
We're almost starting, so please take a seat. Okay, let's continue.
Right, I don't have any flashcards, so.
Oh yeah, so
take it away.
So after this last break, we have to again thank our sponsors. So shout out to the Dutch Rust community and our ecosystem supporters, which are Infineon, Ferris Systems, Roxys, Jitter, Polars, and NLNet Labs.
Which is where I work.
Yeah. So give a huge round of applause for these sponsors. So to kick off the 2 final talks of this conference and of today, we have another person working at Achilles. I shouldn't say Achilles, right? Achilles, that's correct? Yeah. He has worked also on Embassy and I think also at Nordic Semiconductor, if my memory serves. And he's going to talk about a really cool embedded project, I believe. So a big hand of applause to Ulf.
Hello, everyone. So my name is Ulf. I work for Achilles. And clearly, I have too much spare time. My background is primarily in backend systems, and I spent, 14 years in industry, mostly doing that. But I did a short turn doing embedded C for a very short while. And I stopped liking embedded systems. But then I got the opportunity 3 or 4 years ago to do Rust embedded full-time again. And I kind of refound my love for it. Pretty grateful for the existence of Rust, yeah. What I'm going to talk about today is, however, not work-related. I've been poisoning my arm or wrist with Rust. And I'm probably not the first one to do this or the last one. But with this talk, I kind of hope to inspire people to have fun, play with new things, and see where it goes. So I made an open source project for running Rust with Embassy and firmware updates and so on my smartwatch. And sorry, this project is called Watchful because I like anagrams, using my own name and so on. But let's talk a bit about the hardware first. So the watch I'm using is a Pine Time. It has one of those small or medium-sized MCUs that Dario mentioned earlier. It has a Bluetooth radio. It has a touch display and a touch sensor, some heart rate sensor, and some extra storage. So that's not great specs for a smartwatch, but the big upside of this hardware is that it's hackable, or you can play with it. You can buy a development kit from their store, and you can use a standard debug probe to program it, which, you know, it's a lot of fun. Obviously, we can't wear this one, so to actually run Rust on this one, which is sealed, there's some additional tricks involved, which we'll see. Comes with some software, some C-based software. And as I said earlier, my experience with embedded C isn't that great. And I kind of, coming back to Rust Embedded, I kind of realized that there's a lot of talk about needing an RTOS in C. And I think one of the reasons for that is that you need libraries. You don't want to have to write drivers for everything. You need a dependency manager and so on. And in the C world, this is largely part of the RTOS you're using. But for Rust, it's done the right way. And I really mean that, because developing an embedded Rust application is very similar to just developing a regular application, but there's just some stuff you can't use in the language, and that's fine. But the tooling and everything is just amazing. So what do I want for my smartwatch firmware? I need to display the time. Of course, you kind of forget that the purpose of a watch is to keep track of time these days. But I also lose my phone all the time and really like to find it again. I want to display my heart rate in case I'm working out, you know, bragging a bit there. Basically, if you used an Apple Watch and any other Garmin or Polar, they have a lot of features, but I don't really need all of that. So the hope is to have a decent battery usage. And also, since I don't want to, you know, crack it open and put the debug probe on and flash it and then glue it back together every time I want to program it, I need to have firmware updates over Bluetooth. But first, it's important to start with the, let's say, something that you can see, something that you can brag about to your friends, and that's the visuals. So it's been really interesting to hear about all of these UI toolkits at the conference. In my case, I've been using something called embedded graphics. It's a really stripped down crate that allows you to do basic 2D graphics. It integrates a lot with this embedded ecosystem traits for using SPI to draw graphics, and you have drivers in the crates.io for display and the touch sensor already. This is another example of how Rust has done this right, because I can just depend on a crate, on crates.io, pull it in and use it, reuse it. Reusable, composable, it's just great. There's also a simulator, so you can actually test the UI on your on your PC before you actually deploy it to your watch. And this is basically how this is the limit of my design skills. Like this is how pretty I can make things. The next step I went to was to start on the connectivity, to be able to send firmware updates and synchronize the time on the watch itself. And I really wanted to do this early because I was a bit familiar with it, but I also wanted it to work really well and reliably. So it got a lot of testing during the development process. And this, using Bluetooth in Rust is pretty great. So Dario made a lot of effort there with the NRF support, with the embassy, but also the integration with the Bluetooth stack that you find from the vendor. But to meet my requirements, I wanted to have firmware updates. So I implemented Nordic's firmware update service so that I could reuse my phone to update the software. So that's, made it in Rust, published a crate, others can reuse it. More composability, all right? To synchronize time, you actually have a standard Bluetooth service for that the phone supports, so you can actually implement a client on the watch that talks to the phone and asks it what's the current time. So, yeah. Last step, storage. It has external flash, and to use that, it's really easy. We can use embedded HAL to talk to any SPI peripheral, and then you can expose an API using the embedded storage trait. And that's really not a lot of code. You just implement these two interfaces, and then you have a generic reusable driver. Firmware updates. Embassy has a bootloader that supports A/B switching between the firmware, so I can have the one that's currently running, and I can have the one that's going to be updated in a separate partition, which the bootloader can be instructed to swap. So it's a really simple piece of software, but it's pretty critical. So, the great switcheroo. How do I convert from the existing software to the Rust-based one? Because basically you need to go from this layout in the flash storage to that one. And that's wildly different. You need to kind of rewrite your entire program. And this is the solution. Basically, I wrote a reloader app which contains the new Bluetooth stack, the new bootloader, the new application, writes the Bluetooth stack to the flash, writes the bootloader to flash, writes the application to the external flash, and finally it instructs the bootloader to swap your new application in. And how many, show of hands, how many think that it's worked on the first try? Come on. Yeah. Because it did. And actually, a lot of credits goes to everyone who is working in the Rust ecosystem, creating these crates. That I believe that a lot of the reason why this was, maybe I was just lucky, but a lot of people wrote software that's using Rust, but because of that, it catches a lot of these edge cases. But I did have one bug, and then I didn't actually discover it until 2 weeks later when I did a firmware update that was failing, and it rolled back, and I found a bug in the rollback process. So yeah. So I had to crack it open, and so on. But the good news is that this smartwatch costs, I don't know, at the time it was like 30 euros or something. So that's kind of cheaper than a lot of other smartwatches, so I got a new one. after fixing the bug, of course. So what can I say about this? Like getting the display working, getting the storage working, the connectivity and stuff like that. That's kind of a solved problem. The only real time I had to spend that was critical was this testing, upgrade and downgrade path. But it kind of doing this kind of project renews your appreciation of crates.io and the Rust ecosystem, because you have so much great software out there. And also, you know, the tool set of building with Cargo is great, but also ProbeRS, which, like, if you compare it to what was there 5-10 years ago, it's just so super easy to use. And just like you're just running this application on your microcontroller, but it feels like you're just debugging a regular program on your computer. I have a wish list for Rust. Like, there's a few nuances, a few annoying things. Like, if you have an embedded project, you usually have some parts that are common that you want to unit test in the SDD environment, but then you have your other thing that's specific to a particular target, and it's a bit it could be more native, a more native feel to it. Also, there's a very big desire to put a lot of projects in the same repo because it's easier to maintain that way. I wish there was. I don't have a solution. I'm just complaining, but like if there was a way to. I don't know, like keep dependencies in sync across Git repositories more easily. And also, when making new Rust features, take embedded into account, because it's like a complete game changer in my mind on how embedded development is done. And I'm 100% certain that a lot of companies will be looking at that in the future. So. Check out my real-time operating system called Watchful, or just a collection of libraries, really. And then there's the Embassy project, ProbeRS. Embedded Rust has done a fantastic job on defining the APIs that you can use to create reusable code. If you're interested in Bluetooth, talk to me. We're doing some interesting work there on creating a Rust-native Bluetooth host. And that's my talk.
All right, thanks, Ulf. Are there any questions? There you go.
Hi, so I was wondering, I'm assuming the watch charges to USB. Can't you just do the firmware update and debugging over USB, or does the chip not support that?
Well, I don't think this one has USB peripheral, actually. The NRF, it's one of the more stripped down NRF52s, but also there's no USB connector on it. So.
Thanks for the nice talk. You said at the beginning one of your goals was to have a week of uptime and some other things. Did you reach all of your goals?
Good question. No, it's not nearly done. You know, you think it's going to be a quick thing, and it ends up like a multi-year thing. But well, I think the battery can last maybe 2 days at the moment, but I haven't. That's without doing any kind of power profiling and stuff like that. So that's better than an Apple Watch. So I'm pretty happy with that.
All right, where's more questions? Over there.
So I was wondering about the NRF soft device integration, whether you had any challenges with that. So for instance, the TOC operating system is looking into using the NRF soft device, but apparently it makes some assumptions about other parts of the software stack on those chips. So
yeah, that's a good question. So as you saw, I had to go a bit briefly through it, but the soft device is very particular about where it can be placed in RAM. The good, or sort of good news, is that Nordic has a new soft device, if you will, that implements just the controller part in Bluetooth that you can embed as a library in your application. The problem is that now you have to write your own Bluetooth host. And this is the reason why I mentioned this Trouble project, which we're working on at Achilles to use in our products, because we also felt the pain of that, right? So please, if you're interested in that, let's talk later.
All right. Any other questions? I'm looking for hands. Here's one more hand.
Have you looked into what it takes to root any higher spec watches? Like, what's the fanciest watch that you could probably get this stuff into?
I don't have a good overview of what's out there. I found one that's in the same category of hackable that has a GPS. And that's, if there were one thing I was missing from the hardware, it would be a GPS. So I don't remember exactly the name of that, but yeah, need to Google it.
All right, do we have time for more questions? Looking at timekeepers, one more. Over there.
Thank you. Would it be possible to use the existing bootloader on the watch in some way?
The existing bootloader that was on the watch? Yeah. Ideally, that would be great. Like, it has an MCU bootloader that could have worked if it hadn't been for the soft device that actually has to be placed there. But with the new stack, well, I could have potentially, like with a Trouble and a new soft device, which can be embedded as a library, I could have potentially reused it. So if I started the project now, well, it goes for a nice talk, so I don't regret it.
All right, and with that, please give it up for Ulf. All right, then I'm going to announce the final speaker of this conference, the final speaker of this two-day Rust extravaganza, basically. He has not only worked with Rust, but worked on Rust since 2011. He's led the design of the current and future borrow checker, I believe. He's helped launch the Rust Foundation, and he was previously a member of the Rust core team. Are you all set up? Are you ready?
I will be soon.
Will be soon, yeah.
You can keep saying cool things.
Yeah,
about me.
Well, I have here, you're also the co-lead of the open source Rust language design team. Is that still correct?
That's true.
That's all true. Well, that's where my card ends, but he is an absolute legend, I can tell you that.
Oh, man.
All right.
All right.
Looks like you're all set up. Is the block big enough there?
Nah, it'll do.
It'll do. Please give it up for Nico.
Thank you. All right. So, oh, thank you. Yeah, I'm scared to have that up here, so I'm going to put it down here. I can be a little clumsy. So I'm going to talk about type theory for busy engineers. So normally, I give, at least lately, I feel like I'm giving talks about Rust roadmap and Rust features and things like that. And I decided to do something a little bit different. So yeah, who am I? Well, as I guess a legend, I was kind of going to make me feel a little blushy right now. But yeah, I work on the Rust type system and on the Rust language, and I've been doing that a long time. And one of the things I've noticed along the way is, at first when we were building out and designing aspects of Rust, we would do like little models. So we would say, okay, we want to think about how the type system should work. I'm going to figure out, just think about this part in isolation, and that can get you really, really far, right? And then we would think about a different part. And so we would draft, make a model, a sort of some subset of Rust that's relevant, and just think about that part. But we've gotten to the point now where actually it's becoming kind of hard to keep the whole thing in your head, and we have unexpected interactions, or little problems that arise. And so I've gotten interested in how can we make a better model that will help us understand and extend Rust going forward, and think about the new things that Rust should do, right? So the goal is to make something that lets you kind of play with the type system and experiment with it in prototype, not to build a shippable compiler, but to help you understand Rust as it is today and where it might go. And along the way, so that's what the goal of this project is, right? Mere formality. I was told I need to explain this for non-native Rust speakers. So there's an expression we say, oh, that's just a mere formality. Like it's a tiny little detail that you can get past. And in this case, mere is also the mid-level IR, the middle IR of the compiler. So that was the pun of this project. But the goal is to basically model in a formal-ish way how the type checker works, especially for the mid-level IR. So not really all the way to Rust surface syntax yet. But I'm not actually going to talk about mere formality here right now. What I'm going to talk about is a subset of it that I call formality core, mostly because formality was already taken on crates.io. I don't remember by whom. I should find them out. But, but it's like a reusable part of it that you could use to model your own type systems if you were designing a language. Like some people we saw today, like the really cool June language and so forth, maybe it might be useful to them. I don't know. I found it fun for my own experiments. It's heavily inspired by a tool I used called PLT-Redx, which is this other programming language called Racket. And it's basically the same thing. It's like a lightweight tool for playing with type system definitions and letting you kind of use the notation that you might have read in an academic paper and put it into your computer and run it and play with it. Now, I just said that you might have read in an academic paper, but what I've noticed is, shockingly, not that many people have actually read academic papers. They're kind of not designed for easy entry and understanding. And so what I thought I would do today is talk about how I think about it and how formality core, like use formality core and kind of to walk through a very simple type system and give you a feeling for what it looks like. And true fact, I have not done a dry run of this talk. I have no idea how long it's going to take. So either we're going to go way over or way under, and we'll take a bunch of questions. We're going to figure it out. It's going to be fun. But part of this is, I didn't really learn. I never really took a course on type systems, actually. I just kind of read things, and eventually it sort of made sense. So I'm going to be telling you kind of my way of thinking about it. Probably some people who've actually studied this kind of thing will have their own opinions, but right. So the way I think about formality core, anyway, is that I guess if you've written parallel systems before, like in Java, actually I'm going to tell you an anecdote because it's funny. One of the first courses that was taught in Rust was a systems programming course at Northeastern, and they went through and they taught the students Rust, and they got up to concurrency, and then they had a problem because they wanted to teach them about data races, but they couldn't produce them. So they said, okay, we're going to stop, and we're going to teach you Java, and then you're going to learn Java. Now look at this horrible bug. Okay, let's go back to Rust. Now you don't have this bug. Okay, good. So Rust kind of made... That is a true story. But Rust made concurrency this thing, at least my experience of it, is, yeah, I can still have bugs, but it's kind of like I plug it together and I can think about it and experiment with it. And if it kind of works, it usually works all the way up. If it works for simple stuff, it works also for many complicated cases. Formality core has the same feeling. I want to bring that same feeling, but to experimenting with type systems. So here's the language we're going to walk through, called EG. And it does well, it's kind of a calculator, fancy calculator. So like this program, shockingly, prints 66 when you run it. I know. But it does some more stuff. You can have tuples, and they will be added up pairwise. You can define little functions, like so. And you can call them with this weird @ sign, which is because of a limitation I'll explain later. And you can even have generics. Right? So all of these are actually runnable examples in formality, or in the program. And part of what I'm going to do today is kind of show you the actual program. Oh wait, someone earlier did this. I forget who. I think it was the first talk. Let's start with a cargo clean, just cause. So when you build something in this, it really is just a Rust program that you can work with. Let's see, source, or where did I put the tests? Under source, test, talk examples. Right, so like for example, here's that first one. Hopefully you can read it. Executing 22 plus 44 gives me 66, and so on, right? Okay, so how do we define a programming language in a more formal way? Oh, what am I doing here? Oh, I'm just showing you that what I am not modeling in this definition is type inference. So you can have generics, but you do have to specify their values explicitly. That makes things a lot easier, actually. So how do we define a program more formally? It starts out with something called a grammar. How many of you have heard of grammars? Okay, good. I figured I wouldn't have to explain it too much. But basically, that defines the syntax. Right, so you might write something like, oh, a program in EG is a series of function definitions, 0 or more, followed by some expression that's going to compute the value. Well, in formality core, we're going to define that, but we're going to do it with a Rust structure. So we might have, let's see what I have here. Yeah. So we might have this struct saying this is what a program is, and you can see it has fields, and you put an annotation on it called term. And that's a kind of bit of PL programming language jargon. A term is basically just a thing, something that you're a part of your program or a value or something we're going to talk about, essentially. We need a word for thing, so term is it. And in here, you put the grammar, right? So the $, that will tell you, oh, I'm going to parse the value of this field here in the input. And if you have a little star, that says take 0 or more things, collect them, and put them in a vector. Right, so this would be 0 or more function definitions. Of course, it's using traits and everything under the hood to drive the execution. And this would just parse a single expression. Okay, so that's a pretty simple grammar. Sometimes you have grammars that are a little more complicated, like the expression could be an integer, or it could be an identifier indicating a variable, or a bunch of expressions in a tuple. So when you have a choice of many different options, we'll model that with an enum. And we're going to say, OK, we're going to put the term annotation on the enum. And then for each of the variants, we're going to give the grammar. So these are the different choices. If it's an integer, it should just look like an integer. OK. And when it's an anonymous field, I just call it V0, V1, and so on. So here, one little handy macro is this ID macro. That just declares a string, an identifier. So we're saying, OK, there's going to be an identifier type that I call ID, and I'm going to parse, if I see an identifier, that's a var. OK. And here you see a little bit of handy notation. You can say $ with parentheses. That means a parenthesized list. So I've tried to put in like the common conventions you'll often find. And so we're going to parse one or more expressions and build a tuple. Then we'll continue. Maybe we want to have plus, minus, times, and star. We can do that. That's just some more variants, nothing complicated. The only thing is I can add these precedence annotations to kind of guide the parser. So we're doing this declaration on our structs and basically telling formality core to generate, it's going to auto-generate a parser and everything else using these grammar annotations. Right? One minor point is if you have recursive types, it's still Rust. They have to have arc, otherwise the type would have infinite size. That's no problem, and so on. And sometimes the grammars can be a little non-obvious, like let. So here we're declaring a local variable. It's going to be called ID or whatever. It's going to have an initial value. It's going to execute an expression. That's going to look like this, right? So I have the ID and the arc and so on. OK, you get the idea. So let's look at an example. Now, we wanted to write some tests, right? Because the whole idea of this is you can write this grammar and then play with it. Let me see where I have some tests. Okay, here we go. So here's one where one of the things I can do is test my parser. So for example, I can take this, let me explain this now. So e.g. lang, I'll come to that in a second, but basically I have to declare my language somewhere. It just gives it a name, and it makes a crate with a couple of boilerplate things. But one of the things it gives you is this function term, which will parse a string and give you back a data structure, right? So here I'm saying, parse me an expression from this thing. And so E is some expression, which then we can run a test. And actually we use the grammar to kind of help guide not just the parsing, but the debug impls and so on. So if, for example, we just write E : question mark, that's the normal debug impl, you get something that's generated with the grammar in mind, right? A kind of pretty printed version of it. But if you ask for the full detail with the hash sign, then you actually get, the standard thing you get from a debug impl. This is pretty useful when you're writing tests of the parsing, because it gives you all the detail. And as some people who've played with my systems before will tell you, or when we didn't have this, it's kind of helpful when you're learning if you really want to know exactly what data structure you've got. In this case, in particular, we can see that the multiplication had higher precedence, right? We parsed x plus y times 3 plus 66. If we did that wrong, we might have, for example, parentheses like this. We might have a plus that was getting multiplied rather than an addition of a sum, but we don't. We have the multiplication inside and then the adds. Okay, cool. That's all just parsing, and it's not a particularly smart parser. Oh, I already showed you this. But you have to declare the language. Okay, this is boring. Well, one thing I'll note is you tell it what you want to have as keywords. But let's do, okay, boring. Let's talk about type checking. This is where it gets a little more interesting. So far we allowed you to define data structures and specify their grammar, and you kind of get for free a parser that will parse and give you what's called an abstract syntax tree, which is just an instance of those data structures, right? A way to view your program as a data structure and not as a string. But now we want to do type checking. And the type checking rules for this e.g. language are pretty simple. You can add, if you're adding things, they basically have to have the same type. So I can add 2 integers, I can add 2 tuples that are both 2 integers, but I can't add a tuple and an integer or 2 tuples of different arities. That should not work. So that gives us a question, though. What are types in this language? Right? The next thing we have to define, we defined what the program language is, but we didn't define the grammar of types. So the next thing you have to do is define that. We're going to have it basically be, I'm starting with the simple. I'm excluding generics for the moment. It's an integer, or it's a tuple of some set of other types, right? So that's just an enum with 2 variants. One is an integer, one is a tuple, okay? And now we're going to get to this inference rule stuff. How many of you have seen something like this? Okay, how many of you understood what the hell is, what is going on here? Yeah, me either. Yeah, okay. So this notation is actually ridiculously simple. It's like the world's, how many of you have written in Tickle? Okay, that was more than I thought. I have not written in Tickle, but what I do know about Tickle is that everything is a string. Well, this is kind of true here also, right? The way programming languages work, basically, or these rules work, it's like you took the world's simplest interpreter and you run it, and it has to be simple because we have to be able to map it to like mathematics. So it has to be very, very simple so that mapping is very, very simple so that we can formally prove things about it. But I'm going to kind of walk through it. The very first confusing thing about inference rules, in my opinion, is their name, which is like, what is that? What is inference? I don't know. I think of type inference. It's not really about that. It's about this English word infer, right? It's basically a rule that says, like, if I infer something, it means I figured it out based on something else, right? Well, an inference rule is basically how can we figure out a conclusion based on a set of premises. If these things are true, in other words, you can kind of read them as, if you see a big rule that has a big line, The stuff on top of the line, that's the conditions. If X and Y, then Z, right? This is the conclusion. And then there's this thing over in the side, that's just the name. That's just so you can refer to it. So like here, these are the two conditions on top, and that's the conclusion. Okay. Sometimes there's no conditions, and then we just write up a line. But it's a pretty handy notation, even though it's so simple. So here's an example of one of the inference rules you might write in EG, which is somewhat simpler. What is this saying, though? What is going on here? So we've got this kind of, even in this very simple example, we've kind of got this crazy notation. What's happening there, when you see a string like this is also a term. It basically has two different parts to it, right? Overall, this is basically a predicate. It's something that we can say is true or not true, or at least true or not known to be true. And inside of it, there are variables. So here, the t, that's a variable saying some type. I'm going to call it t. Oops. And actually, you could call them meta variables very properly, but let's just call them variables. Basically, when you have these letters, usually, that's kind of the variables. So t is some type. Maybe it's U32, maybe it's parenthesis U32, U32. Gamma, by convention, I put it in here because I'm Greek, but I personally prefer to use the letter E because I actually speak English as a primary language. But gamma is usually used to mean the typing environment. It's basically the types of all the variables that have been declared, though it could have other stuff in it. In Rust, it might have lifetime relationships and so forth. It's kind of just a convention, right? So effectively, it's just a list of variable names and types for those variables. So we can actually define gamma, like everything else, when we're doing an informality, we have to kind of define this stuff with Rust data structures. So here I'm not using the term macro just because I never need to parse it. But the so-called environment is basically just a list of variables that are in scope and their type. And I'm just using a map. You know, it's a B-tree map, actually, but goes from one to the other. I'm also carrying the program along with me. That's so I can look up function definitions when you call them. We won't use that right now. But so that's what we're going to call, when you see gamma, we're going to basically just think it means some environment, right? Okay. And this notation we saw, gamma parenthesis x, well, you could think of gamma like a function you can call to get the type of a variable. So we'll do that by accessing the map. So what about the other stuff? We saw these variables. What about this weird thing? That's called a turnstile. Why? Because, you know, when you walk in the subway, the little thing turns. That's why. That's a turnstile, the thing that turns. And this colon, the answer is this is just stuff. It doesn't have any meaning. It's like opaque strings, like a name of a function. Effectively, the name of this predicate, if you want to, is like gamma colon. So it's kind of like Objective-C, if you did that, or Swift. I don't know how Swift works exactly, but in Objective-C, the name of a method is kind of strung out across, interspersed. So the name of this method, insert object, is actually, it's actually insert object at index, like one big string, even though you write it in parts. So here you could say the name of this rule is gamma colon, which is kind of hard to say out loud. Sounds awkward. So maybe we can give it a better name. We'll see, we will in a second. There are some conventions. So I said they're just random stuff. That's how I think of it. Like, you just have to accept it. It's just this is what they chose to use. But there are some common conventions people often use. Like, the turnstile separates assumptions, your environment, the things that you got from the outside, from the thing you're trying to prove with those assumptions. Like, if I know that the variable x is a U32, then I know that a reference to x has type U32. That's based on this assumption. And colon usually means has type. Okay. So you could kind of read this as assuming gamma, then E has the type T. And what I would say is this was actually like a turning point for me, personally. When I realized that this weird symbol basically meant assuming, or lets me say, that's how I thought of it at first, I remember. Lets us say, like this lets us say that. But I was like, oh, I can read this now. It reads like English instead of this weird string of symbols. So just knowing what people mean by it is usually very impactful, I would say. But how will we write that in formality? We're just going to write it like a Rust function. So we have to give it a name. I'm going to call it type expression because it computes the type for an expression, like the type of an expression. And then we're going to put, for each of the variables, they're going to show up as variables, right? But you'll notice that some of them, the first two, show up as parameters to this function, and the last one, the type that comes after the colon, that's actually the return value. So that's a bit of a less abstract. Normally, when you define the rules, there's not really a notion of input and output. It's just like a relationship between these things. Like, if you have this variable, it has that type, and you can kind of run it in both ways. But when we're really going to execute it in real life, we have to think about what's the input and what gets computed from the input. Otherwise, it's not like a function, executable function. So usually, so I just kind of bake that in, right? And so what this is saying is, given an environment and an expression, we should be able to figure out what the type of that expression is. And that's actually a property, right? We're not going to like guess it. We're going to have to, it has to be something deterministic. But okay, so here's how we're actually going to write it. We're going to write judgment function. And what this is it's a crazy, wicked macro that I'm going to show you later. And then we're going to start with what looks like a fairly normal Rust function, except for this part here, where I have 2 arrows instead of 1 arrow. And that's because what we're going to do when you write this typing, it's possible that actually we're going to write a series of rules that we can use, like the rule we saw. And it's possible that more than one of them applies, right? It's also possible that 0 apply. So in some sense, we're computing all the possible types for this expression. And if there are no possible types, then it's not a well-typed expression. It's invalid. But if there's more than one, well, that might be okay. Sometimes there's many ways to draw a conclusion. Any one of them is valid. Sort of like A or B, right? It's true if A is true, it's true if B is true, and it's true if they're both true. It's fine. And this is how the rules are going to look. So this is the equivalent. This is the math up here. What did I do? Okay. Got me nervous. I was like, is there some horrible bug? Probably there is. Anyway, this is how the rules are going to look. There's going to be parentheses, and then this line, and then sort of the conclusion down here, and the premises above, right? So we're saying, if you ask me to type an expression, and the environment, let's call it end. This is just Rust pattern matching, so end. And the expression is a variable, the name of which will be called x. Then I can compute the type by running this steps on top. Like I'm going to ask the environment to look up the variable x. You see that I put the question mark? That's because actually this, the way it's defined, can return a result. So this is the definition of that function. It's just a method defined in Rust on the environment. And it returns something which is fallible. What is fallible? Well, that's my cute nickname for anyhow result. So it just returns a thing that may succeed or not, right? And so question mark just says, well, if this returns okay, then the rule applies. If it returns error, the rule doesn't apply. But we track the error value for giving you better error messages later, because we're going to want to tell you why the type rule failed. And we would like to use this error message when we do so. And if that succeeds, then we know the type of x, and that becomes the final result. Right? So this is one way to compute the type of an expression in the case that it's a variable. There might be other ways. There aren't in this case, but there could be. Okay, so let me show you that just to prove I'm not lying. How do I use my editor? Let's see. Where did I do this? So this is the actual project, e.g. main. I have no idea where the code is, so I just have to read it. But now you can kind of see what the main, oh, I should show you this. Oops. So yeah, so this is a Rust program. I can run it. I don't even remember what arguments it takes. Let's see. No. Right. So I can use it to execute expressions. Oh. I wish this annoys me all the time. Okay. I can use it to do mistyped expressions, and then I'm going to get an error message, which looks pretty crazy, but actually it's telling you exactly what's going on. I'll explain it in a second. But basically it's saying, hey, I tried to compute the type of this expression in this environment, and I wasn't able to do so. Why? This is handy. Because this rule, there's a rule, so I'm jumping in here, a rule for typing additions, and it did not apply. It almost applied, but it didn't. And why didn't it? Well, because there was another rule that was for typing binary expressions. Don't ignore that for a second. Let's jump down. And eventually I was supposed to compute the left and the right. They were supposed to be equal, but they weren't, so I got it false. So this is kind of telling you, I tried to prove it with the rules you had. I haven't shown you all these rules. I'm kind of jumping out of order, but it's okay. And where I hit dead ends, I'm going to propagate it back up so that you can see why these rules didn't apply. But ultimately, the rules didn't apply. This is not a valid program. Right? And here now you can actually see the 10 minutes. Okay. You can actually see the real code. So type expr, just like I said. And it's a macro here, and here's some rules. Let's scroll down. Where was the rule I just gave? This is the rule for variables. Right? And we have other rules, like the rule for lets, which I'm about to tell you about right now. So this is the rule for lets. It's a little more complicated. It's kind of interesting. What does it say? Well, when we're going to type an expression, it starts from this environment. If it's a let expression with a variable and an initializer and a body, then what are we going to do? We're going to recursively type the initializer. So we're going to compute what was the type of the initializer and store it in this variable var_ty. And you'll note that this uses this right-hand arrow. So that's basically applying the judgment again. It's saying, let me type this expression. And remember I said it may have more than one possible type. So when you use that arrow, that's kind of saying, pick some type, right? It doesn't matter which one. If there's more than one, just take one of them, whichever one you like, and as long as it's valid for one of them. And then we're going to create a new environment, right? And so I'm going to call this function with program variable on the variable env, and I'm going to make a new variable called env. So here I'm leveraging Rust's ability to shadow. This is probably horrific if you're used to formal stuff, but it's very, very convenient, because it basically lets us say, for everything from this row down, I mean this modified environment, which has more variables than the original one, because I just brought the new variable into scope, right? And then I can, so when I do this last thing where I type the body, where I had let a equals b, or let a equals some expression, I'm going to type that other expression, then I'll use this modified environment. So I have the new variable in scope. So, and that'll give me the result. Okay, let me run that just for fun. So here's an example like this, right? If I say, let x is 22, so this works, of course, but what's happening? Here's the rule. So in this rule, the variable var is going to be x. The initializer is 22. And then the body is 44 plus x, right? So we're going to type the initializer, that is 22, and we're going to get back this u32. That's the type. Then we're going to make a new environment. Before we had an empty environment because there were no variables at all. So that's going to become, what is this crazy thing? No. That's going to become like basically just oops, saying, hey, we now have a variable called x that has type u32. And if you look at the definition of this function, all it does is insert something into the map. Very simple. And then we're going to retype this expression in this modified environment. Right? But now when we type 44 plus x, when we go to look up the type of x, we'll get that it's an integer. So, okay. So typing binary operators, this is kind of interesting. It's actually a little different in the source code, but this is the basic idea. It's sort of simplified. I'm going to type the left and the right-hand side. They're both going to give me a type, lty and rty, and then I'm going to check if they're equal. So this is a little bit less elegant. If you were to write this mathematically in a more formal notation, you'd usually write it like this, where you just use the same t everywhere, and that implicitly means it must be the same type in all three places. But because of the shadowing and other things that Rust does, you have to write it like this, where you give two different names and then assert that they're equal, but it still works. Okay. So I've been doing demos throughout, but that's okay. What I'm going to do, how much time do I got left? Okay, a few more minutes, cool. I'm going to show you one other thing, which is, maybe you know about this and maybe you don't, but one of the things I really like is that all of this is just Rust code, right? And so what that means is, you know, I can write a test, like test that 1 plus 2 as a tuple should not be addable to an integer, and then I can run this test, right? And it's just a Rust analyzer test, so it just works. Oh, hey, it passed, but maybe, let's suppose I'm going to modify the test now. So now the test is going to succeed, meaning this is well typed, but I've told it that I should assert, I had this handy utility function that says, when you give me back a result, it should be an error, right? So of course this is not going to pass now. This is sort of simulating the experience. Well, let me do a better way. Let's suppose I went in and modified my rules. I would start to get the, like, where did I have this if eltai? Yeah, here. If I just take this if out, now I'm saying I can now type it. I don't actually care if it equals the type I expected it to equal. I'm not actually testing for that. So of course when I run this, I'm going to get a test failure, right? So this lets me do, I also get a bunch of warnings, which is cool, but this is sort of the same way you develop any other code, right? You have your tests, you run your tests, you check that, oh, I made some changes to the type system. Does it still behave the way I expected it to on all my examples? Oh, good. And we also make use of this expect. I don't know if you've all have seen expect, but it's a Rust analyzer supplied crate that lets you have kind of what was the result you expected. And so here you can see I'm saying, I actually expect this to fail, not just fail, but fail in this particular way, right? That the type did not equal the expected type. And then I can go in and tell the IDE using Rust analyzer run. However I do that. No, how do I do it? Okay, well, it's not working for some reason. I think because I'm not in the right place, but there's a way to run it if this was not just a markdown, but also if this project was working, that would automatically update this with whatever the correct output is, right? Because this is a pain in the ass to type it in. But you can have Rust Analyzer fill it in for you. Super useful. Or you can even just do this. Cargo test dash update expect is one. Now, of course, I'm encoding this bug directly into my test, which I really shouldn't do. But you can see that it updated to the new output. So what this new output actually says, this leads me into my final point, I guess. It's still getting an error. Why is that? It's getting an error because I also wrote an interpreter, and the interpreter is now executing, right? Before the type, so if you look at what happens when you run a given test, it first, here we go. It first tries to check the program. If that check succeeds, it will actually run the program. So before it was failing here because the type check was failing. But now the type check is succeeding because I broke the type checker. And so it's running the program. But the program is getting an error because it doesn't know how to add tuples and integers, right? So why is that cool? That's cool because although I haven't written it yet, and I wanted to, I was hoping to demo it for you, but I didn't do it yet. What we can do is we can start applying fuzz testing and other techniques. Right? We can say, hey, the purpose of my type checker is to guarantee that my interpreter will never fail in this way. It should never be possible to type check a program and then have it try to add tuples and integers because that should fail the type check. So I can ask the fuzzer to go and try to show that that's true. Generate random programs for me. And it's not just going to be like random strings, right? It actually is going to be generating random instances of my Rust programs, my Rust structures, so they're like well-formed programs. And we can see, will we ever find an example that causes the runtime to fail even though it passed the type check? And that doesn't give us, if we can't find an example, of course we haven't proven that our type check is sound, but we've increased our confidence. And what my experience has been is that usually what I do is fuzz testing in Rust is like Nico says something that he thinks is true and then puts it on Zlib, and then people say, no, it's not. Look at this example program. And that's great, but it would be also nice if I didn't have to have people awake on Zlib. I could do it locally and then put it to the Zlib for figure out the hard stuff. So that's sort of where we want to get to, I guess, is I want to be able to do the fuzz testing. I want to be able to do a few other nice things. I don't want to have this hack, whatever this is, I forgot. But, and we'd like to be able to, stepping back one step, when we use, there is a version of this that we're building out that models the actual Rust type checker in its almost full complexity. And so my goal is that we can actually run that on real Rust programs, and look for interesting cases like, hey, the real Rust compiler accepts this program, but the model says it shouldn't. Is that a bug? It's a bug somewhere, but where, I don't know. Possibly in the real Rust type checker, more likely, but maybe not, maybe in the model, and vice versa, right? We can look for discrepancies and kind of test and build up the model and make it more accurate. So that's all I got. Thank you for listening. I'm happy to have questions.
Wow, very cool to see academic work also being actually used in this way for Rust in the future, at least. Very nice. So are there any questions?
That's all very cute.
Thank you.
How does it scale up to real things like Rust with trait implementation, inference, and lifetimes, and everything like that? How well does, when you really try to use it in anger, how does it stand up?
Well, let me see what I have here. I don't know how up to date it is, because I usually work on a remote desktop, but this is the local. I mean, the short version is we're finding out. I think pretty well. It doesn't. Keep in mind that, sort of intentionally, things like the trait system or type inference aren't part of the formality core, right? They're part of the rules we write, and that's because we want to check that Rust's inference rules work. While it does not yet implement the full system, it does have an implementation, for example, of coherence and the trait system. And let me see if I can find you a fun. Here's a little example where, get rid of that, where, okay, this is a little bit weird, but here's the base program that we're taking as input. We have an iterator, a trait called iterator, a trait called mirror, which defines an associated type. We implement mirror for all types A with the associated type equal to A. We have a local type and a local trait, right? And then I'm generating sample programs based on that base thing with extra things. So if it's just that base code, it type checks correctly. But if it's just that base code and I have a second iterator that causes an overlap, then indeed I get an impls may overlap. So it's scaling up to a reasonably complete thing here, but I'm not yet doing the thing I was saying I want to do of like fuzzing it against RustC and so forth. So I can't say how many fun dark corners we will discover. But I will say one other thing. My goal is, one thing I didn't say so far is that formality core is like, what if you wrote Rust and you didn't care at all about performance? What if you cloned everywhere you could just for fun? You were like, I don't need to clone it, but I'm going to do it anyway. So I don't expect this to really scale to like hundreds of lines of code. I'm happy if it scales to tens. I think it actually does scale to hundreds, but that's not really my goal. Like I just want small, usually a type system bug can be shown in like 4 lines of code. That's what I want to do. So it's absolutely prioritizing as clean and clear as possible over performance.
Another question.
Hello. I heard that Rust is either moving or has already moved to semantic lifetimes. So I was wondering, can the system describe those? How does it do it?
So Oh, what's wrong? Oh, there we go. Wrong command. I've been playing with this, and I've been playing. I have this other programming language. It's a toy. It's for fun. But in that context, I was trying out mirror formality to get a feel for how well does it work if I want to. And in this one, this is like a really weird way to talk about this. Well, anyway, in this one, it does handle it's kind of a playground for what might the borrow checker look like if it worked that way. And I have modeled a lot of those things in this model and found that it scales out pretty well, and I was able to test stuff. We're now in the process of sort of taking this model, or at least I'm thinking about doing this, taking this model and porting it over to Rust, right? And implementing the borrow checker, Rust's borrow checker, kind of in this style, in a similar way. So the short answer is yes, it will scale to that, and we've kind of proven it out, but not on Rust. And I expect to do it on Rust next. Rust is a little more complicated, has other things to deal with. That was the whole point of doing it here, was to, even with a model, Rust is too complicated, but if we take a model of Rust and model that, we can do it, and then we can step our way there. You want to see syntax? Okay, let's look at some syntax. I don't even remember is the problem. This language is very different in its syntax, but let's find one example. I shouldn't have opened this module. Let's look for a test. Where are they? How do I make this work? -F. Yeah, okay. Here's a test. Okay, here's a test showing in this crazy language. Like I said, this is a weird way to introduce it, but that's okay. Showing you have a class choice with a shared reference to self.pair. So it's using internal references within the struct2, which is, I think is something we can do in Rust if we revamp our model. And I'm able to create a pair like this and share it around. So this is like, I guess going to Jim's point, this is showing the system scaling up to kind of new languages and languages that do other kinds of interesting type checker ones. I want to show one that gets an error somewhere. Oh, here's a fun error. One thing I've noticed, it might be nice to trim these errors a little bit, because the only important part is sort of this last part here of why did this exactly fail. But what is this example doing? I don't know. These are too complicated. I can't find a nice simple one that looks easy to explain, but this is doing something bogus.
I might have just missed this in the talk, but you seem to have made something that helps you construct an AST using grammar rules, and that helps you make inferences over it. There's like a bajillion frameworks that do this already. What is the reason to remake that in Rust?
Good question. That's actually a really good question. Because initially, I didn't want to do it in Rust. I built the whole thing in PLT Redux. It was beautiful. PLT Redux was a great system. But I had this problem. I want Rust contributors to use it. My goal is that we're going to have a model that is going to be, when you write an RFC that touches the type system, maybe not you, but somebody is going to take that idea and extend the model before we finalize it. Right? Before we stabilize it, we will model it and test it and fuzz test it and play with it, and that's how the types team will come to understand it. But for that to work, it turns out nobody wanted to learn Racket. They're used to Rust. They wanted to work in Rust. It makes sense. But also, what I found was many of those systems, at least the ones I played with, weren't designed for long-term engineering, right? Like Redux was explicitly designed to be a playground that you use also in the short term. Like you build a little example, you learn some stuff, and then you throw it away. And so trying to maintain that over time, it didn't have the type checking and so forth. I was like, why can't I just use Rust? Like I want to write a match and know that I have exhaustively covered all the cases, and I want to do all the things that Rust does well. So actually, I found the two blend together really well, that using Rust, the system feels playful, but it gives me the nice Rust type checking guarantees that I'm accustomed to and finds a lot of stupid bugs. I mean, we even saw it here, right? Like I commented out one line, and all of a sudden I'm getting warnings about unused variables and stuff like that. So that kind of helped me already, before I even get to running my test, weed out most of the stupid bugs that I had to deal with. I can't say that I explored every single system, but the ones I tried, this was just a better experience for what I'm trying to do.
All right.
I have one question. You have this nice notation which came from mathematics, of course, from the programming language papers. Why did you choose to make it look like those inference rules in the papers?
As opposed to like
Yeah,
just Rust code or something?
Because you want to appeal to the theoretical programming language researchers, or is it reduces it boilerplate?
There's a reason. I guess one, it's a good question. There's a reason that the papers use that notation, is sort of the short version. It's a really good notation, once you get used to it, for thinking about your type system and writing those rules down. It's very concise. And so what I found in formality, actually, I didn't show you all of this, but actually it's a bit of a hybrid, right? Like, you kind of saw it when you wrote the program that first calls check program and then executes it. That was just regular Rust code. Or the environment, those methods, those were just regular Rust code. But then some of the stuff was in type rules. The actual rule of thumb that I've been following in mere formality is sort of, I actually use Rust syntax whenever I can. And it usually makes sense. For anything that's like purely deterministic, it makes a lot of sense. But when you get into trait matching and when you get into some of the more complicated type rules, there's a lot of sort of options. And in the Rust compiler, we've written a bunch of potentially correct code that like tries to decide which of those options to use in an efficient and thoughtful way. But mere formality just tries everything, right? It's just like, okay, you got 4 options. Let me just try them all and see if any of them work. And so that takes a lot of the load off of you, the person writing the rules, because you don't have to think about how you decide which rule to use. That's somebody else's problem. You just have to think about, if you took one of these rules, would it be correct? Right? Would it be correct to accept it in the case that these hypotheses match? And you can think about each rule one at a time, because it doesn't matter which rule you take, they should be correct no matter which one. So that sort of simplifies your mode, and I found it's just a really helpful construct. So I guess I use it because it's good. There's a reason everybody uses it. It makes sense.
Okay, so final question.
First of all, thank you so much for this talk. It was amazing. I really enjoyed it. I had a question. I remember hearing that the Rust language doesn't technically have a formal specification. Do you see this as part of moving in that direction as well in the future?
It's a good question, and I'm glad you enjoyed it. And yes, I do see this as part of moving in that direction. So we've got a couple of efforts going on that are sort of interrelated, and I think time will tell how they end up playing out. One is there's the spec working group that's actually kind of authoring a spec, starting from the Ferrocene work. Actually, Mara's here. Mara works on that. That's one effort, and that's going to produce, I think, something closer to what you would expect if you go to a traditional Rust language traditional language specification, right? And then you have sort of mere formality, and you also have Ralph Young's mini Rust, which is a different, sort of similar but different effort to formalize the unsafe code rules. And they're both basically written in Rust code, right? They're both executable, very precise definitions in some sense of different parts of Rust. I don't know exactly how they're going to end up relating. Maybe it's just that we'll check for consistency. I kind of like the idea that the sort of English language spec will not go into all the detail of saying exactly how the borrow checker works or exactly how the type checker works, but it'll say something like, there is a borrow checker, and it guarantees this invariance. You know, your program doesn't reference memory like this. Your program doesn't do that. And then we can sort of test, if maybe mere formality defines the borrow checker very precisely. We can test it against those invariants and say, can we actually find an example that violates those invariants and passes the type checker? That's a problem, right? That's a bug somewhere. Either the invariants are wrong or the mere formality is wrong. So I think that's a nice separation. That's what I'm interested, at least for the first draft, but maybe over time we'll find a different relationship is better. I don't know.
Okay. I don't think my mic is working. Okay, so thank you, Nico, for this fantastic talk. Yeah. And I think that is this for this conference, right?
That was the last talk, yes.
Yeah,
absolutely.
Yeah.
Okay, we have a couple of last things that we want to do. First of all, we want to say that there are still boats for today. So they'll leave at 7 and 10 minutes later, so 19:10. The time, not the date.
Yeah.
So they'll both head back directly to Delft Station. There's no tour today, so it's just directly to station, get home as quickly as you can, by boat at least.
Yeah.
Well, also, you might have, we've said this a couple times, there was a live stream. It's actually still going on probably, which is also already up on YouTube. But of course, we'll be publishing the talk separately as well, and we'll get that done fairly soon. So if you want to rewatch any of the talks that you've seen today, we'll notify you. We'll notify you on, well, the socials of RustNL. We don't have a slide for it, unfortunately, but it's RustNL everywhere, right? Like Mastodon, or the thing formerly known as Twitter, or you know, wherever. It's RustNL. You can find us. You found this conference, right? So you've
yeah.
Right, and then finally, we want to get a little bit crazy here on stage by inviting all of the volunteers and the speakers on stage for a big final celebration.
So could all volunteers and all sponsors please come up here?
Yes, everyone. And watch out for the water over there, because it's good. It might be full up here on stage. Just to sort of show the insane amount of work that went into this, how many people were necessary to make this all possible. We have the volunteers in the yellow shirts. We have Erik and Jonathan and Laura. And no, we're mingling. We're mingling. Of course we are.
Make multiple cheers.
Please let me take my natural position.
Yes. All right. Okay, so please give it up for all these amazing people. All right, and then we want to thank, of course, Lijm en Cultuur for hosting us here. We've had an amazing time. We think this is an amazing venue. And we do hope to see you again next year, ? Please check whatever social media you're checking to keep up to date with that, because, I don't know, we've had fun and we want to do this again, and we hope to see you there. We're doing it again. I'm hearing already. Nice.
And lastly, I want to thank all of you for coming to this great conference, of course. Without you, this wouldn't also happen, so thank you. And then that means that we can have drinks now, right?
That means that we can have drinks, absolutely, because there will be drinks. Go have drinks. Okay, I'm still on. James Muntz has asked me to say one more thing. If you want a postcard, like this one, they have to do what?
We have 50 of them. They're going to be at the one variable booth.
We have 50 of them. They're going to be at the one variable booth. Go get your postcard.